Section 21 of Chapters on Evolution by Andrew Wilson. This LibriVox recording is in the public domain. Chapter 8, The Evidence from Missing Links, Part 2. Summing up these preliminary observations on the theory that missing links are by no means so necessary on a fair showing of nature's ways and polity as might be supposed, we may submit, firstly, that the favorable variation of a species is a slow process, depending not merely on changes in the constitution of the included animals or plants, but on many other external causes, such as changes of climate and the like. Secondly, in connection with this first discouragement to the mixing of specific characters, we must remember that detachment of land surfaces will account for the absence of intermediate forms, and in cases where such forms have existed, they would be developed, as we have seen, in fewer numbers than the species they would tend to connect, lesser numbers implying few chances of either actual or geological preservation. But we may not forget that up to the present stage we have been merely contending for the relevancy of the indictment. Supposing our objections to the invariable necessity for missing links have been maintained, there yet remain very many instances wherein, as the evolutionist would freely admit, such connections require to be supplied, theoretically or actually, for the support of his case. The connected chain of life which the evolutionist postulates implies the presence of numerous links. The chief question relating to the exact stages or points at which these links are demanded, and this question again depending on another, what is or was the exact sequence and order of development? Suppose Mr. Browning to be as correct in his poetic rendering of the descent of man, as he is, judged by ordinary theories of evolution, absolutely incorrect, when he says, in Prince Hohenstiel-Schwangau, that mass man sprang from was a jelly lump once on a time. He kept an after course through fish and insect, reptile, bird, and beast, till he attained to be an ape at last, or last but one. Then, according to the poet's rendering of man's evolution, his descent would imply connecting links between the amoeboid or protoplasm stage of his existence and the aftercourse, and also between the successive stages of which that aftercourse is alleged to consist. Fortunately for scientific criticism, poetry possesses an invaluable commodity known as license, and it may suffice in the present instance to remark that the sequence and succession of life indicated by the most psychological of modern poets are certainly not those held by Mr. Darwin or any other competent biologist. Man's descent from the gorilla, the chief element in the evolutionist's creed as propounded by popular notions and by a dogmatic but unlearned theology, is after all but the baseless fabric of a vision, from which a better acquaintance with the facts of nature and with theories explanatory of these facts will most effectually awaken the unconvinced. The knowledge of what evolution really teaches and reasonably demands constitutes, therefore, the first condition for ascertaining what missing links are required. To bridge over the gulf between the gorilla or any other anthropoid ape and the human type may be the mental bane and lifelong worry of unscientific minds contorting the demands of evolution. Such a task is certainly no business or labor of Mr. Darwin and his followers, or of any other school of evolution. And Mr. Darwin, writing in his Descent of Man, and after a review of man's theoretical origin, is careful to add, quote, "But we must not fall into the error of supposing that the early progenitor of the whole simian or ape-like stock, including man, was identical with or even closely resembled any existing ape or monkey." Unquote. We must, in truth, look backwards along the files of time to the point whence, from a common origin, the human and ape branches diverged, each towards its own peculiar line of growth and development on the great tree of life. Thus much by way of caution in alleging how or what missing links are to be supplied. The contention that, even on the showing of the evolutionist, the connecting links between distinct groups of living beings are not supplied even to the extent he himself requires, is answered in the expression of Mr. Darwin already quoted, namely, the imperfection of the geological record. No fact of geology is more patent than that, to use Sir Charles Lyell's words, quote, "It is not part of the plan of nature to write everywhere and at all times her autobiographical memoirs. On the contrary, continues this late distinguished scientist, her annals are local and exceptional from the first, and portions of them are afterwards ground into mud, sand, and pebbles to furnish materials for new strata." Unquote. The very process of rock formation consists in the rearrangement of the particles of previously formed materials, and the manufacture of new strata implies the destruction of the old with the included fossils of the latter. The geological series is thus certainly a detached and discontinuous collection of formations, interrupted by gaps of considerable and often undeterminable extent. Of the contemporaneous life history of the globe, during the periods of time represented by such gaps, we have no record whatever. But even when the materials for forming a detailed history of any past period of our globe are found in tolerable plenty, the record is never complete. Quote, "We can never hope," says Lyell in a most emphatic passage on breaks in the sequence of rock formations, "to compile a consecutive history by gathering together monuments which were originally detached and scattered over the globe. For as the species of organic beings contemporaneously inhabiting remote regions are distinct, the fossils of the first of several periods, which may be preserved in any one country, as in America, for example, will have no connection with those of a second period found in India, and will therefore no more enable us to trace the signs of a gradual change in the living creation than a fragment of Chinese history will fill up a blank in the political annals of Europe." Unquote. Add to these considerations the brief chronicle of a long and important chapter of geological history, namely, that soft-bodied animals and plants are rarely preserved as fossils, that land animals are but sparsely represented in any formations as compared with marine forms, and that even metamorphism, or the alteration of rocks subsequent to their formation, is known to alter and obliterate their fossil contents, and we find reasons of the most stable and satisfactory kind for the imperfect nature of even the fullest records of rocks and of their fossils that man has been able to obtain. But in what direction does the positive evidence we have been able to obtain lead? Clearly to the side of evolution, and towards the supply of missing links, in a fashion which even the most sanguine expectations of scientific order could scarcely have hoped to see realized. Bearing in mind that vast tracts of rock formations are as yet absolutely unexplored, the present subject is seen to be one to which each year brings its quota of new and strange revelations. And at the most, any one record of what has been done toward supplying missing links must be held to be merely provisional, and to serve but as a prelude to the discoveries of a succeeding period. Especially within the last few years, however, has the evidence of the existence of animals which may fairly be deemed missing links accumulated in a very marked degree, and in some cases in a very astonishing fashion. The reader has but to become informed of recent discoveries amidst the tertiary rocks of North America to learn the surprising revelations concerning intermediate forms between existing groups of mammals or quadrupeds, which chiefly through the researches of Professor Marsh have been added to the conquests of science. What, for example, is to be said of the zoological position of the huge Dinoceras and its allies, creatures as large as existing elephants, and which, from the examination of their skeletal remains, can at best be regarded as intermediate betwixt the elephants themselves and the odd-toed ungulates or hoofed quadrupeds, such as the rhinoceros, etc.? Dinoceras thus possessed 2 large canine teeth, 6 small molars on each side, and 4 horn cores, besides a pair of similar structures in front of the upper jaw. Or again, which rank, save that of an intermediate position, and as a veritable group of missing links, can be assigned to the extinct quadrupeds, included by Marsh under the collective name Telodontia, the remains of which occur in the Eocene tertiaries of the United States? For how else should we classify animals with great front teeth, like the rodents or gnawers, grinders like the ungulates or hoofed quadrupeds, and a skull and skeleton generally like that of the carnivorous bears? Or once more, what can be said of the affinities or relationship of the extinct toxodonts, also from American deposits, in which the characters of rodents are united to those of ungulates and edentates, the latter being a group of animals represented by the existing sloths, armadillos, and anteaters. Nor is the list of extinct quadrupeds, which fall into no existing group but present a union of the characters of several distinct divisions, exhausted with the foregoing brief chronicle. Again drawing upon the well-nigh inexhaustible treasure house of geological specimens in the recent deposits of the New World, we find the extinct Macrauchenia connecting the odd-toed hoofed mammals with the even-toed division. Passing to the whales and their kin, we find the extinct Zeuglodon with its well-developed teeth, a feature unusual in living whales, appearing to connect the whale tribe with the seals and their allies. Similarly, the curious Anoplotherium of the Eocene Tertiary deposits appears to connect the swine race with the true cud chewers or ruminants, just as the Paleotherium itself, one of the first animals whose remains were disinterred from Montmartre, connects the pigs and tapirs with the apparently far-removed rhinoceros. The case for the existence of missing links wherewith the at present distinct orders and suborders of quadrupeds may be connected would thus seem to be very strong. There would appear to be more than sufficient cause to account for the hopeful spirit of the evolutionist, whose scientific prophecy that philosophic research into the nature of fossil organisms, begun by Cuvier in the now classical quarries of Montmartre, is destined to powerfully aid his cause, seems likely to be realized, when it lies in the power of the naturalist to point, as well he may, with pride, to the perfect series of forms and missing links which connect the one-toed horse of today with the curious 3-, 4-, and 5-toed steeds of the past. One may overlook the jubilant tone of the evolutionist in the more silent and deeper satisfaction with which mankind at large is given to welcome the demonstration of a great truth. It is of such a demonstration that Huxley writes, quote, "On the evidence of paleontology, the evolution of many existing forms of animal life from their predecessors is no longer an hypothesis, but an historical fact. It is only," he adds, "the nature of the physiological factors to which that evolution is due which is still open to discussion." Unquote. But not merely in the highest class of the animal world have intermediate forms been discovered. The case for evolution grows in interest when we learn that in the lower ranks of vertebrate life, groups of animals, separated apparently by the widest of intervals, are now being linked together by the discovery of intermediate fossil forms. The best known example of the latter facts is found in the relationship which may be now regarded as being clearly proved to exist between reptiles and birds. Were we to search the whole animal kingdom through for examples of creatures of thoroughly different appearance, habits, and general conformation, no two groups would fall more familiarly to hand than birds and reptiles. There would indeed appear to be no similarity or likeness between the secretary bird, which daily devours its quota of snakes, and the prey upon which it lives, or reversing the comparison betwixt the unfortunate bird and the serpent whose stony gaze has allured it, literally, to a living death. Activity of organization on the one hand would be opposed by a torpidity of action on the other, beauty of form and color by appearances frequently grotesque, and often in popular estimation at least repulsive. The contrast is one which, in the popular view, would be complete and perfect in every respect. Birds are warm-blooded and have a 4-chambered heart. Reptiles possess a slow circulation, a low blood temperature, and a 3-chambered heart, which, however, in the crocodiles becomes 4-chambered. The former class is covered with feathers, the latter with scales, bony plates, or both. The forelimbs, modified for flight in the bird, are never thus used in reptiles, the so-called flying lizards possessing no true powers of flight, but being enabled by a parachute-like arrangement of their front ribs to take flying leaps from tree to tree. Birds, as we well know, want teeth, and although in tortoises and turtles, as typical enough reptiles, a dental apparatus is also wanting, the reptilian character tends decidedly towards a large and perfect display of teeth. A closer inspection and comparison of the skeletons of the two groups, such as may be made in a very general view of their bony possessions, would reveal several interesting points of likeness and also of divergence. Thus, both classes have a lower jaw which may be called compound, since unlike the simple two-halved lower jaw of quadrupeds, that of birds and reptiles is composed of numerous pieces united to form the single bone. Then also this lower jaw is joined to the skull, not of itself and directly, as in man and quadrupeds, but by a special bone named the quadrate, which, curiously enough, by a wonderful process of alteration and metamorphosis, becomes represented in man and quadrupeds by one, the malleus of the small bones of the ear. Such, among others, are a few points of agreement between reptiles and birds. But plain grounds of distinction are apparent within the same region of dry bones. A bird has never more than 3 fingers, thumb and 2 next digits in its hand or wing, and the supporting bones of these fingers, corresponding to our palm, are united together. The reptile's fingers are never so few as 3, and their palm bones, moreover, are not ossified together. The merry thought of the bird, indissolubly associated with mystic forebodings of hymeneal nature, consists of the 2 united collar bones, such a disposition of the collar bones being unknown in the more prosaic reptilians, and the great keel, seen on the bird's breastbone, is wanting on that of living reptiles. Next in order we find that the sacrum, or bone wedged in between the haunch bones, consists in birds of a goodly number of vertebrae or joints of the spine, whereas in the reptile 1 or 2 vertebrae form the sacrum. In all birds, save the ostrich tribe, the 2 haunch bones are not united below or in front in the middle line. In reptiles such a union does take place, this union indeed being also seen in man and quadrupeds. In birds the tail terminates in a plowshare bone, giving support to the oil gland, the secretion of which is used in preening the feathers. In reptiles, no such bone exists, and the joints of the tail simply taper towards the extremity of the appendage. The axis of the thigh bone in the bird, like that of quadrupeds, lies parallel with the median plane or axis of the body, but in reptiles, the axis of the thigh makes an open angle of varying dimensions with the median plane. The ankle of the bird is peculiarly formed inasmuch as the upper half of the ankle or tarsus becomes united to the lower end of the shin bone or leg, whilst the lower half of the ankle unites with the bones corresponding to those of man's instep, the union producing the so-called tarso-metatarsal bone. It is this bone which becomes so greatly elongated in the waders such as the storks and ibises. As seen in the young fowl, the shin or leg bone bears at its lower extremity the astragalus of the ankle, shortly to be firmly united to the leg by bony union. The latter condition is where the astragalus has become united to the tibia or chief leg bone, the other bone of the leg, or fibula, being rudimentary. Such a complete union of ankle bones with the leg is not seen in any living reptiles. Whilst the latter have 4 toes as their least complement, birds have never more than 4, the 5th toe being invariably wanting. And whilst in birds the bones of the instep unite with the lower half of the ankle to form a single bone, in reptiles the instep bones, or metatarsals, are not united together and are distinct from those of the ankle. Thus much for dry details. The reader who has taken the trouble to follow this category of the personal characters of birds as compared with those of reptiles will probably find that the somewhat extended examination will assist his comprehension of certain abnormalities in the structure of several extinct forms of bird and reptilian life, since many of the characteristic features of each class just detailed will be found to have been curiously modified and often united in the missing links which bind these 2 groups of animals together. It may be firstly asserted that the ostriches, cassowaries, and their relatives differ from all other birds in possessing a flat, shield-like breastbone instead of the normal, keeled structure proper to the class. Their merry thought is likewise incomplete, and their haunch bones are united below or in front instead of remaining open as in other birds. But he would be worse than an overbold zoologist who would venture to maintain that such points of difference meant more than the merest tendency reptile words. And the ostriches and their neighbors can hardly be denominated lynx which appreciably narrow the gulf betwixt reptiles and their bird kith and kin. But presuming that the zoologist, dealing with the birds of today, refuses assent to the idea that he can supply us with missing links between reptiles and birds, can the contents of the geologist's aviary be shown to be better adapted to supply the gap? Research here may proceed in two directions. Either we may try to discover if any extinct birds are nearer reptiles than their living allies, or we may endeavor to ascertain if any fossil reptiles exhibit a closer relationship with birds than the reptiles of today. We may very profitably discuss in brief detail both aspects of the case. Fossil birds make their first appearance in the upper oolite rock formations lying in their natural order just below the chalk. Prior to the Oolitic epoch, however, and in the Triassic rocks of America, certain large footprints supposed by some authorities to be those of birds are found. But these footprints may, at the same time, be those of reptiles, and it is safer at present to hold their exact nature as undetermined, and to assert that the first unmistakable bird fossil belongs to the Oolitic period. The lithographic slates of Solnhofen in Bavaria are rocks resulting from the consolidation of the finely powdered mud which once coated an ancient Oolitic sea or lake bed. On this fine-grained deposit belonging to the upper Oolite series, the merest traces and most delicate impressions of living organisms have been preserved, the impress of even a filmy jellyfish having thus been brought to light. In 1861, the impression of a single feather was found, and later on in the same year, a Dr. Haberlein of Poppenheim brought to light the fragments of a skeleton which was soon discovered to be that of a thoroughly unique kind. This scientific treasure was duly purchased for the British Museum and was named the Archaeopteryx macrura. The skull of Archaeopteryx was wanting in this first specimen, but the leg, foot, pelvis, tail, shoulder, and some of the feathers are well preserved. And by these relics the materials for a strange history was in part supplied. Of the bird nature of this creature no doubt exists. In the matter of its feathers and feet it is wholly birdlike, but it is also discovered to differ very materially from all known birds. Thus, firstly, Archaeopteryx possessed a long tail exactly resembling that of a lizard, consisting of some 20 joints, each of which supported a pair of quill feathers. Then, secondly, no plowshare bone was developed. The fingers, united by bony union in existing birds, were free and reptile-like in Archaeopteryx, and whatever their number may have been, it is certain that these fingers were provided with reptile-like claws, such as are seen in no living bird. End of Section 21. Chapter 8, The Evidence from Missing Links, Part 2. Section 22 of Chapters on Evolution by Andrew Wilson. This LibriVox recording is in the public domain. Chapter 8, The Evidence from Missing Links, Part 3. Such were the details of Archaeopteryx structure at hand till the last 3 years or so. In 1879, Professor Karl Vogt made a communication concerning a fresh specimen of this ancient bird, found in the same deposits which afforded the previous specimen. The new specimen was singularly complete, and its wings were unfolded as if death and fossilization had overtaken it in the act of flight. Its examination revealed certain startling features, which only served to confirm in an unmistakable manner the thoroughly intermediate nature of this animal. Its upper jaw bore 2 small conical teeth. The breastbone is reduced to 0, and whilst its arm bones present no features peculiar to reptiles or to birds, its hand can be compared neither to that of a bird nor to that of a pterodactyl, but to that of a 3-toed lizard. If the feathers had not been preserved, says Vogt, no one would have ever suspected that from the examination of the skeleton alone of Archaeopteryx, this animal was furnished with wings when alive. Head, neck, chest, and ribs, tail, shoulder girdle, and arm or wing are all built on a reptilian type. The haunch is more reptilian than bird-like, but the hind limbs are those of a bird. The reptile characters unquestionably predominate in the skeleton, just as the bird characters come to the front in the feathers. Professor Vogt strenuously asserts that a study of Archaeopteryx shows that it is neither bird nor reptile, but that it is a decided link betwixt the two classes. It is a bird by its feathers and hind limbs, it is a reptile by the rest of its structure, and it is, moreover, a bird only insofar as we regard its type as having emerged from a reptilian stock. The birds to be presently described from the American chalk are later developments. As such, they are nearer the birds of today, but they retain the reptilian teeth, whilst the rest of their organization has been evolved along the lines of bird structure. Professor Vogt further insists on the fact that the adaptation to flight is not necessarily combined with an erect position, since the extinct pterodactyls and the living bats illustrate cases in which that position was and is not maintained. The bird-like hind feet of the Archaeopteryx must be viewed as having been independent of flight, and as related to the possibility of sustaining the body on the hinder feet alone. In other words, we are not specially entitled to concern ourselves with the question of flight in this ancient animal, and the consideration is worth attention in dealing with the affinities of the Archaeopteryx. Finally, as Vogt points out, there is a complete affinity betwixt the scale of the reptile and the feather of the bird. The feather is, in fact, the further modification of the scale, and we may therefore, quote, imagine the ancestors of the Archaeopteryx as lizard-like terrestrial reptiles having feet with fine, hooked, free digits, showing no modification in their skeleton, but having the skin furnished at different points with elongated warts, downy plumes, and rudimentary feathers, not yet fitted for flight, but susceptible of further development in the course of generations, unquote. But that this odd relic of the oolite leads us decidedly in the direction of the reptiles by its tail and its hand, there can exist no reasonable doubt. Skepticism may exist on this latter point, but the doubt is neither of a learned nor of a scientific kind. We may not say that Archaeopteryx actually leads us from any one bird to any one group of reptiles. It rather stands intermediately and alone. But even in its solitary position, it certainly makes the gulf betwixt the two classes seem less formidable. Next in order from the aviary of the geologist may be produced evidence of the existence of reptile-like birds in a most interesting series of fossils obtained from the chalk of Western America by Professor Marsh. About 1871, a headless bird skeleton was discovered in the upper chalk of western Kansas. This bird evidently resembled our living divers and was duly christened Hesperornis regalis. Like our living ostriches, emus, and their allies, this extinct bird possessed no keel on its breastbone. It had the merest rudiments of wings, and certain reptile-like resemblances seen in its haunch bones made geologists naturally anxious for the realization of their hopes in the discovery of a complete skeleton. In 1872, fresh discoveries rewarded the patient and indefatigable search of Professor Marsh. Not only were the missing parts of the Hesperornis duly obtained, but the remains of another and still more remarkable species, Ichthyornis dispar, of extinct birds, were duly brought to light. By the new discovery, both Hesperornis and Ichthyornis were found to possess teeth, the former having its curved teeth set in a common groove in the jaw bones, whilst Ichthyornis makes a further advance towards perfection in dental apparatus in that its 20 or so teeth of each jaw were lodged in distinct sockets. The importance of these facts as bearing on true reptile-like characters in birds may be readily imagined. No living bird possesses even the semblance of teeth, if we accept the horny ridges of the merganser's bill. Prior to Marsh's discoveries, no fossil bird was known to have been provided with true teeth, although indeed in certain bird remains described by Owen from the London clay, Eocene of Sheppey, under the name Odontopteryx, the jaws were provided with bony projections. These projections, however, are not true teeth, which, as many readers may know, do not resemble bones either in development or structure, being developed from the gum or lining membrane of the mouth, and not from cartilage as true bones usually are. Doubtless these bony projections aided Odontopteryx to catch its finny prey, as the horny ridges of the mergansers enable them to retain the fishes they so dexterously capture. One curious bird, Phytotoma, A South American leafcutter certainly possesses a double row of bony projections on its palate. But even this novel and unusual addition to the list of bird possessions bears but a faint resemblance to the bony teeth of Odontopteryx, as these latter in turn are an entirely different and relatively modern feature of the bird type, when compared with the true teeth of their American cousins of the western chalk. The Ichthyornis, moreover, diminishes the distance betwixt birds and reptiles in yet another fashion. The joints of its spine were concave at either end, a conformation familiar to us in the joints of the fish backbone, utterly unknown in living birds, but common enough in reptiles. This character alone, in the eyes of the naturalist, becomes invested with an importance hardly to be overestimated as regards its reptilian relationships. And in Hesperornis, also, certain features in addition to those already noted show unmistakable marks of affinity to the reptile type. The teeth of this latter bird, set as already remarked in a common groove, strongly remind one of the manner in which the teeth of certain lizards are fixed in their jaws. Some of the teeth of this curious bird also exhibit the manner in which one series of teeth was replaced by another. For as most readers know, reptiles and fishes possess an unlimited supply and a continual succession of teeth. The old teeth are ousted from their sockets by new teeth which are developed at their bases. And in the jaws of Hesperornis, such a manner of tooth formation exactly imitating a common reptilian mode of renewal is plainly to be seen. The tail of this great diver of the chalk seas was lastly, like that of the Archaeopteryx of the Oolite epoch, and exhibited a very different structure from the caudal appendage of existing and of other fossil birds. At its middle and under parts, the joints of the tail present long projections of flattened shape, which strongly suggest the idea of the tail having been a rigid, unyielding member insofar as a side movement was concerned, but, like that of the beaver, being probably mobile in a vertical direction, and being thus of use in the diving movements of its possessor. The last joints of the tail were massed together, but in a fashion different from that in which the plowshare bone of living birds is formed. Insofar as the birds themselves have rendered an account of their past history, it is clearly seen that their affinities to reptiles become very strongly marked in various directions, especially in the structure of the spine and in the possession of true teeth. Ichthyornis, in the matter of its hollowed spine bones and in that of its socket-implanted teeth, is a more modified and more truly reptile-like bird than Hesperornis. This latter, again, approaches much nearer reptiles than Odontopteryx of the London clay, which latter, as becomes its nearer approach to the existing order of affairs, presents a less marked relationship with the dragons of the prime. But what evidence, we may lastly ask, do the reptiles afford, on their side, of any tendency towards the bird type? Have the reptiles remained as passive to advance and evolution as they would appear at first sight to remain today, or does their history but repeat the changes and variations exhibited by their bird neighbors? Let the history of the reptile class in the past answer these queries. A considerable number of fossil reptiles are ranked to form a distinct order or division, marked by various near approaches to the structure of birds. A single example of this curious group will suffice to show the intermediate nature of its included forms. Once again, the lithographic slates of Solnhofen yield a rich reward to geological investigation and present us with the fossil skeleton of an animal which in the flesh attained a length of about 2 feet. This is the Compsognathus of the geologist, a long-necked reptile possessing a small head, the jaws of which, however, were armed with teeth. Its forelimbs were short, its hind limbs being long and bird-like. Like that of birds, its thigh bone is shorter than its leg bone. As in birds, the upper half of the ankle bone of Compsognathus unites with the lower part of the leg, but the lower half of the ankle was not, as in birds, united with the instep bones or metatarsals, which are 3 or 4 in number, long and slender, and which in Compsognathus support the second, third, and fourth toes. A mere trace of the instep bone of the 5th toe exists, and the first or great toe is of small size. In all birds, the 5th toe is entirely wanting. Looking at the structure of Compsognathus, and of its fossil allies, such as Iguanodon, little or no doubt can be entertained that these reptiles were capable of resting on their hind limbs in bird-like fashion, and of walking or hopping after the fashion of the feathered bipeds, to which indeed, by a use of the imagination, strictly scientific, we may regard this reptilian group as having in due time given origin. It is unquestionably to the struthious birds, that is, to the ostriches and their allies, that this curious reptile bears the closest resemblance, and a comparative glance at the hinder extremities of the crocodile, bird, and its reptilian neighbor will suffice to show the marked resemblances and gradation which connect and at the same time distinguish this curious series of forms. The Compsognathus limb stands intermediate betwixt the saurian and the bird, and, strictly judged, is comparable most nearly to that of the unborn chick. These dragons of the prime, known as Iguanodon and Megalosaurus, from the chalk and oolite, are near relations of Compsognathus. When we think of the size of these reptiles, which attained a length of from 40 to 60 feet, and of the probability that, like their diminutive neighbor, they may have walked on 2 legs, the origin of the giant footprints of the Triassic sandstones would appear to present no special difficulties in the way of satisfactory solution. Mention must here be made of the curious pterodactyls, or those extinct reptiles of the lias, oolite, and chalk, in which a wing member or fold of skin, similar to that seen in bats, stretched from an outer and enormously elongated finger of each hand to the forelimb, sides of the body, and hind limbs, and between the hind limbs and tail. By aid of this wing membrane, these literal flying dragons must have winged their way through the air with ease and speed. Their breastbone was keeled like that of the bird, their shoulder girdle was bird-like, and their bones, as in birds, were hollow, and were filled with air in place of marrow. The pterodactyl brain was essentially bird-like, but the hind limbs and pelvis were reptilian and unlike those of the bird. And these flying dragons possessed prominent jaws, usually furnished with socket-implanted teeth. The pterodactyls are thus not markedly bird-like in any sense. They do not lie in the direct line, nor form one in the series of links between birds and reptiles, but apparently represent a bird-like but independent offshoot of the reptilian branch. In any view of their nature, however, they serve to show plainly and forcibly the modification of the reptilian type for flight. It requires but a limited draft upon speculative philosophy to support the belief that reptile modification in another direction, and certainly at an epoch anterior to the appearance of the pterodactyls, probably produced the modified birds of which our existing ornithology is the collective product. Space fails us in the endeavor to describe other examples of animals which from their anomalous structure seem to connect very diverse types of living forms. Mention might be made of the interesting fact that the apparently distinct groups of living and extinct crocodiles are linked together in a very exact fashion by their bodily structure, or conversely, that it is easy to conceive of the varied crocodiles known to science as having originated by modification of a common type. The mere mention of such fishes as Lepidosiren and Ceratotus, linking their classes to that of the frogs or amphibians, or of such a mammal as the Ornithorhynchus, the duck-billed water mole of Australia, with its bird-like skeleton, and other structures of avian nature, suggests to the naturalist the idea that such anomalies are after all only to be accounted for by a theory of nature which postulates the necessity for links binding together groups which, at first sight, appear of widely varied and distinct nature. Summing up the results of this investigation in search of missing links, what may be regarded as the results of our labors, and to which side does the weight of evidence lead? To evolution and modification as the parent of all that is in living nature, or to rigidity and fixity of type and form as the rule and way of life at large? Judged by a very ordinary standard of value, the evidence appears overwhelmingly strong in favor of the former view. The demand for missing links as necessary features of the evolutionist scheme of creation is not left unanswered, where just cause is shown for the production of these connections between the life of the past and that of the present. There is neither wildness nor absurdity in the idea that the bird stock began in animals resembling Compsognathus and its neighbors, and that through modified bird forms, probably resembling the living ostriches and their allies, the further and higher development of our existing bird life was gradually evolved. The exact stages of such development we are unable to picture. The sketch is as yet in meager outline, but the outlines foreshadow tolerably well the actual details of the finished work. And what is true of the relations between reptiles and birds, or of those between the various races of crocodiles, which it is important to note, living and extinct, are bound together in a series almost as graduated and complete as are the horses and their progenitors, what is true of the connecting links betwixt quadrupeds that today appear distinct and separate must by every consideration, alike of logic and common sense, be held to apply with equal force to the entire world of animal and plant life. There is no law of evolution for one group and of special creation for another. There can be logically postulated no evolution for the lower races and some process of creation for the higher forms of animal life or for man himself. Uniformity and sequence exist wholly or not at all. Quote, "If one series of species, says Huxley, has come into existence by the operation of natural causes, it seems folly to deny that all may have arisen in the same way." Unquote. The unbiased mind, contemplating the varied phases of living nature, will stand in no dread of any conclusions respecting the order of this universe, to which evolution may lead. For, after all, evolution in tracing out the ways of nature is but the handmaid of truth, and it is with the truth, as it is in nature, that the earnest mind will most desire to close. End of Section 22, Chapter 8, The Evidence from Missing Links, Part 3. Section 23 of Chapters on Evolution by Andrew Wilson. This LibriVox recording is in the public domain. Chapter 9, The Evidence from Development, 1. The Earlier Stages in the Life History of Animals, Part 1. Among the many features which mark the varied universe of life, none are more universally recognized or more typical of the living world than those which herald the production of a new being, and which usher a new form upon the stage of existence. From the shapeless mass of protoplasm that crawls over the water weed as a microscopic speck, upwards to man himself, the varied processes of development are laid down in orderly sequence and along lines of special kind. Every living being, animal or plant, animalcule and whale, the humble lichen and the giant sequoia alike, passes through a definite series of changes before attaining the form and likeness of the parent which gave it birth. In virtue of such changes it assumes that parental form. These changes, occurring in orderly array, mark its pathway from shapelessness and physiological nonentity to the characteristic form of its race. It is development which molds the baby figure of the giant mass, and from the minute beginnings of life evolves the highest of Earth's denizens, or directs the production of the teeming swarms of animalcules that people the stagnant drop, and pass an existence none the less interesting or important because often all unknown to the larger and higher world without. It is this same process of development which, as one phase of living action, draws the sharpest and clearest of boundary lines between the world of life and that of non-living matter. Growth and increase are truly represented in the inorganic world, but these processes are different in kind from the actions which stamp the development of the animal or plant. The birth of a crystal, although regulated by definite laws, is, after all, a matter of outside regulation alone, and one in which the crystal itself is but a passive agent. New particles are added to the outside surfaces of the old and already formed particles, and crystal and stalactite thus grow mechanically and by accretion, but without active participation in the work destined to mold and form their substance. Very different are the forces and laws which regulate the production of the living form. Here the changes of form and the building of the frame are marked out in plain and definite pathways by laws essentially independent of external conditions. True, the development of the living form may be retarded by cold or favored by warmth, but these conditions leave unaffected the course and direction in which it is destined to pass towards the form and belongings of the parent which gave it birth. Stamped ineffaceably on the pages of its life history, the way of the animal or plant towards maturity is written for it, not by it. Internal forces and hidden but all-powerful laws of life direct its progress and ultimately evolve the perfect being from the shapeless germ, in which its past as derived from its parents and its future as depending in some degree at least upon itself, meet in strange and incomprehensible union. The development of a living being may be further shown to be merely a part of the wondrous cycle in which life appears to direct its possessors. From the egg or germ, development leads us to the perfect being. Next in order we consider its adult or perfected history, and in due time we may discover the adult existence to merge into that of the immature state in the production of germs, in the development of which its own life history will be duly repeated. The period of adult life in this view merely intervenes betwixt one development and another, and serves to connect those ever-recurring stages in the life history of the race which it is the province of development to chronicle and record. As a necessary item in the perfect understanding of animal and plant history, it may readily be understood how important a place development occupies in modern biology. Nor is the interest in the study excelled by its importance. The mystery of life itself might well be thought by the older physiologists to resolve itself into an understanding of the fashion in which nature molded and formed her varied offspring. The manner of development might be almost expected to explain the mystery of being, but the problem of life is left as insoluble as before, after the course of development and even the lowest grades of existence has been traced. The history of development but environs the puzzles connected with life and its nature. It leads us to the beginnings of life, it is true, but it leaves these beginnings unaccounted for, and as mysterious as before. It explains how this tissue or that, this organ or that, is fashioned and formed, and as we watch the formless substance giving birth to the formed, the indefinite evolving the defined, we might well be tempted to think that the why of nature was explained by the how. Yet the springs of life and vital action remain hidden as of yore, and the exact origin of life is a mystery as insoluble as when the thoughts of men were first directed to its elucidation. Apart, however, from the admission that the study of development has not brought us nearer to the solution of the question, what is life? The investigation of the life histories of animals and plants is fraught with high importance in another sense and in other aspects of the scientific interpretation of nature. The early observers hardly imagined that in their researches into the formation of the chick, they were laying the foundation of a study which in future days would be destined to aid man's comprehension of his own origin and that of all living beings. Aristotle's observations upon the developing chick and his bestowal of the name punctum saliens, or beating point, upon the first beginnings of the heart in the embryo bird, were in truth fraught with an importance to succeeding generations which that philosopher could barely have realized had he possessed any prophetic foresight whatever. And no less would Harvey himself have been astonished had he beheld the results to which the pursuit of his favorite study has led in these latter days. It was that great philosopher himself who first maintained that the chick was developed, not from the white of the egg, but from a minute speck or scar on the surface of the yolk, known as the blastoderm or cicatricula. In felicitous terms, Harvey enunciates his opinion that the Medici, or disciples of Galen and Hippocrates, were in error when they supposed that such important structures as brain, heart, and liver were first produced simultaneously as minute sacs or vesicles, and he disagrees with Aristotle in respect that the latter had maintained the punctum saliens, or punctum sanguinum, or heart, as the chief agent in forming the structures of the new being. Harvey ascribed to the blood itself the formative power in developing the chick. With Aristotle, however, Harvey is in perfect agreement in believing that the chick is formed not by the sudden formation of new parts outside the already formed organs, nor by the growth of a miniature and perfectly formed embryo into the larger chick, but by the gradual development and elaboration of uniform and like matter into the new and varied parts and organs of the bird. Such were Harvey's views regarding the nature of development. Of the supreme interest exhibited by the discoverer of the circulation in this study, no better proof could be cited than his own words when he maintains, quote, that it is most apparent that, in the generation of the chicken out of the egg, all things are set up and formed with a most singular providence, divine wisdom, and an admirable and incomprehensible artifice. Unquote. Harvey's doctrine of development received the name of epigenesis, which the physiologist himself defines in his 41st exercitation as, quote, the additament of parts budding one out of another. Unquote. Contrasted with this opinion is that of such physiologists as Malpighi and Leibniz. They held that the body of the chick could be traced in the egg before the first rudiment of the heart appeared, and that from the first formation of the egg and prior to incubation, the young bird was to be found perfectly formed therein. Thus, by Malpighi's view, the process of development was merely one of expansion, unfolding and enlargement of parts already formed, and this idea became known as that of metamorphosis, in contradistinction to Harvey's theory of epigenesis. So also Bonnet maintained the existence of a miniature chick in the egg from the first moment of its formation. Subsequent growth and nutrition merely expand the elements and parts of this germ into those of the adult, and thus Bonnet declares the process of development to be merely one of evolution. Thus, the doctrine of epigenesis, as enunciated by Harvey, becomes opposed to that of evolution as maintained by Bonnet and Haller, the development of new parts and structures from a structureless substance as distinguished from the mere enlargement and unfolding of the miniature but already formed elements of the frame. But when Bonnet, in 1762, in his work entitled Considérations sur le corps organisé, was elaborating his theory of evolution and less rational views on emboîtement, a theory holding that each germ is the receptacle of the germs of all future beings of its race, Caspar Friedrich Wolff had already lent his aid towards placing the Harveyan views on a secure and stable basis. Wolff showed that the scar on the hen's egg consisted of particles amidst which no rudiment of an embryo chick could be traced. He further demonstrated the changes whereby the chick was built up from these cells, and showed the process of development to be truly one wherein new parts were formed in succession and added to the already formed organs. Succeeding Wolff came Pander, who filled in the outlines his predecessor had so well sketched out by detailing the earlier stages and processes seen in the formation of the young bird. From Pander came the name blastoderm, given then as now to the substance or formative material resulting from early changes in the egg scar, and from which material all the parts of the young animal are formed. This observer also cleared the way for his successors by pointing out the presence of the 3 layers into which the blastoderm divides, each layer bearing an important share in the formation of the tissues of the developing being. To Pander came in due time a worthy successor, who may be said to have laid the solid foundations of the study of development as prosecuted in modern times. This was von Baer, whose labors each physiologist and naturalist of today must hold in grateful remembrance. He it was who, besides perfecting the details already to hand, discerned the important fact that the highest animals are developed from eggs or germs, resembling in essential nature those of the lowest. But perhaps the greatest triumph of discovery and research as represented by von Baer's labors resulted in the enunciation of his law of development, which may be briefly expressed in the phrase that, quote, development proceeds from the general to the special, unquote. To rightly understand the purport of this axiom, our preliminary studies in the constitution of the animal kingdom must be borne in mind. The animal world, as we have seen, is divided into a number of great types, the most consistent and most firmly established of which are the vertebrates, including the backboned animals from fishes to man. Molluscs, including shellfish, such as oysters, cockles, snails, and cuttlefishes, and annulose animals, or articulates, represented by animals with jointed bodies, such as worms, insects, centipedes, crustaceans, etc. Now, if the development of a number of animals belonging to any one of these three divisions is observed, the egg of each animal is seen to pursue the even tenor of its way, and to pass at first through exactly the same stages of development. Up to a given point, the stages in the development of all vertebrates, for example, are essentially similar. Sooner or later, however, development begins to specialize its course, and hence arise the differences which mark the adult forms. So also with mollusks, which in their earlier stages pass through essentially the same changes, but sooner or later diverge in their course, each organism passing on its own way to assume the special features which characterize the adult. Such was the important generalization of von Baer. Succeeding research has but tended to establish von Baer's doctrine, whilst it has also enlarged the conception he was the first to promulgate. It is now known that there are stages in early development which are common to the eggs or germs of all animals alike, and that from the common track thus pursued, up to a given point, by animal life at large, each group of animals ultimately diverges on its own special way of life. Von Baer's generalization has thus come to include the whole animal world, and has in recent times tended powerfully to support the doctrine which would explain the origin of living beings by presuming their descent from pre-existing forms, and their relation with each other as twigs, boughs, and branches of a great connected tree. The relation of development and its study to the hypothesis of evolution is thus easy of determination. It is a perfectly reasonable and most natural conception that in the development of a living being we should obtain some clue to the history of its origin and to the birth of its race. If its origin be a subject of research at all, any information concerning the stages through which an animal or plant becomes the adult organism, and by which it advances from literal non-existence to the staid solidity of mature form and perfect life, should by analogy the most natural be regarded as a veritable mine of knowledge concerning its own beginning, and by further analogy regarding the beginnings of the world of life at large. Upon such a thought is founded the dependence which modern biology is led to place upon development as a clue to the evolution of living beings. Succinctly expressed, it is thus held by evolutionists in general that the development of the individual is a recapitulation in brief of the development of its species or race. The history of the production of the individual is viewed as the abstract and brief chronicle of the changes and developments through which its race has passed in prior ages of this world's existence. It is true that such a history often appears meager and imperfect. Some of its phases become altered in the lapse of time by the influence of surroundings acting favorably or the reverse upon successive generations. As the lines of human progress are not always easy to trace, so those of animal advance and evolution frequently appear blurred and indistinct. But on the whole, the record is tolerably complete. The gaps in animal histories do not affect the main question at issue, namely that, as Darwin says, the embryo or young animal, quote, is a picture, more or less obscured, of the progenitor, either in its adult or larval stage, of all the members of the same great class, unquote. That such a study must teem with interest is a remark scarcely requiring mention, nor may it be regarded as other than a triumph of scientific research, when development may be seen to demonstrate how individual history repeats the history of the race, and how the living world of today once existed in simpler guise, and in the dim obscurity of the past, lay hidden as the music of the moon sleeps in the plain eggs of the nightingale. Although the study of animal development is in many ways an intricate branch of research, there exists no difficulty in comprehending the broad outlines which mark the building of the body in the higher as well as the lower forms of animal life. If we watch the development of some animal, such as a sponge, belonging to the lower grades of organization, we may be enabled to distinguish certain stages which not only mark sponge development, but also that of animal life at large. The simplest form of a sponge exists as a cup-shaped body attached to some fixed object. Such a form of sponge is olynthus. The walls of this cup, consisting of two layers, are perforated with holes or pores, which open into the substance of the cup, and thence into the interior, which communicates with the outer world by the wide mouth, or osculum. This sponge cup consists of two layers, of which the inner is provided with delicate filaments, resembling eyelashes in miniature, and named cilia. These cilia, by their constant movement, cause currents of water to flow into the sponge by the outer pores, whilst by the same movement the water is driven outwards by the mouth of the cup. In this way, the living particles of the sponge are supplied with nutriment, and the comparison of a sponge to a kind of submarine Venice, with canals and waterways on the banks of which the inhabitants live, is thus seen to be fully justifiable. The development of such an organism takes place through the production of eggs, which are developed in the tissues of the parent sponge, and which are merely specialized portions or cells of the inner layer of the parent body. The sponge egg, it must be remarked, presents the essential elements seen in the eggs or germs of all animals. It is a little speck of protoplasm, embedded in which we find a smaller body known as the germinal vesicle, and this latter, in turn, contains a still more minute particle, the germinal spot. When such an egg is about to undergo development, the first changes which occur in its substance are those collectively named segmentation. The egg is then seen to undergo a process of division. It divides internally and successively into 2, 4, 8, 16, etc. cells or divisions, these portions ultimately becoming so numerous that the egg at the close of its segmentation, from its resemblance to a mulberry, has been named a morula. Soon the outer cells become elongated and provided with cilia, and by means of these filaments the young organism swims freely about in the water. In this stage it is known as the planula. Next in order, a central cavity and then a mouth are formed, this aperture leading into the cavity of the cup. It is now named the gastrula, and its body is seen to consist of two typical layers, an outer or ectoderm and an inner or endoderm. These two germ layers, as we shall hereafter note, are common to all animals in the course of their development. Indeed, the formation of the embryo takes place through the subsequent development and elaboration of these two primary structures. Thereafter, this sponge embryo will attach itself to some fixed object. The outside cilia, no longer required for locomotion, will disappear, and it will assume its so-called ascula form. Other and new cilia will become developed in the inner or lining membrane of the body. The wall of the cup will next become perforated with pores, and with the inauguration of the inward and outward circulation of water, the ordinary features of adult sponge existence will thus have been attained. Such being the course of affairs in one of the simplest animal developments, we may briefly summarize the stages included therein. These stages consist firstly of the segmentation of the egg, which process produces the mulberry-like mass or morula. Next in order we find the planula with its two layers and its outer cilia. Then succeeds the gastrula, possessing an internal cavity, into which a mouth shortly opens. And with the formation of pores and internal cilia, the form of the adult sponge is duly produced. End of section 23. Chapter 9, The Evidence from Development, 1, The Earlier Stages in the Life History of Animals, Part 1. Section 24 of Chapters on Evolution by Andrew Wilson. This LibriVox recording is in the public domain. Chapter 9, The Evidence from Development, 1, The Earlier Stages in the Life History of Animals, Part 2. Selecting a form of animal life widely removed from the sponges, let us briefly investigate the stages through which the sea squirts, or Ascidians, attain the somewhat prosaic features which mark their adult existence. The adult and ordinary sea squirt presents itself as a bag-shaped organism, rooted to stones at low water mark, and bearing two apertures on its upper extremity. The resemblance of these Ascidians to an antique wine jar, ascus, is forcible enough, and the characters from which the familiar name sea squirt has been derived are also readily discernible. When prying humanity, even in the legitimate guise of the scientific investigator, presumes to handle the Ascidian constitution too roughly, these animals are given to eject water from the orifices of their jar-like bodies, a playful habit, the unpoliteness of which, from its reflex and unconscious nature, even other than scientific investigators may well excuse. Sea squirts are usually regarded by naturalists as near relations of the oysters and other mollusks, but their differences from the familiar shellfish are so numerous and so important that their separation from mollusks as an aberrant type of animals and their inclosure even in the vertebrate group is a perfectly legitimate procedure. Again, the aptness of the Harveyan motto, omne vivum ex ovo, is apparent when we find that sea squirt history begins with the production and fertilization of an egg or germ, which resembles that of the sponge and of all other animals, man included, in possessing a germ vesicle and a germ spot. Once again, as in the sponge, we meet with the process of egg segmentation, resulting in the production of a morula. Then the cells of the morula arrange themselves to form the two layers, as in the sponge, the outer layer being pushed inwards upon itself so as to form a central cavity, much as a nightcap is so modeled to fit the head. Thus our gastrula stage once again appears, and in the life history of an animal very far removed from the sponge in structure and relationship. From this stage, common alike to sea squirts and sponges, ascidian development begins to specialize itself. Another opening or depression appears above the opening which formerly led into the gastrula body. Within this depression, which at first communicates by an opening with the exterior, a part of the outer layer is contained, and finally becomes shut off from the other portions of that layer. This separated and confined part of the outer layer becomes the nervous system of the sea squirt. Next in order, we find the body to extend itself behind, so as to form a well-marked tail, within which a rod-like body, the urochord, is formed. Overlying this body at its front portion, the nervous system just mentioned is further elaborated, and muscular elements become developed in connection with the tail and its contained rod. Meanwhile, the beginnings of a digestive system and of the breathing sac are being formed, and at this stage the young sea squirt appears to be actively mobile, and to swim freely in its tadpole-like stage of development. Fixing itself thereafter by specially developed points of attachment, there begins a process of apparent degeneration in our as yet undeveloped ascidian. The tail wholly disappears, and the nervous system degenerates until but a mere fragment remains, and with an alteration of the form of the body, and some modification and further development of the other systems of organs, such as the digestive apparatus and heart, the larval ascidian becomes the mature sea squirt. It is of interest to note that in a few aberrant members of the sea squirt group, the larval or immature characteristics are retained throughout life. Such are the appendicularians, which, although ranked as veritable sea squirts, retain as a permanent belonging the tail which their neighbors possess only in the days of their youth. Within this permanent tail, the notochord appears developed as in the fleeting appendage of other sea squirts, whilst the other organs of sea squirt existence, digestive system, heart, etc., are fully developed. From the possession of this notochord, these curious animals appear as unique invertebrates, and stand alone amongst their fellows as presenting the closest resemblance to the vertebrate animals. In the appendicularians, we may perceive the existing representatives of the stock and ancestry which gave origin alike to the fixed sea squirt race and to the great vertebrate group itself. These permanent larval forms, as Appendicularia and its neighbors are termed, thus present us with the least modified members of their class, with the primitive and unchanged organism whose development in other directions has produced the highest races of living beings. Of these organisms, Darwin himself remarks that, quote, "If we rely upon embryology, ever the safest guide in classification, it seems that we have at last gained a clue to the source whence the vertebrates were derived. We should then be justified in believing that at an extremely remote period a group of animals existed, resembling in many respects the larvae of our present ascidians, which diverged into two great branches, the one retrograding in development and producing the present class of ascidians, the other rising to the crown and summit of the animal kingdom by giving birth to the vertebrata." Unquote. Ascending now to the confines of the vertebrate subkingdom of animals, we may trace the development of the curious little fish, known as the lancelet or amphioxus, a form interesting not merely as being at once the lowest fish and vertebrate, but as evincing in its development a most marked likeness to that of the sea squirt whose manner of entrance upon the stage of life we have just studied. The lancelet is a little fish attaining a length of 1 or 2 inches and found inhabiting sandy coasts in various parts of the world. Its body is pointed at either extremity, and save for a narrow fin bordering the upper and part of the lower surface of the body, no traces of the appendages commonly seen in fishes are to be found. This fish occupies the position of a very singular and anomalous member of the vertebrate series. Unlike most of its congeners, it has no skeleton or backbone, a mere soft and gelatinous cord, termed the notochord, existing in the place of and representing the spine. It has no paired fins or limbs, it wants a heart, it has no skull or brain, and its organs of sense are represented by mere pigment spots for eyes, whilst the mouth possesses a series of filaments, probably subserving the sense of touch. This little animal would seem thus to hover, as it were, on the outermost confines of vertebrate existence. Its adult characters resemble the rudimentary traits of other vertebrates, and in respect of its entire structure, and still more so of its development, it may be said to be a connecting link between invertebrates in general and sea squirts in particular on the one hand, and the vertebrate subkingdom on the other. Like all other animals above the very lowest, the lancelet's history begins with the production of the germ or egg, which exhibits in its essential structure the closest similarity to that of the sponge or ascidian. The first changes to be witnessed in the developing egg of the lancelet consist in the complete division of its substance. Segmentation of the egg of the lancelet is on an exact parallel with that of the egg of the sponge or the sea squirt. We shall presently note that this segmentation is also imitated, completely or in part, in higher forms of life. As in the sponge, the blastoderm is duly formed, the infolding of this blastoderm and the formation of the pocket-like gastrula taking place exactly as in the development of the sea squirt. Furnished with its eyelash-like cilia, this gastrula lancelet swims freely in the surrounding water. Not a trace of its vertebrate character can be observed at this stage. It might be the forward progeny of a worm, or might be ranked as a developing snail, whilst if it were alleged to be an embryo starfish or a baby sea squirt, the zoologist would probably own his inability to say which assertion was correct, or most in accordance with the appearance of this curious organism. The succeeding course of events in the gastrula stage brings an elongation of the body, and from the inside or pocket-like cavity of the gastrula, the digestive tube of the future lancelet is seen to be gradually formed. Then also appear the first marks and traces of its vertebrate relationship, and of its kinship with the aristocracy of the animal kingdom. The flattened aspect of the body now shows a tendency to develop 2 ridges or projections, which soon meet and unite in the middle line to form a tube, enclosing the nervous axis. This nervous tube remains open for a time in the lancelet. The body of the young fish now assumes somewhat of the appearance of a flattened cylinder. It resembles closely the young sea squirt, and like the latter, possesses in its back region a rod-like body, the notochord. In the lancelet, however, the notochord extends completely from head to tail. The identity of the 2 developing bodies may be best demonstrated by a comparison of their longitudinal sections, where the arrangement of parts and organs is seen to be essentially similar. The next change results to the forepart of the body, where the throat is seen to become cleft or perforated by the gill slits, a sea squirt feature again being apparent in this latter phase of development. It is equally curious to note that similar clefts, to be more specially alluded to hereafter, appear in the development of all other vertebrates, including man. These clefts in fishes bearing gills, but in reptiles, birds, and mammals becoming obliterated. Ultimately, the free-swimming lancelet assumes habits of more staid character. The notochord, which in most other and higher vertebrates is replaced by the spine, remains in the lancelet as the permanent representative of the backbone, just as in the appendicularia. Among the sea squirts, the urochord persists throughout life. And with the appearance of the systems and organs characteristic of its adult existence, the preparatory stages of lancelet life may be regarded as having been completed. Thus it is certain that the development of the lancelet, whilst clearly that of a vertebrate animal, is also seen to produce a low type of vertebrate organization, and to present unmistakable affinities and likenesses to the development of the sea squirts and of other invertebrate animals. Noting the absolute likenesses which exist between the development of the sea squirt and lancelet, there seems every justification for the scientific belief that both animals have arisen from a common stock. The gulf between vertebrate and invertebrate life in this view no longer exists, and the lancelet may be legitimately regarded as the parental form of all vertebrates, from the fish to man. Still higher in the vertebrate scale do our researches in development lead us when we approach the study of the chick and its early life history. And what is true of the chick's development is, with greater or less modification of details, true of the production of every other vertebrate animal, man included. In the developing egg of the bird, the yolk undergoes segmentation, as in the sponge, ascidian, and lancelet, but the process is partial in the bird, whilst it affects the entire egg mass in the development of lower life. The blastoderm is duly formed as the result of segmentation, and from this substance, seen in the cicatricula or scar of the egg, arises the future fowl, the great mass of the yolk and white serving as nutrient material for the developing bird. Soon the cells of which the blastoderm is composed are seen to form themselves in 3 layers, an outer layer or epiblast, a middle layer or mesoblast, and an inner layer or hypoblast. It may be well to remark at this stage of our inquiries the part played by each of these 3 layers in the formation of the young animal. From the epiblast arise the outer skin and the nervous system. The superficial layer of the body and the great internal nerve centers governing the frame, its movements and vital processes, thus arise from one and the same layer, a fact appearing to argue in favor of the origin of the nervous system of vertebrates from a layer which in anterior stages of existence, as in the animalcules of today, originally formed the outer and sensitive margin of the body. From the mesoblast or middle layer arise the bones, muscles, blood vessels, the underskin, and other parts, whilst the hypoblast or underlayer gives origin to the lining membrane of the digestive system and to such digestive organs as the liver, pancreas, etc. About the 6th or 8th hour of incubation, these 3 layers of the blastoderm in the chick are duly formed. Very rapidly succeed the changes which result in the production of the chick itself. A groove soon appears on the surface of the blastoderm, this furrow being known as the primitive groove, and constituting the keel of the body, so to speak. The edges of the groove finally grow together and convert the groove into a canal. A portion of the epiblast is pinched off from the remaining portion, and being included within the tube thus formed, duly gives origin to the brain and spinal cord. As 2 projections of the blastoderm grow upwards to form the spinal region, so 2 folds grow downwards and thus tend to form the body walls of the young animal. Contemporaneously with these changes, we find a structure of high importance to be gradually formed in the back region of the chick. This structure is the notochord, a rod-like body composed of a string of cells, which lies just beneath the first formed tube, or that containing the nervous rudiments. The formation of this notochord cannot but forcibly call to mind the similar string of cells which appears in the course of development in the sea squirt's larva, such a similarity being of too marked a character to admit of its being regarded in the light of a mere coincidence. On each side of the notochord the elements of the spine, in the shape of little cubical vertebrae, are duly formed from the middle layer or mesoblast. The notochord itself, a permanent structure in such fishes as the lancelet, sharks, dogfishes, etc., gradually disappears in the chick, its retrogression being apparent after the 6th day, whilst it is found to have entirely disappeared at the time of hatching, whatever of its substance remains being absorbed in the formation of the spine. The folding of the blastoderm in front and behind soon specializes the head and tail of the young animal, the head extremity presently showing 3 swellings, or dilatations, from which the brain is duly formed, and bending downwards in a highly characteristic fashion. Brain development is accompanied by the formation of organs of sense, such as the nose, eyes, and ears, which arise as pocket-like ingrowths from the epiblast or outer layer of the body, whilst the mouth is similarly formed by an infolding of the outer layer, and is later on placed in communication with the digestive system. During the third day of incubation, certain highly important structures appear in the neck of the chick. 4 clefts or slits are formed in the walls of the throat, these being named the visceral or branchial clefts. The upper edges of the clefts form thick folds, named the branchial folds, 5 folds existing to the 4 clefts, as the last cleft has its lower border thickened in addition to its upper edge. The significance of these clefts and folds will be hereafter alluded to. It may at present, however, be noted that all the clefts in the chick, save the first, are closed by the 7th day of incubation. The visceral folds contribute in an important fashion to the formation of the jaws and other structures belonging to the skull, the 2 hindermost folds disappearing in the chick without leaving any traces of their existence. The limbs begin to be developed about the 4th day and first appear as little buds projecting from a ridge, the Wolffian ridge, running round the young being from the neck to tail at about its middle portion. But it is only about the 5th day that the distinctive characters of the limbs can be discerned. By the 10th day, however, the wings and feet, in all their characteristic structure, may be distinguished. The skull dates its history from the 5th day, and only during the succeeding day may the bird type of the chick be perceived in the characters of wings, feet, digestive system, and other structures. So remarkably alike are the developing young of higher vertebrates in their earlier stages of development. Meanwhile, as early indeed as the 3rd day of life, the lungs have been formed as little pocket-like growths from the throat, and even before hatching, the chick begins to use its breathing organs. With fully formed parts and perfectly equipped for the new existence which lies before it, the chick duly breaks the shell with its armed beak, and throwing off the shriveled remnants of organs once useful in its earlier stages, enters upon the characteristic life of its species. If the development of a quadruped were traced, or the stages of man's physical progress in early life reported upon, much the same course of development as that described in the case of the chick would be chronicled. We would see segmentation of the quadruped germ as in the lancelet. We should see the formation of a blastoderm and its 3 layers, of a primitive groove, of a notochord, of 3 brain vesicles, of visceral or branchial clefts, and of other structures similar to those of the chick. Only in the latest stages should we be able to trace the appearance of the higher features of the quadruped or mammal as distinguished from those of the bird. Human development, so far as has been traced, runs parallel with that of lower forms of life, and exhibits the morula stage, equally with the sponge, sea squirt, or lancelet. Man's development is in truth but an epitome, condensed and modified it may be, but still a recapitulation of that of lower forms of life. Thus it is no mere supposition, but a weighty physiological fact, that through flitting and successive stages which exactly repeat and represent permanent forms in lower life, man finally attains to be the paragon of animals. And thus also the community of type and general structure which man shares with the lowest fish is demonstrated anew by the marvelous history of the manner in which that type is evolved, alike in its lower and higher phases. End of section 24. Chapter 9. The Evidence from Development. 1. The Earlier Stages in the Life History of Animals. Part 2. Section 25 of Chapters on Evolution by Andrew Wilson. This LibriVox recording is in the public domain. Chapter 9. The Evidence from Development. 1. The Earlier Stages in the Life History of Animals. Part 3. The marshalling of facts to form generalizations and the stringing of these facts upon the thread of a connected history is a duty which lies next to hand in treating of development and the lessons it is calculated to teach. Let us, in the first place, try to discover the place and import of Harvey's teachings concerning development as compared with those of succeeding investigators and theories. There can be no question that the researches of the 19th century have but confirmed and enlarged the observations of Harvey in the 17th. Epigenesis is seen to be the method of nature in developing the animal form with that admirable and incomprehensible artifice which Harvey so justly admired. From the primitive and undifferentiated protoplasm of the egg, modern embryology beholds the formation of the chick in a fashion strictly corresponding, in all essential details, to that outlined by the genius of Harvey. Compared with the views of Malpighi, holding that the egg contained a miniature chick, and that development was merely an unfolding or expansion of already formed parts, Harvey's description and theory of development stand forth in marked contrast in respect of their thorough correspondence with the fruits of modern research. Bonnet's theory of the evolution through the supply of nutrition of an already formed chick contained in the egg meets a like fate to the opinion of Malpighi, whilst his doctrine of emboîtement, crediting each germ with being the repository of all future germs, when taken literally, shares a like fate with his ideas regarding the evolution of a single animal form. As supplementing the ideas of Harvey by direct observation, we note the philosophic nature of the views of Wolff, through whose researches the foundations of modern embryology may be regarded as having been laid. The line of research leading from Wolff to Pander to the present day may be held to represent merely the direct continuation of the exercitations of Harvey, whose philosophizing has thus led to results of which its sage founder, with all his perspicuity, could have had no warning or idea. The details of the studies in development outlined in this chapter must now be briefly summed up. Whilst a glance at their bearings upon and teachings regarding evolution may form a fitting conclusion to the present stage of our studies. Firstly, then, it is noteworthy that the germ or ovum of all animals, excepting the very lowest, or protozoa, appears as a protoplasmic mass, which exhibits all the characters of the microscopic body known as a cell. In the lowest animals just named, the difficulty of distinguishing their germs, and indeed their entire developmental history, arises in great part from their ill-defined nature, and from the marvelous analogies and likenesses they present to their lower plant neighbors. In the biological no man's land, where the lowest animals and lowest plants meet in a confusing identity of form and function, distinctness of germ elements may neither be expected nor found. But it is at the same time noteworthy that even in this lowest group of the animal series, the observed phenomena of development occasionally present a singular resemblance to the primary process about to be alluded to, and already named segmentation, such resemblance being inexplicable save on the supposition that in these lowest forms the development of the higher is foreshadowed in dim outline. Take as an example the development of Magosphera, a low form of marine animalcule found living on the Norwegian coast by Haeckel. It resembles the familiar animalcule known as the amoeba, but during the development of new beings, the Magosphera assumes a spherical form, within which a nucleus and a nucleolus give it the appearance of a veritable egg. Next in order succeeds a process remarkably like that known as segmentation in the eggs of higher animals. In the course of this process, the Magosphera divides until a stage resembling the mulberry stage, or morula, is attained. Thereafter, the outer surface becomes ciliated, and liberated from its investment, the Magosphera swims freely in the sea. Soon this free-swimming sphere breaks up into detached fragments of protoplasm, at first ciliated, but finally assuming the adult Magosphera form. In the well-defined groups of the animal world, ranging from the zoophytes, corals, and their neighbors, coelenterate animals, up to the vertebrates, including man himself, we are presented with a marvelous likeness and an undoubted correspondence in the form and nature of the germ, and of the processes in virtue of which that germ is started on its developmental journey. Next in order, we note the occurrence in the developing eggs of all animals of that process to which the name segmentation has been given. We have seen that the germ or egg of the sponge, equally with that of the sea squirt, lancelet, chick, and also with that of mammalia or quadrupeds, exhibits this process of division. The egg, at first single-celled, becomes in this way many-celled, and the variations observable in the process itself are but insignificant when contrasted with the extraordinary uniformity in the broad outlines thus exhibited by the eggs of all animals in their first stages, and in the changes preparatory to the outlining of the future form. But the similarity between the development of widely different animals ends not thus. If the process of segmentation is universal, the morula or mulberry stage in which that process culminates is seen to be no less uniform and unvarying in its occurrence. Even among the protozoa, as we have already remarked, we may perceive stages in development which imitate the mulberry mass of higher forms. We have already traced the occurrence of this stage in the sponge and in the other life histories described in this chapter, whilst a wider survey of the animal world would serve to show that in the early history of every group the mulberry stage is to be witnessed as the first prominent landmark or halting place on the journey of life. The egg of such an animal as a tardigrade or bear animalcule, minute organisms allied to the mites and found in the gutters of housetops, thus exhibits in its development stages of a nature essentially similar to those seen in the history of both lower and higher forms of animal life. The egg itself exhibits a structure comparable with that of all other germs. In its development, the germ not only passes through the stages of segmentation already familiar to us in the sponges, sea squirts, and vertebrates, but also arrives in due course at the mulberry epoch or morula, whence the special features of the tardigrades are specialized. How perfectly these details in the animalcule correspond with the stages in the development of the vertebrates or highest animals is a fact which may be best appreciated by the comparison of the segmentation of the egg of a vertebrate animal from its commencing development to the attainment of the mulberry stage, whilst that of the frog exhibits essentially the same phases as the developing germ of bird or mammal. With Professor Alan Thompson, we may therefore hold that, quote, the occurrence of segmentation and the regularity of its phenomena are so constant that we may regard it as one of the best established series of facts in organic nature, unquote. But the further stages in development of different animals run parallel beyond the mulberry stage of progress. The morula, as we have seen, becomes the planula, a stage we saw distinctly in the sponge, and which is repeated with but little variation in the development even of the highest animals. Thus the planula appears to be well nigh as universal in its occurrence as the morula. But we saw that the planula, in due course, became the bag-shaped structure named gastrula. The wall of the planula is pushed in upon itself on one side, a central cavity being thus formed, bounded by a double wall, and communicating with the outer world by the mouth. Such is the gastrula, and in its composition we are able to discern the two primitive layers, named, as we have seen, ectoderm and endoderm, or epiblast and hypoblast. A third layer, the mesoblast, makes its appearance between these two primary membranes, and from these three layers, as we have already seen, all the structures of the future animal are in due course developed. It seems perfectly certain, then, that if the mulberry stage constitutes a first landmark in the development of the animal kingdom at large, no less does the gastrula stage form a second resting place in the track of life. Since, as Haeckel and other embryologists have shown us, the gastrula stage of development, with its primitive mouth, body cavity or stomach, and double layers, occurs equally in the zoophyte and worm, is as typical of the starfish as of the crustacean, and aids as materially in the formation of the snail as in the development of the vertebrate. After its gastrula stage, each animal form may be said to assume the special features of the group to which it belongs. At this point, the vertebrate will pass towards its own subkingdom and develop in due time the special features of the fish, the frog, the reptile, the bird, or the quadruped. Hence, as from a common point whence numerous ways and paths diverge, each animal will elaborate or develop its gastrula germ into a frame more or less complicated, and into belongings and structures suiting its rank in the great kingdom of animal life. From such a standpoint, we may discern, more clearly perhaps than at any other stage of our researches, the justice of the comparison which symbolizes the animal world and its origin by the figure of a tree, whose divergent branches bear at their extremities the apparently distinct and specialized groups of animals, but whose stem and trunk from which these branches spring no less powerfully represents the common origin and uniform development of its varied parts. That the evolutionist case for the common origin and production by descent of the forms of animal life is strengthened and supported by the facts of development is a statement which can admit of no question in the eyes of those who fairly face the facts, and who logically and without bias or prepossession construe their meaning. On any other supposition than that of the common origin and subsequent specialization of the varied forms of animal life, the fact that a sponge, a sea squirt, and a lancelet pass through essentially similar stages of development presents itself simply as an inexplicable mystery. Community of development betokens community of origin. Otherwise, the facts of nature must present themselves as absurdities, admitting of no logical construction whatever. Why a vertebrate animal in its earlier history should resemble a sponge or sea squirt is a query simply unanswerable, save on the hypothesis that vertebrate ancestry was at one period transmitted through forms of which the sponges and sea squirts are the existent, and it may be the altered, representatives. The development of an animal thus reasonably stands before us, in the newer interpretation of evolution, as a veritable panorama of its descent. Often, according to Darwin's already quoted remark, the series of pictures may here and there be obscured. The continuity of the shifting views may be interrupted by the extinction of stages through the influence of external conditions or of unknown causes. But in most cases, the outlines remain clearly and fairly drawn, and afford us a glimpse into the order of nature, not only more astonishing, but also more convincing in its teachings than the views obtained of the world of life from any other standpoint. There yet remain for consideration one or two important points suggested by the details of animal development, these latter points bearing as intimately, perhaps, on the argument for evolution as the grand facts of development themselves. First in order, it behoves us to note the interesting facts concerning the branchial arches and gill clefts of vertebrate animals, already noticed, and the conclusions to which the observation of these facts eventually leads. The branchial or gill clefts were remarked as being developed in the neck or throat of the chick about the third day of incubation. The part subsequently played by certain of these structures in the formation of the jaws was duly noted, the remaining clefts and folds disappearing in due course and leaving no trace of their existence behind. Shortly stated, the history of these gill openings shows us that they are of universal occurrence in the development of the vertebrate group of animals. They appear in the fish and in the bird. They are developed as persistently in man's early history as in the development of the frog or reptile. No more convincing proof of the community of development in this respect could be adduced than the comparison of the early embryos of different vertebrate animals. The gill arches are there seen to be as clearly the natural heritage of man as of the rabbit, calf, and pig, whilst they are as typically represented in the chick and fish. In the fish and in some newt-like animals, the visceral clefts and arches become permanent features of their adult life and are associated with the gills or breathing organs. But reptiles, birds, and quadrupeds are lung breathers and possess gills at no period of their life. Why then, it may be asked, should they invariably develop in their early life gill arches and gill clefts which bear no relation to the wants of their adult existence? The gill arches of reptiles, birds, and mammals never develop gills, and even the gills and gill clefts of tadpoles disappear when these animals become adult toads, frogs, and newts. Why, then, it may be repeated, does this seemingly irrationality and useless expenditure of creative power in nature exist? The true and only answer to such a pertinent query is that the gills and gill arches of higher vertebrates bear reference to a former condition of matters. They relate to anterior stages of vertebrate existence when the ancestors of lung-breathing animals were represented by gill-bearing and aquatic forms. Gill arches and gill slits thus appear as a true legacy and inheritance from an aquatic ancestry. In the higher vertebrata, the first gill opening becomes converted into structures and parts connected with the ear. The remaining clefts disappear, whilst the gill arches themselves contribute to form the tongue bone, hyoid bone, and the small bones or vesicles of the internal ear. Only on the theory of descent with modification can we rationally explain the presence of now useless structures such as the gill arches and gill clefts of lung-breathing vertebrates. On this principle, quote, "We may cease marveling," says Darwin, "at the embryo of an air-breathing mammal or bird having branchial slits and arteries running in loops, like those of a fish, which has to breathe the air dissolved in water by the aid of well-developed branchiae." Unquote. The method of disappearance of the gills and their arches is as reasonably detailed when Darwin states that, quote, "In order to understand the existence of rudimentary organs, we have only to suppose that a former progenitor possessed the parts in question in a perfect state, and that under changed habits of life they became greatly reduced, either from simple disuse or through the natural selection of those individuals which were least encumbered with a superfluous part, aided by the other means previously indicated." Another fact of interest derived from our studies in development relates to the position of the sea squirt larva and of the lancelet as together constituting links which bridge the gulf between the invertebrates and their higher backbone neighbors, the vertebrate animals. Only when we think of the apparently great gulf fixed between the fishes as the lowest vertebrates and all invertebrate forms can we realize the gain to evolution of the knowledge which shows how the development of the sea squirt and that of the lowest vertebrate run in parallel lines. Such a correspondence in development and the discovery of the possession by sea squirts of the notochord, long thought to be the exclusive possession of the vertebrates, constitute together a veritable tower of strength for the evolutionist, whence he may survey a formidable gap supplied, and a missing link satisfactorily brought to light. It should lastly be noted that the facts brought to light by a study of the early stages in the development of animals may be regarded as being thoroughly in favor of the theory of evolution. Professor Alan Thompson, in his presidential address to the British Association, 1877, stated the latter fact forcibly when he said, quote, "I consider it impossible, therefore, for anyone to be a faithful student of embryology in the present state of science without at the same time becoming an evolutionist." Unquote. These are weighty words, but they are fully justified by the circumstances of the case to which they apply. And no less apt are the terms in which the same authority in matters embryological further alludes to the support received by evolution from daily life histories of living beings. Quote, "If," says Professor Thompson, "we admit the progressive nature of the changes of development, their similarity in different groups, and their common characters in all animals, nay, even in some respects in both plants and animals, we can scarcely refuse to recognize the possibility of continuous derivation in the history of their origin." Unquote. End of section 25. Chapter 9. The Evidence from Development 1. The Earlier Stages in the Life History of Animals, Part 3. Section 26 of Chapters on Evolution by Andrew Wilson. This LibriVox recording is in the public domain. Chapter 10, The Evidence from Development, continued. 2. The Life Histories of Starfishes and Crustaceans. Part 1. Allusion has already been made in the preceding chapter to that most fundamental proposition of modern biology, which maintains that, quote, "community in development reveals community of descent." Unquote. It has also been shown at length that in the eyes of modern naturalists, the development of an animal or plant is regarded as affording a clue to the manner of its evolution or descent from pre-existing forms. The formation of a living being today, in other words, repeats for us the formation of its race and species in time past. So that, once again to quote Darwin's words, we can understand how it is that, in the eyes of most naturalists, the structure of the embryo is even more important for classification than that of the adult. Unquote. Or again, quote, "Embryology, or development, rises greatly in interest when we look at the embryo as a picture, more or less obscured, of the progenitor, either in its adult or larval state, of all the members of the same great class." Unquote. Second to none in interest in the eyes of modern biologists are the phenomena presented to them in the formation of the animal or the plant frame. In former years, the mystery of development was great indeed. There could be offered in the past decade of biology no reason, appealing sufficiently to the rational intellect as explanatory of the events in question, why a frog in its development should appear first as a gill-breathing fish, later on as a tailed newt-like creature, and ultimately as a tailless, lung-breathing amphibian. nor could natural historians in the past venture to account in more lucid fashion for the curious changes which a butterfly or beetle undergoes in its progress from the days of its youth towards the adult form, and from the stage of the crawling grub through that of the quiescent chrysalis to the full-fledged imago with its wings. Kirby and Spence summed up and dismissed such matters in a manner, unfortunately for the free play of intellectual vigor, not quite extinct in these latter days, which said much perhaps for faith, but little or nothing for reason and science. These famous entomologists held that insects pass through a metamorphosis because, quote, such is the will of the Creator, unquote, and they supplement this confession of faith with an attempt at a scientific explanation by the further assertion that insects, being voracious in their feeding habits, especially in earlier life, perform an important function in the economy of nature in that they remove from the earth's surface superabundant and decaying animal and vegetable matter. A further reason for this providential arrangement was given in the fact that, as, quote, unusual powers of multiplication, unquote, were indispensable for recruiting the ranks of the insect scavengers, and as nutrition and reproduction are incompatible functions, the removal of decaying matter during the youthful stages of the insect's life was to be regarded as a convenient subdivision of its labors, seeing that its adult existence is spent in the work of reproducing its race. But it might easily be shown that, whilst a goodly number of larval insects do feed upon carrion, a large proportion of the class does not exhibit any such habit, and it might reasonably enough be maintained that the argument of Kirby and Spence is open to the serious objection that, in its character, it tends to illustrate the post hoc ergo propter hoc fallacy. Decaying matter exists, therefore insects were designed to pass through a metamorphosis, and were gifted with veracity of disposition that they might remove the said matter from the earth's surface. A proposition vitiated in its exactitude by the fact just mentioned that many insects do not eat such matter, and also by the further facts that many do not undergo a metamorphosis at all, that many voracious caterpillars, instead of eating decaying matter, destroy our trees and flowers. It might also be added that many of nature's scavengers of higher and lower rank than the insects do not pass through a series of changes in development, but grow, nourish themselves in the exercise of their sanitary work, and likewise at the same time and as adult forms reproduce their species and continue their race in time. Clearly, then, the explanation of Kirby and Spence affords no satisfaction to the contemplative mind in the natural anxiety and desire to discover the causes of things. At its very best, such explanation leaves the reason why untouched, and conversely, it can well be understood how any other system of thought which presents a more satisfactory method of accounting for the facts in question should find ready acceptance as expanding and enlarging the thoughts of men. In the previous chapter, we discussed the meaning of the remarkable likenesses which can be readily proved as matters of fact and observation to exist between the early stages in the development of very different animals. A sponge, a sea squirt, a lancelet, and even higher animals still appear in the first beginnings of their existence to pursue a remarkably similar course. Each form parts, company with its fellows at a given stage on the way of development, and thereafter passes by the special pathway of its race towards the adult and perfect stage. Von Baer's axiom that development proceeds from the general to the special thus declares a great truth of nature. Modern biology appears provided with a host of witnesses to the truth of that axiom, and supplies a reason for the likeness by assuming similarity of descent from lower life as the explanation of those common and general beginnings from which the special and varied forms of animals and plants are evolved every hour around us. The axiom that the development of the individual, ontogenesis, is the rapid shifting or panoramic recapitulation of the development of the species, phylogenesis, is now regarded in biology as the keynote of the whole study of animal and plant formation. If we find, for instance, that the frog in its development is firstly a fish, then a tailed amphibian or newt, and last of all a tailless, air-breathing frog, we see in such a panoramic succession of changes, constituting the development of the individual, the evolution and development of the frog race. We read such a history as showing us clearly enough that the frogs have been evolved from some ancient fish stock, that this fish ancestor became, through succeeding modifications, a tailed, newt-like amphibian, and finally the newt in turn became the higher frog. Most reasonable is the supposition and belief that, if the living hosts have descended from common ancestors, the appearance of ancestral features in their development is a most natural expectation and a highly natural law of life. That transmission from parent to offspring of hereditary features, so familiar to us in human existence, the reproduction of family features in the successive descendants of the family stock, is, in truth, but the repetition in higher life of the likenesses to its ancient ancestry we see in the developing frog. On such grounds we may attempt successfully to explain the mysteries of development, and on such a principle we may note in passing it is easy to see how important a guide to the classification and arrangement of living beings their development affords. If those animals which are descended from a common ancestry resemble each other in their development, such resemblances may be held to represent the truest of those blood relationships which it is the business and aim of classification to express. The chronicle of the development of animal life is, however, not completed when the earliest changes seen in the formation of the animal frames have been noted. Long after the common and earliest stages, described in the last chapter, have been completed, there may be produced before us marvelous resemblances and likenesses between animals which, when adult, would seem to possess no community either of origin or of other relationship. It is to these later stages in the animal form that we now purpose to direct attention. The history of those changes which more immediately precede the assumption of adult life affords us valuable evidence of the evolution of species, as does the chronicle of the very beginnings of existence. It is only needful to point out at the commencement of such a study that, admittedly, the panoramic views of evolution we are about to discuss frequently present breaks and gaps in their succession. The expanding canvas of life here and there exhibits a blank surface, due to the part erasure of the picture which, we believe, formerly existed thereon. There exists a second principle in nature and evolution of equal importance to heredity, or that in virtue of which the likeness of the parent or ancestors is transmitted to the offspring or descendants. This second principle is that of modification by adaptation to surrounding or varying conditions. The living being is a plastic unit capable of being affected and impressed in various and often undetermined fashions by the forces of the world in which it lives. Such external conditions, heat and cold, food, habitat, and a host of other circumstances influence its development in the present, as unquestionably in the past they have modified the history of its race. In truth, the germ idea of evolution is that of progressive change and alteration induced by the great factors, internal or innate, hereditary and vital forces, and the external or outside circumstances of life. To the operation and influence, then, of surroundings acting variously upon different natures and organisms, we rightly ascribe the deletion of stages we would naturally expect to meet with in that recapitulation of the animal evolution exhibited in its development. As the geological record, through its imperfections, due to the metamorphism and destruction of fossil-bearing rocks, causes grievous gaps in the history of past life on the earth, so the history and development of the life of today shows its blanks and imperfections likewise, these blanks caused chiefly, we believe, by the varying outward conditions under which the development of the race was carried out. Thus, if the main outlines of the development of the frog race be plainly delineated, the pictures likewise may exhibit here but the dimmest possible contour, and may there show a blank. The original fish ancestor of the race must be sought for amid the fossils. Possibly it may never come to light at all. The successive stages whereby the tailed newt became the frog are barely outlined in the animal world of today, and are here and there wanting altogether. But the finger posts exist nevertheless, and they guide our mental way satisfactorily enough, so long as we trust to their indications. Even though we have to wade through the high tides of difficulty and dimness of knowledge which obscure the intervening ground, we may walk with confidence in that sober path which is founded upon the reason that is attainable. As Huxley pertinently remarks in a recent manual of zoological instruction, quote, "In practice, however, the reconstruction of the pedigree of a group from the developmental history of its existing members is fraught with difficulties. It is highly probable that the series of developmental stages of the individual organism never presents more than an abbreviated and condensed summary of ancestral conditions. While this summary is often strangely modified by variation and adaptation to conditions, and it must be confessed that, in most cases, we can do little better than guess what is genuine recapitulation of ancestral forms and what is the effect of comparatively late adaptation. The only perfectly safe foundation for the doctrine of evolution," continues Huxley, "lies in the historical, or rather archaeological evidence that particular organisms have arisen by the gradual modification of their predecessors, which is furnished by fossil remains. That evidence is daily increasing in amount and in weight, and it is to be hoped that the comparison of the actual pedigree of these organisms with the phenomena of their development may furnish some criterion by which the validity of phylogenetic conclusions, or race development, deduced from the facts of embryology alone, may be satisfactorily tested." Unquote. A survey of some typical groups of animals in relation to their development will provide us with satisfactory means of judging how far and how plainly the history of the individual repeats that of its race. Turning firstly to some fields of lower life, we may select the class Echinodermata, represented by the starfishes, sea urchins, sea lilies, or crinoids, and sea cucumbers, as a starting point for our inquiries. There is little need that a list of zoological characters should be enumerated by way of impressing the idea of the varied appearance of the animals just mentioned. But it may be remarked that, firstly, they all exhibit a fundamental likeness in structure, beneath diversity of form, and secondly, that such general or fundamental agreement is seen in the management of their internal organs, digestive system, heart, nervous system, etc., and especially in what zoologists term their radial symmetry, that is, their generally rounded form arising from their bodily elements, so to speak, being molded around a central point, the mouth. However like these animals may be in general structure, they at the same time present us with very diverse forms. On the hypothesis of special creation, nothing could appear more rational than the idea that dissimilarity of form was due to the separate circumstances of their creation. But such an idea overlooks at the same time their general likeness in structure, and it certainly takes no account and gives no explanation of the singular uniformity and resemblances presented by these animals in early life. The general likeness in question, in fact, simply reiterates and strengthens the evidence and conclusions that the varied tribes of starfishes, sea urchins, crinoids, and sea cucumbers have arisen from a common ancestry. Let the history of their development prove the truth and validity of this conclusion. Selecting a starfish as the most familiar form of the class, we find its early development to exhibit those stages of egg segmentation common to the developing ovum of all animals, and which have been already discussed. But the special features of starfish development soon begin to show themselves in the production of a worm-like organism utterly different from the starfish form, and which swims freely in the sea by means of the delicate cilia or vibratile processes with which the sides of its body are provided. This larva possesses a digestive system, a system of water tubes, and other structures, and it would thus seem as if from the egg of the starfish a wholly different progeny was destined to arise. So unlike is the young organism to the parent that, when first discovered, it was described by Sars in 1835 as a hitherto unknown form under the name of Bipinnaria. In due time, however, a secondary formation begins to appear within this latter body, and the curious spectacle is soon beheld of the form of the young starfish growing within and absorbing the materials of which the Bipinnaria body is composed, so that when development is completed, the Bipinnaria's substance has become appropriated by the new and secondary formation, which latter duly appears as the true starfish, destined after ordinary growth to assume the adult form. The study of a sea urchin's early life history reveals a striking similarity to the development of a starfish. The embryo sea urchin, in escaping from the egg, says Agassiz, quote, resembles a starfish embryo, and it would greatly puzzle anyone to perceive any difference between them. The formation of the stomach, of the esophagus or gullet, of the intestine, and of the water tubes takes place in exactly the same manner as in the starfish, the time only at which these different organs are differentiated not being the same. Unquote. But at a later stage, the young sea urchin develops a different phase and form from those of the starfish. It appears as a curious body, shaped somewhat after the fashion of a painter's easel, and formerly named Pluteus, under the idea that it represented an adult and distinct being. Within this Pluteus, a skeleton of limy rods is developed, and a digestive system is also formed. Then succeed the final stages in development. The body of the Pluteus is absorbed by the future sea urchin, which, as in the starfish, is formed within and from the substance of this larva, with this difference that a portion of the Pluteus is generally cast off as useless material, whereas in the starfish the whole larva was utilized in the manufacture of the perfect form. There exists a second group of starfishes, including the brittle stars and sand stars, and exhibiting certain differences in structure from the common starfishes of our sea beaches. In their development, these sand stars and their neighbors approach very nearly indeed to that of the sea urchins. Their larva is also a Pluteus, and possesses a limy skeleton, and it is singular to find that forms so divergent in character as the sand starfishes and sea urchins should thus resemble each other in development. The interesting group of the crinoids, or sea lilies, well known in a fossil state under the name of encrinites, presents us with beings that may best be described as starfishes born on stalks. There exists, however, a well-known free crinoid in the shape of the Comatula Antedon rosacea, or the rosy feather star of our coasts. This form appearing in its adult condition as a free, unattached starfish, but indubitably proving its crinoid nature in that it spends the early part of its existence in a stalked condition, resembling the permanent state of its neighbor sea lilies. Now, in the development of the crinoids, we meet with an oval, free-swimming larva, within which a digestive system duly appears. This organism in due course attaches itself by a stalk, and the future crinoid is developed within this larva. A new mouth and digestive apparatus are produced, and the adult stalked form is assumed. In the rosy feather star, such development, with its characteristic modifications, is well seen. Here we first see the oval larva with its 4 bands of cilia, and a tuft of these organs at the posterior extremity. Then traces of the future adult appear within this body. As development proceeds, the cup or body of the crinoid is formed, the tentacles or arms bud forth, and the young feather star, already stalked, appears in the likeness of a true crinoid. Here development might be thought to have well nigh attained its limit. So thought the discoverer of this little stalked form when it was announced that in the Cove of Cork a rara avis in the shape of a British stalked crinoid, duly named Pentacrinus europaeus, had been found. But years afterwards, the little Pentacrinus was seen to leave its stalk and to appear before the eyes of zoologists in the guise of an old familiar friend, the rosy feather star of the coasts. Thus we discover, firstly, that crinoids resemble their neighbors the sea urchins and starfishes in the essential details of their development. And we discover, secondly, in the case of the rosy feather star, a further development of the crinoid race, in that this latter organism has advanced to a free-living stage. Also noteworthy is the fact that when existing in its rooted and stalked stage, the rosy feather star closely resembles the ordinary fixed crinoids, and perhaps bears a still closer likeness to certain fossil members of the group. The last class of echinoderms demanding attention is that of the holothurians, or sea cucumbers, found around our own coasts, but developed typically as the trepangs and bêches de mer of tropic seas, and in marketable form as the delicacies of the Chinese. A sea cucumber presents us with an elongated body bearing a tuft of feathery tentacles at the mouth extremity, and moving by aid of tubular feet, similar to those of the starfishes and their neighbors. Here, development resembles that of the starfishes and begins with the production of an oval, ciliated body, which soon acquires a digestive system. The young sea cucumber, in the guise of what is called its auricularia stage, presents a cylindrical figure with 4 or 5 bands of cilia, and bears ear-like processes, hence its name. Before this larvae is fully formed, the future sea cucumber commences its existence as a growth existing near the larval stomach. The tentacles of the young Holothuria soon appear, the ear-like projections are absorbed, the auricularia assumes a cylindrical form, and becoming the pupa, bears a striking resemblance to a worm. When the process of absorption proceeds to a further stage, the auricularia wholly disappears, and as the new body which has been developed at its expense elongates, the young sea cucumber form is duly evolved. End of section 26. Chapter 10, The Evidence from Development Continued. 2, The Life-Histories of Starfishes and Crustaceans, Part 1. Section 27 of Chapters on Evolution by Andrew Wilson. This LibriVox recording is in the public domain. Chapter 10, The Evidence from Development Continued. 2, The Life Histories of Starfishes and Crustaceans, Part 2. Such is the course of development in the sea urchins and their allies. The chronicle in question is well adapted to supplement the important considerations advanced at the commencement of this chapter. There is strikingly seen in the development of these animals, firstly, that broad resemblance in their earliest stages which augurs for a common derivation, and which proves what their adult structure teaches, that these organisms are simply so many modifications of a common plan. In each and all, the first larva gives origin to a second within itself, this second growth becoming the true and adult form, so that the first larva produces the new being, as it were, by deputy. And whilst general similarity in development thus may be taken to mean community of origin, if it has any meaning at all, there remains illustrated to us the second principle involved in the study of development at large. The differences between the early forms of these various groups are readily enough explicable on the theory that adaptation and variation, acting through undetermined laws of life, or through the influence of outward conditions, or through both of these phases, have been at work, evolving from the common larval type the differences of form perceptible in their present-day development as well as in their adult structure. This principle of adaptation is perhaps best illustrated by those cases of direct development seen in some species of holothurians and starfishes, etc., in which the young appear in the likeness of the parental form without undergoing a metamorphosis or series of changes. In such a case, the obliteration of these changes has probably depended upon causes which at present we are unable to trace, the directly developed forms probably representing the later products of evolution. But it is needless to remark that on the clear evidence afforded by the typical development of these animals generally, the theory of their common origin is in no wise affected by the elimination, here and there, of the ancestral features of the race. Perhaps the sea cucumbers and starfishes represent the most typical and least altered cycles of development, whilst the sea lilies and sea urchins present us with the results of a more modified series of changes. But theoretically, there is little difficulty in assuming that, could we look backwards in time with definite glance, we should expect to see the origin of our sea stars and their allies in a stock which, if anything, approaches most nearly to the form of some primitive worm than to that of any other animal form. Such a primitive form is perhaps best outlined in the larva of the sea cucumber itself. Indeed, the evolution of the echinoderms from some such worm stock is one of the well-founded generalizations of modern zoology. There exist, it may be added, in the developmental history of the worms themselves, certain features which go far to support the idea of a far-back relationship with the sea urchins and their neighbors, these latter forms being apparently removed very far from the worm stock as they present themselves to our view in the forms of adult and perfect existence. there is a curious marine worm named Balanoglossus, the larva of which, known as Tornaria, certainly approaches of all other known forms most nearly to the youthful starfishes, sea cucumbers, and their neighbors. Indeed, the young Balanoglossus has been described as intermediate between the young of echinoderms and the larval forms of mollusks to be hereafter described. Balanoglossus itself is peculiar in possessing gill slits resembling those seen in the early life of all vertebrates. There seems little reason to doubt that this curious animal is a survival of a once widely represented type, which today exhibits decline and decay, whilst preserving for us the important characters of a common ancestor of several existing groups of animals. Ranking above the sea stars in respect of generally higher organization, we find a very numerous and varied assortment of animals known as the Crustacea. The etymology of this latter term might suffice to convey information respecting the typical representatives of the group, inasmuch as the presence of a hard crust or shell characterizes the higher forms, as well as many lower members of this class. Such higher forms are the crabs, lobsters, shrimps, prawns, water fleas, and their neighbors, which possess a shell, although, as even a tyro in zoology knows, the shell of the crab is a widely different structure in nature as it is in appearance from the shell of the oyster or whelk. The crab shell is periodically slipped off its body to admit of the animal's increase in size, whilst that of the mollusk, oyster, mussel, whelk, etc., is a permanent structure, attached by muscles and other organic means to the animal's body, growing steadily as bones grow in our cells, and forming therefore a much more important item of bodily belongings than does the crustacean's covering. But apart from the nature of the shell, the crustaceans, as one may see in the jointed tail of the lobster or shrimp, are very differently planned, so to speak, from the mollusks. They are articulate or jointed animals, and naturally claim insects, centipedes, scorpions, spiders, et hoc genus omne as their relatives and friends. Now this great crustacean class includes a very motley and varied series of beings. At its head, as we have seen, are the lobsters, crabs, shrimps, and prawns. Its middle classes are represented by the water fleas, whose name is legion, and its lower orders are the barnacles, the sea acorns, the sacculinas, and a host of allied creatures which certainly present us with the best examples of degradation in the animal kingdom, in that they exist for the most part as footless, often as mouthless, and frequently as shapeless organisms, attaching themselves to fishes and to other crustaceans, and living the low existence pertaining to the parasite, whether of higher or lower grade. There seems no wider dissimilarity, for instance, between any two animals than between the shrimp or prawn and the bag-like sacculina, which attaches itself to the bodies of crabs. There is apparently a wide distinction between the structure of a crab and a water flea, and still more between a barnacle and a prawn. Yet, in the classifications of zoology, these diverse beings are ranked as members of the same class, and development, as the great criterion of classification, sanctions the arrangement. Let us endeavor to discover the grounds which warrant the assertion of such near relationship. No fitter starting point can be found than the development of the barnacle, which, attached to floating wood by its fleshy peduncle or stalk, enclosed within its shelly habitation, and sweeping the waves with its set of feathery plumes or cirri, lives a life bordering nearly on the state of parasitism itself. From the egg of the barnacle, and after the preliminary stages of development which are common in greater or less degree to the personal evolution of all animals, comes forth a little creature, so utterly unlike its parent that one might well feel disposed to reject the claims of the aphorism like begets like, so universally expressive of the relation betwixt parent and progeny. The body of the young barnacle is triangular in shape. Its anterior angles are protruded into horn-like processes, and it possesses a mouth and digestive system, a single median eye spot, a forked tail, and 3 pairs of feet or limbs. In this stage it is known as a nauplius, and it may be well to keep the characters of this little organism in mind, since we shall find them to reappear in the progeny of animals of diverse nature from our barnacle. The course of nauplius life lies in the direction of frequent molts, and by it assumes, after a special change of skin, the form of the pupa barnacle. It passes, in other words, from the days of its infancy to the days of its youth. As the pupa, its body is enclosed in a bivalve shell or carapace. 2 compound eyes replace the single organ of vision of the nauplius stage. The first pair of legs have become enlarged and appear as antennae or feelers, provided each with a sucker, whilst behind the mouth 6 pairs of cirri or small hair-like limbs are developed. The mouth appears to become abortive in this stage, in which the resemblance of the young barnacle to a water flea, such as Daphnia or Cypris, is sufficiently striking. Darwin remarks that in the nauplius stage, the young barnacles feed actively and increase in size, whilst in the second stage, their function is, quote, to search out their well-developed organs of sense and to reach by their active powers of swimming a proper place on which to become attached and to undergo their final metamorphosis, unquote. The concluding phases in barnacle history are not difficult to trace. The body of the young barnacle becomes somewhat flattened and compressed, and, as Darwin remarks, resembles in its shape a mussel shell or the water flea known as Cypris. The carapace or shell appears paramount in the final stages of development, the limbs and body being hidden and enclosed by the shell. And although jaws exist, these organs are covered by integument, and the organism is thus deprived of the power of nourishing itself. Certain remarkable glands now begin to be developed in the pupa barnacle. These organs open by the so-called cement ducts in the suckers of the well-developed first pair of appendages, the great feelers or antennae already mentioned. The pupa in due time seeks a location and resting place, and adheres to its floating log or to the side of the ship by means of its feelers. Thereupon the cement glands pour out their secretion, which acts as a veritable marine glue, defying the solvent action of the water and fastening the barnacle head downwards to the place of attachment. Then the compound eyes disappear, leaving the future existence of the barnacle sightless. The characteristic limy formations or plates seen in the shell of the adult barnacle are developed. The 6 pairs of swimming feet become the plumes, cirri, or glass hand of the barnacle, and by their incessant waving draw food particles into the mouth. With the production of the characteristic fleshy stalk or peduncle of the full-grown form, which grows from the front part of the body, this curious history comes to an end. Barnacle growth therefore exhibits as its stages, firstly, a free-swimming larva or nauplius, with its 3 pairs of legs or appendages, then a pupa with its bivalve shell, its large feelers, its 2 eyes, and its 6 pairs of swimming feet, and finally the eyeless, stalked, and degraded adult stage, in which, to quote the words of authority, a barnacle appears as a crustacean, quote, fixed by its head and kicking the food into its mouth with its legs, unquote. From the crustacean array, we may next select an animal which, whilst it resembles the barnacle in many of its features, and especially in development, is yet sufficiently distinct to lead towards forms presenting greater differences in the adult stage and yet exhibiting close identity in the early phases of existence. Such a form is the Sacculina, a type of crustaceans of the very lowest grade, which live in attached, rooted, and parasitic existence on fishes or on other crustaceans. If a barnacle exhibits retrograde development or physiological backsliding, in that it appears to be a lower and more modified form when adult than when in the pupa stage, the Sacculina and its neighbors exhibit a still more degraded condition. The organism just named exists as a sausage-like bag attached to the bodies of hermit crabs. There exist no traces of a mouth, or as Fritz Müller remarks, quote, they lose all their limbs completely and appear as sausage-like, sac-shaped, or discoidal excrescences of their host, filled with ova, or eggs. From the point of attachment, closed tubes, ramified like roots, sink into the interior of the host, twisting round its intestine, or becoming diffused along the sac-like tubes of its liver. The only manifestations of life which persist in these non plus ultras in the series of retrogressively metamorphosed Crustacea are powerful contractions of the roots and an alternate expansion and contraction of the body, in consequence of which water flows into the brood cavity and is again expelled through a wide orifice." Unquote. Now, the history of the Sacculina development clearly proves its relationship with other crustaceans. As an adult, a Sacculina might literally be anything in the way of animal organization. It is a bag filled with eggs and attached by roots to a hermit crab. As such, its true nature is not recognizable by any of the deductions to be drawn from the ordinary facts of animal structure. Development, however, not only shows us its descent, but settles its place in the animal scale by declaring its affinities, not only with the barnacles, but with other crustaceans. From each egg contained within the bag-like body, there is developed a little free-swimming creature. This embryo possesses an oval body ending in two short processes. 3 pairs of swimming feet are developed, a single eye may or may not be present, but we find in the young Sacculina a clear and unmistakable reproduction of the nauplius of a barnacle. No mouth or digestive system, however, exists in the youthful Sacculina, which shortly changes into the pupa state. Here it closely resembles the Cypris water flea, whose development we shall also presently note. It possesses a shell folded down at the edges so as to enclose the body. The front pair of limbs, as in the barnacle, become modified to form organs of attachment. The 2 remaining pairs of feet are cast off, and as in the barnacle, 6 pairs of forked swimming feet appear on the body behind, while the forked tail is also a characteristic feature of the young Sacculina. Then succeeds the stage of attachment. The front feet or feelers serve as means of fixation to the body of the crab host. The remaining 6 pairs of feet are cast off. The roots are developed from the feelers, and the animal thus assumes the adult, sac-like, and degraded form. Thus, a Sacculina and its parasitic neighbors closely resemble barnacles up to the pupa stage. At this point, the evolution, manifested in degradation of the Sacculina, intervenes, and the 6 pairs of feet, which in the barnacles are converted into the cirri or plumes, are cast aside as useless. The process of extreme modification for a life of parasitism effectually molds the remaining features of the organism in the characteristic ways of Sacculina life, namely as the sausage-like sac fixed to its crab host. But there can be no question that barnacle growth and Sacculina development run in strictly parallel grooves. Allusion has been made to the likeness exhibited by the pupae of the barnacle and Sacculina to the perfect and adult form of those water fleas which, like Cypris and Daphnia, are familiar tenants of our fresh waters. The development of the water fleas, under which general name very diverse beings are included, is highly instructive in that it leads us to note how the community of development existing among Crustacea extends its roots so as to include every group or order of that class within its limits. The Cypris and its neighbors are known by their possession of a distinct bivalve shell, that is to say, a shell consisting of 2 pieces, united along the back by a membrane serving as a hinge. 2 or 3 pairs of feet exist, but these creatures appear to swim chiefly by aid of the tail. Now the young Cypris leaves the egg as a nauplius with 3 pairs of limbs. It possesses, like the barnacle nauplius, a single eye, and it appears to develop a shell likewise. The adult condition is attained in due course with the production of the bivalve shell, and the 3 pairs of limbs of the nauplius are converted respectively into the greater and lesser pair of antennae and into the mandibles or jaws of the adult. The other feet of the full-grown Cypris are also developed in its later stages of growth, which are manifested by frequent moltings of the skin. A young Cypris therefore resembles a young barnacle in its nauplius form, and in the transformation of its anterior limbs into antennae or feelers, which in the water fleas serve the purpose indicated by the latter name, or may even be used for swimming, as in the Daphnia or branched-horned water flea. In the correspondence between the bivalve Cypris and the pupa barnacle or pupa Sacculina, we may possibly discover likewise the ultimate point of divergence between these diverse groups of crustaceans. Other water fleas, such as Daphnia and Cyclops, present variations in their early history from the chronicle of Cypris development. The Cyprides are perhaps the least modified of the water flea race, this conclusion being supported by the greater complexity of other water fleas as well as by the course of development of the latter. The anatomical investigation of a cyclops presents us with an oval body or carapace, bearing a single eye with two pairs of feelers, big and little, with a jointed tail forked at its tip, and with 5 pairs of swimming feet. In cyclops development, a singular resemblance is presented to that of certain low crustaceans parasitic on fishes, and it will be instructive therefore to compare these early stages in both groups. The first stage in cyclops history repeats the now familiar Nauplius with its oval body, its central eye, and its 3 pairs of legs. Next are developed the chest and tail regions, and 6 feet appear as the belongings of the latter. Then appears another pair of limbs, and the 3 limbs of the Nauplius become the greater and lesser pairs of feelers, and the great jaws as in Cypris. After a series of molts, the outlines of the cyclops body begin to be apparent, but it is worthy of remark that beyond the stage in which the tail region with its 6 feet is developed, those lower and parasitic crustaceans, the fish lice just referred to, do not pass. The further history of cyclops is simply a record of molts and the growth of new joints and appendages. That of the fish lice is a history of retrogression. The fish lice are represented by such forms as Lerniosura or Chondrocanthus, which latter in its maturity may be found sometimes by the dozen in the gill chamber of that ungainly fish, the angler or fishing frog, Lophius piscatorius. Lerniosura presents us as an adult with a shapeless, flattened body, about ½ an inch long, possessing the merest rudiments of limbs. Each fish louse begins life as a Nauplius, essentially resembling that of the cyclops water flea. It develops to resemble still more thoroughly the after stages of cyclops, but retrogresses therefrom and becomes modified for a parasitic life. Still more marked is this modification in other fish lice, Actheris and Lernii, which resemble cyclops as closely as does Lerniosura, but which sooner or later become worm-like or otherwise degraded. The suppositions entertained by competent authorities, firstly, that the fish lice and water fleas of the cyclops type have sprung from the same stock, and secondly, that the fish lice are simply cyclopean beings degraded by the adoption of parasitic habits, are therefore fully warranted by a consideration of the plain facts presented to us in their development. Or once again, to state a cardinal proposition of evolution, the passing development of individuals repeats and reproduces, with modifications, the fixed and past development of the race and class. End of section 27. Chapter 10, The Evidence from Development, continued. 2. The Life-Histories of Starfishes and Crustaceans, Part 2. Section 28 of Chapters on Evolution by Andrew Wilson. This LibriVox recording is in the public domain. Chapter 10, The Evidence from Development, continued. 2. The Life-Histories of Starfishes and Crustaceans, Part 3. To trace in full the record of crustacean development would considerably exceed the limits which the patience of the reader might bear, and would unnecessarily protract and repeat facts already exhibited and illustrated by the life histories just recorded. It might be highly profitable, for instance, to trace the development of those peculiar crustaceans, the king crabs, or limuli, which as living forms stand well nigh alone in their class, and remain connected with other crustaceans only as the leaves on the extremities of one branch of a tree may be said to be connected with those at the tip of another and widely divergent bough. These crabs at one stage of their development and before leaving the egg, within which all their notable features are acquired, present a most remarkable resemblance to certain of those singular fossil crabs, the trilobites, Prestwichia, and likewise at another stage to the larvae of certain other trilobites, Trinucleus. This resemblance is well seen on comparing the larva of the king crab with the larval trilobite, and still more striking is the resemblance between the king crab at a later stage with the adult trilobites. Thus, whilst the trilobite race and their neighbors, Eurypterida of Silurian age have died out of existence, the king crabs, springing presumably from the same rootstock, have undergone modification as descent proceeded along the files of time and remain to present a crab race of an age and type compared with which our existing crabs are but as creatures of yesterday. So also we might, did space permit, strive to show that those curious creatures, the brine shrimps, Artemia, of the Limington salt pans and the Great Salt Lake, the fairy shrimps which like crustacean ghosts flit through our fresh waters, or the curious apis with its 60 pairs of feet, begin life each as a nauplius, bearing either 2 or the statutory 3 pairs of limbs. And the account of other crustaceans in which, as in the woodlice tribe, the nauplius stage is passed either within the egg or is altogether suppressed, might similarly bring again before our mental view the operation of the laws and principle of modification. It may, however, suffice if in drawing crustacean history to a close, we select a few examples of development from the highest and most specialized group of the class, that of the crabs, shrimps, prawns, etc. In such a history, we may discover the important fact that, notwithstanding modification, and despite the high specialization of these latter animals from the primitive types and rootstock of Crustacea, their community of descent with that of all other members of the class is proved by those clues and traces which, all insignificant as they may appear to the ordinary observer, literally afford to the zoologist proofs and confirmations of the strongest character of the truth of the theory of descent. The higher crustaceans, or decapoda as they are called, including the crabs, lobsters, shrimps, prawns, etc., as their typical representatives, present us with a sufficiently diverse group of beings viewed as adults, and likewise afford illustration of equal diversity in their development. Such diversities may be well observed in the comparative study of the early history of such a series of forms as is presented by the lobsters and crayfish, by certain shrimps, and by the common crabs. In its development, the crayfish apparently presents but little that is remarkable, as compared with crustaceans of lower nature. Both crayfish and lobster come from the egg, in the essential guise of their species or race, and the free-swimming nauplius stage, so universal amongst lower crustaceans, is apparently unknown in their life histories. There is clear evidence at the same time to show that a nauplius condition is represented in their egg development, and that this phase is obscured and modified, presumably through those causes and conditions which have placed the lobster and crayfish amongst the aristocracy of the crustacean class. Speaking of the development of the crayfish and of its nauplius stage, Huxley says that animal, quote, is wholly incapable of an independent existence at this stage, and continues its embryonic life within the egg case. But it is a remarkable circumstance that the cells of the epiblast, or outer layer of the developing body, secrete a delicate cuticula which is subsequently shed. It is as if the animal symbolized a nauplius condition by the development of the cuticle, as the fetal whalebone whale symbolizes a toothed condition by developing teeth which are subsequently lost and never perform any function, unquote. Again, speaking of the crayfish, Huxley says, quote, in this crustacean, in fact, it would appear that the process of development has undergone its maximum of abbreviation, unquote. As already remarked, the progressive advance and evolution of a group must naturally include in their course changes and modifications in development as part and parcel of the higher order and structure to which the advancing members of the group attain. It is not surprising, therefore, to find that the crayfish or lobster should evince an absence in their development of those phases and repetitions of their ancestry of which their lower and more primitive neighbors, the barnacles, etc., present such typical examples. Whilst at the same time it is equally notable and interesting to discover that in nature's process oft-repeated exceptions prove the rule, and that here and there the exceptions to the ordinary development of higher crustaceans certainly prove that their original way of evolution has lain through the pathways so plainly marked out in the lower ranks of the class. Such exceptions occur within the family circle of the crayfish and lobster kind, and are even represented in the early history of that most familiar of crustaceans, the common crab itself. This animal possesses a life history which, whilst it presents striking analogies to that of lower crustaceans, likewise offers some interesting points of difference from the development of the latter animals. Within the egg, as in the case of the crayfish, the youthful crab appears to pass its nauplius stage, and sooner or later it emerges upon the world of waters in a form with which our previous researches have not made us familiar. The young crab possesses a short body which at first sight appears like a huge head and a jointed tail. In front and above are spinous projections, the upper of which reminds one of the end of a nightcap long drawn out. A single and simple eye is placed between two very large compound organs of sight. 4 antennae or feelers exist, and 3 pairs of jaws are developed, the young crab thus presenting us with the complete furnishings of the head of the adult. There likewise exist traces of appendages which represent foot jaws in the full-grown crab, but the jointed tail possesses no addenda or belongings save bristle-like processes attached to its broad and divided extremity. In 1778 there was figured by a Dutch naturalist a new form of crustacean which was met with in 1822 in large numbers in the Cove of Cork by Mr. Vaughan Thomson. These beings were referred to a genus Zoea, which had been constructed for their reception. Later research, however, showed that the Zoeas were merely the young or larval crabs just described, and the further development of the Zoeas was in due course satisfactorily traced. For after repeated molts, the Zoea becomes the Megalopa. Its body has now assumed a shape distinctly resembling that of the mature crab, and its 5 pairs of walking legs are well developed. It possesses, however, an appendage unknown in the adult crab, in the shape of a jointed tail provided with appendages. And as the Megalopa, the crab bears a very decided resemblance to one of its tailed neighbors, such as the hermit crab, lobster, or shrimp. Ultimately, the body widens after further moltings. The tail decreases in size, loses its appendages, and becomes tucked up under the body to form the characteristic little purse of the adult crab. And finally, with the proportional growth and development of other regions and parts, the features of adult crab life are duly produced. Thus, a crab's body really consists of a greatly broadened head and chest, and the jointed tail we see in the lobster or shrimp is represented in mature crab existence by the little appendage or purse which on examination will be found to bear rudiments of the tail appendages so typically developed in the long-tailed neighbors of the crab. It likewise becomes clear from the foregoing life history that the crabs, in respect of the modification and disappearance of their tail, are a later and higher race than the lobsters, shrimps, and prawns. And geology confirms this surmise inasmuch as the lobster races were developed ages before the crabs. Fossil kith and kin of the lobsters occur very early in the stratified rocks, the crabs being late productions, so that the idea of the crabs having originated from a tailed, zoea-like or lobster-like race is fully supported by the best of evidence. The concluding life histories which may be glanced at by way of summarizing the ways of the crustacean evolution are those of the mysis, or opossum shrimps, and a peculiar genus of prawns known as Peneus. The first mentioned animals are common in the lakes of modern Europe and of North America, and also flourish in the Arctic seas. It is a warrantable inference that the Mysis relicta of the lakes is simply a variety of the Mysis oculata of the Arctic seas, which has been shut off from a former marine existence by the conversion of the Baltic fjords or firths into lakes. Geological changes thus inducing alteration in animal species, and a primitively marine animal thus becoming completely adapted to freshwater life. These opossum shrimps are so called because the young are carried during development in special sacs or pouches of the parent form. They present in their early history a very interesting connection between the marked change of form in lower crustaceans and that direct development of the higher forms of which the crayfish is so well marked an example. Within the egg, Mysis, like the crab, passes through a nauplius stage. Thereafter, however, it grows rapidly, and a remarkable circumstance has to be chronicled, namely, that the original skin or integument remains unaltered and is not molted, or otherwise made to participate in the succeeding growth of the body. In this feature, as Huxley remarks, the young opossum shrimp might be justly compared to the pupa or chrysalis of an insect, since it lies, like the latter, within an enveloping skin from which, in due course, the young shrimp emerges. Here, then, the nauplius stage is represented as a fleeting period in development, and we see in the mysis, when full grown, a being which has no gills, which possesses a large tail or abdomen and a small body or head and chest, and which has but rudimentary appendages to its tail. Notwithstanding the fact that the development of the mysis is well nigh direct, we must not neglect to note the important facts, firstly, that one of its nearest relations, Euphausia, actually leaves the egg as a true nauplius, and secondly, that the form and figure of the adult mysis itself is perfectly reproduced in the development of the crustaceans of higher type. Thus, in the lobster, which so nearly resembles the crayfish in its direct development, and in its imperfectly represented nauplius stage, the young form, named the zoea, from its analogies to the youthful stage of the crabs, passes through a mysis stage, but thereafter develops into the mature lobster, with well-developed tail appendages and head. The idea that in the adult mysis we may see represented a transitory phase in the evolution of such higher forms as the lobster and crayfish is a justifiable assumption. It is one, moreover, which appears to be fully proved by the study of the life history of that division of the prawn tribe which includes the species of Peneus as its representatives. The prawns, as everyone knows, are intimately associated with the lobsters, shrimps, and crayfish as higher crustacea. Yet the first appearance of Peneus is not, as in the crayfish, as a well-nigh perfectly formed animal, nor, as in the lobster, as a zoea, somewhat like the adult, nor yet, as in the crab, as a zoea, widely different from the mature form. On the contrary, the youngest stage of Peneus is a veritable nauplius, with 3 pairs of appendages and a single median eye, accurately reproducing the features now familiar to us in the barnacle, saculina, and lower crustacean life at large. Next in order, this nauplius develops a rounded body shield or carapace, the first and second pairs of appendages becoming the 2 pairs of feelers proper to all crustaceans, whilst the third pair becomes the chief jaws or mandibles. Then are developed 4 pairs of feet, converted in due time into jaws and foot jaws, and behind these appear other 5 pairs of appendages, which become the 10 walking feet. The 6 joints of the tail have as yet no appendages, but the tail itself ends in 2 tufted processes, and we see the zoea form thus limbed out, whilst no less remarkable is the resemblance of the young prawn at this stage to an adult cyclops water flea. 2 stalked eyes, in addition to the single eye of the nauplius, appear in the zoea form, which alters and changes through the decrease of the feelers, till now used for swimming. The tail now increases in size and replaces the feelers in function, and the feelers, each at first double, become single-jointed organs. The 5 feet of the chest region are each provided with 2 terminal joints, and the zoea becomes thus modeled into the exact form of a mysis or opossum shrimp. Finally, the single and median eye disappears. The outermost of the 2 end joints of each of the chest limbs disappears, leaving these walking legs, seen so plainly in shrimp, prawn, crab, and lobster, of single conformation. Gills are developed within the chest, sense organs appear, and the full development of the prawn is then completed. Throughout these varied stages, it is not difficult to trace a panoramic succession of forms accurately reproducing the existing degrees and forms of the crustacean class. The early nauplius, the zoea or water flea stage, the mysis form, each produced in definite and advancing succession, present us with a perfect picture of the evolution of the prawn race from lower crustacean life, and presumably also of the evolution of all other crustaceans belonging to the same rank and series in the class. In summarizing the results to which a study of the development of the echinoderms and crustaceans leads, there is to be recognized the operation of the principles already more than once insisted upon in the preceding pages, namely, that community of descent is provable by likeness in development, just as differences or obliterations and alterations in development are explicable on the grounds of adaptation and change, acting concurrently with the evolution and progress of the race. Only by taking into account these two principles can the hard ways of development be understood. The present subject is one which may be regarded as lying thoroughly without the province and power of any explanation not founded upon evolution and upon the idea that progressive change is part and parcel of the order of nature. Admitting that the only feasible explanation of these curious phases of development is to be found in such an idea of nature's constitution, it seems folly to deny that the general weight of evidence in favor of descent more than counterbalances any difficulties which may present themselves in connection with the exact determination of the lines along which that descent has traveled. That larval or young forms are themselves liable to modification from various circumstances must be admitted. This variation, to be hereafter studied in the insect class of the young form which we regard as representing the primitive stock of the class, must unquestionably complicate the study of evolution and add to the difficulties of constructing a perfect pedigree of the living world. The Pluteus larva of a sea urchin and the Bipinnaria larva of a starfish thus differ in respect that the former possesses a limy framework which is wanting in the latter. But such distinctions do not in the least degree militate against the primary fact underlying all such developments, namely, that the likenesses, not merely of young forms but in adult structure, are explicable only on the theory of a common origin. Indeed, with the best of reason and logic, it may be argued that, as a condition of evolution, we postulate the occurrence of variations in the young stages as well as in the adult form, just as we should legitimately expect to find in living horses the rudiments of those toes which the ancestors of the existing equine race possessed. Thus, direct development, such as we have seen to occur in some starfishes and sea cucumbers, whereby the young pass directly into the form of the adult, and wherein the changes of structure and appearance are suppressed, is a result of the adaptation of the larvae to new ways of life. Rejecting this view, we should have to fall back upon the anomalous position of maintaining that there existed for one echinoderm a law of special creation, and for another a law of descent, a supposition which no logical mind will accept, and which the grander idea of the uniformity of nature at once dispels. As a final remark in connection with the sea urchin class and its transformations, we may add that the changes in form are themselves progressive in nature. The 5 existing groups of this class, sea urchins, starfishes, sand stars, sea lilies, and sea cucumbers, are unquestionably modifications of a common plan of structure, and they originate from a larva which is wonderfully similar throughout, if we consider the diversities of adult structure which arise therefrom. Further, if this larva were to be arrested in its development and to represent a mature form in such an arrested state, it would present a striking resemblance to some of the lower worms and their allies. This fact alone pointing to the probable beginnings of the sea urchin class in a worm stock. No less clearly do we see in the varying degrees of organization exhibited by adult echinoderms the same proof of progressive advance and modification of an originally primitive type. The forces and powers which, before our waking eyes today, evolve a sea urchin from its egg and easel-like larva, or a starfish from its bipinnaria, are, if we will only consider the wonderful nature of the transformations involved, engaged in as evident and intricate a work of evolution as those which have developed the varied twigs and branches of the echinoderm tree in the eons of the past. The foregoing conclusions find, perhaps, plainer illustration in the history of the crustacean class, wherein exists a uniformity not so clearly traceable, although its original existence may not be doubted, in the early life of the echinoderms. The highest members of the crustacea are, as we have noted, the lobsters, crayfishes, shrimps, crabs, and their allies. We have seen that in the crayfish, a nauplius stage is represented, that in the lobster a zoea phase is seen, that mysis likewise exhibits a nauplius, and then settles down as a peculiar form, that in the crab's early history a still better marked zoea appears, and finally that the shrimp Peneus actually passes through a nauplius phase, a zoea or water flea stage, a mysis form, and finally assumes the likeness of the shrimp tribe. The history of Peneus, therefore, is practically an abridged treatise of the evolution of all higher crustacea. Its development, to parody Pope's line, is, quote, not one but all crustaceans, epitome, unquote. And as perfectly are the facts of lower crustacean life correlated with those of the higher development of the class. A water flea, like Cyclops as an adult, matures its development and ceases to progress at a stage corresponding to that at which Peneus has but attained its youth. The barnacles and sacculinas exhibit the influence of conditions of parasitism acting at a definite stage in the course of ordinary development and producing the degraded and attached form of the adults. Mysis advances so far on the way towards the lobster and crayfish type, but stops short in its development at a point represented in lobster history, and beyond which the lobster itself passes, as we have seen. Finally, beyond all such stages, and underlying all the variations and obscurities, even of the higher and most modified life histories, we see the nauplius form continually appearing as the starting point of all crustacean history, or as that point, to use Fritz Müller's expression, which represents the, quote, extreme outpost of the class, retiring furthest into the gray mist of primitive time, unquote. The nauplius appears before us, then, as the founder of the crustacean race. The zoea is a modification and advance upon the nauplius, and from the zoea, as proved by Peneus development, were evolved the higher crustaceans at large. The lobsters and their allies, again appealing to Peneus, were evolved from the zoea form through an intermediate stage represented today by the mysis or opossum shrimp, whilst the short-tailed crabs in all probability arose directly from the zoea without the intervention of a mysis stage, seeing that in their development they exhibit a distinct zoea stage and do not pass through a mysis stage like the lobsters and their long-tailed neighbors. Diagrammatically expressed, we may see in the history of crustaceans that tree-like arrangement of their pedigree which best illustrates the deductions of evolution. The nauplius exists at the root of the class. Developed in direct line, we find Peneus passing through the zoea and mysis stages. The lobster branch diverges after the mysis stage has been attained, and the crabs depart from the main stem before the latter phase. The crayfish, with its obliterated nauplius stage, may be presumed to have followed the course of development resembling that of the lobster, its history, however, being singular in respect of the obliteration of the intermediate stages. The king crabs have presumably originated in the common nauplius form and have passed through the trilobite form, now extinct, to their present position at the extremity of an isolated branch of the crustacean tree, although indeed some naturalists hold that the king crabs are more nearly allied to the spiders and scorpions than to the crustaceans. The barnacles, fish lice, and water fleas, obviously nearly allied, spring from a distinct nauplius stem, but diverge through different ways and paths of life, the former to exist mostly as degraded parasites, and the latter to develop into active, free-swimming forms. Thus becomes clear to us the meaning of those singular changes in animal forms which puzzled the older naturalists. To question the meaning which evolution attaches to these changes is to leave them without explanation or meaning. Our knowledge of the full evolution of the Crustacea or any other animal group, as already remarked, may be, and often is, far from perfect. We are, it is true, still in the gray mists of many biological subjects, and the pedigree of animals, amongst others, is still enveloped in much obscurity. But at the same time, we can detect breaking through the mist gleams of knowledge, bright forerunners of that flood of light which the research of after years will assuredly bring. End of section 28. Chapter 10, The Evidence from Development, continued. 2, The Life-Histories of Starfishes and Crustaceans, Part 3. Section 29 of Chapters on Evolution by Andrew Wilson. This LibriVox recording is in the public domain. Chapter 11, The Evidence from Development, concluded. 3. The Development of Molluscs, Amphibians, etc., Part 1. The attempt has been made in previous chapters to show that in the development of living beings, there lies an enormous store and fund of evidence which goes either directly to support evolution as a rational theory of the universe, or which, at any rate, aids us in comprehending the causes which have, directly or indirectly, made the world of life the wondrous thing it is. The result of our inquiries has been to show that in the first beginnings of an animal's development, and in its earliest phases of progress, there is an amazing likeness to the early stages of every other animal's progress towards maturity. But even after these early similarities have appeared, there may be demonstrated in many groups a later likeness, which may often be traced beneath forms of the most diverse kind. The progress of the living being is unquestionably, as von Baer aptly put it, one from the general to the special. Thus a sponge, a sea squirt, and a man may and do agree in the essential phases of their earliest development. But the special features of each group of sponges, sea squirts, and quadrupeds are soon respectively assumed, and finally there appear those more defined structures which mark the completion of development, and which land us within the class order or even species to which each belongs. Development may thus be compared to a journey in which all the travelers, or developing animals, start from a common point, and in which all pursue, at first, a common path that shortly, however, branches out into numerous diverging roads and routes, each leading to the goal or destination of the race. Community of origin is proved by two animals following the same beaten track for a longer or shorter distance, dissimilarity arising when their pathways diverge and the route divides. Thus, much for what is observed in the development of animals, as already illustrated in these pages. What is to be inferred by the biologist from the facts of early development? The reply was clearly enough given in the phrase, development repeats descent, or otherwise, the history of an individual's development presents us with a panoramic or changing picture, more or less obscured, of the descent or development of its race. In the absence of such a thought, all development is a mystery. Rejecting the idea that the phases of individual development repeat the evolution of the species, we may only say that the facts of natural history are either each a senseless paradox or form a mere snare to entrap our judgment. Even in the later developments of animals, we were able to trace, as we have seen, striking likenesses, provable only on the theory of evolution. The mere reference to crustaceans and echinoderms will suffice to indicate the grounds on which the latter assertion is based, whilst the history of the insect class in its developmental aspect will shortly be shown to teach the same practical and pregnant lesson. It might be thought that the teachings of development had by these examples received copious enough illustration, but there remain for notice one or two life histories which, whilst they may trench upon fields already treated, possess yet an interest of their own. It is to these latter examples that we now refer by way of a closing reference to the early history of animals at large. Above the rank of the insects, or at least in a different group of the animal world from that in which they are contained, we may find plain illustration of that connection between apparently different classes of animals which evolution explains in rational and consistent fashion. The group of the mollusca, known popularly as that of the shellfish, and having as its typical members the oysters, mussels, cockles, snails, whelks, and cuttlefishes, the latter existing at the head of the group, presents us with one or two typical examples of the truths and inferences of development. There are at least 4 well-marked classes in the mollusca, and the names of these 4 groups may be placed before the reader by way of enabling us to retain their distinctness clearly in mind. Thus, firstly, we find the class Lamellibranchiata, or bivalves, represented by the oysters, cockles, mussels, clams, etc. Then succeed the Gasteropoda, of which the snails, slugs, limpets, whelks, chitons, etc. are examples. The Pteropoda form a small class often popularly named sea butterflies, and of this group the Clio and Hyalea may be selected as representatives, whilst last and highest come the Cephalopoda, or cuttlefishes, of which the familiar octopus, the argonaut, and nautilus are examples. Such is the constitution of the molluscan type of animals. When we study the development of the three first mentioned classes, we are struck by the similarity they present in their early history. The cuttlefishes, it may be mentioned, differ from the other groups in development and present us with an ancient and early specialized group of beings whose early history and evolution is really a matter of geological interest and lies without the limits of the present chapter. The early stages of a bivalve, such as a cockle, to select a familiar member of the first of the classes just noted, exhibit the usual process of segmentation of the egg common to all animals. Sooner or later, however, the young bivalve develops a somewhat rounded body, at the upper or head extremity of which appears an expanded disc, often described as consisting of two distinct lobes or halves, richly fringed with the minute vibratile processes called cilia, and named the velum. In the center of this velum, an elongated tuft of cilia is usually found in addition, the tuft being known as the flagellum. Thus provided with its vibratile hairs, the young bivalve swims freely through the sea, and is thus said to exhibit its veliger stage. Then a patch of substance forms on the back of the embryo. This becomes the mantle which lines the shell, and in fact forms the latter structure. Whilst in due course the internal organs are developed, and the young shellfish assumes the likeness of the adult. The oyster and cockle are thus seen to pass through a veliger stage, each with its ciliated lobes and its free-swimming powers, through the exercise of which the oyster spat may be conveyed to great distances from its birthplace. As we shall presently note, the likeness of this wandering embryo to the young of certain lower animals is distinctly marked. The curious shipworm, or the teredo, which was termed by Linnaeus Calamatus navium, and which effects an immense amount of destruction annually on the wood of our piers and harbors, is in reality a bivalve mollusk. Its body is shortened and its breathing tubes are extended to form the worm-like body, whilst its shells are rudimentary and serve as boring organs. The teredo first undergoes segmentation within the egg, and then appears as an active, free-swimming veliger, differing from the young cockle only in that there is no lash-like flagellum. Then its mantle and shell are formed, and when 5½ days old, the shells have well-nigh invested the whole body. Next, the foot of the shipworm is developed, and the velum becomes a crown of cilia. Then, as the young animal seeks the wooden pile wherein it is destined to bore and ensconce itself, the shells come into play as excavating organs, and with the growth of the elongated body, shipworm development may be said to conclude. Thus we find that the course of bivalve development is distinctly enough marked. Only in 1 or 2 cases, such as that of the freshwater mussels, Unio, is the veliger stage suppressed. But this latter fact will cause no surprise to the student of development, who is well aware that the effects of varying conditions on the developing young are seen in the production of many changes in an early life history, and in rendering obscure many phases in the panorama of individual evolution. Coming next to the gasteropods, of which the limpets, whelks, snails, slugs, and the univalve shellfish at large are examples, we find a striking similarity in their early history to the development just sketched. A mussel or oyster or other bivalve has, as everyone knows, no distinct head. This may be the result of degradation, but in the snails, whelks, and their neighbors, the head is plainly enough marked, although in certain low forms of the gasteropod class, this head development may not be at all prominent. Such lower members are illustrated by the dentalium or tooth shell, otherwise often named the elephant's tusk shell from its obvious resemblance to the latter structure. In the early history of dentalium, we find obvious resemblances to the development of the bivalves. First, segmentation or division of the egg takes place. Next, the young tooth shell, on escaping from the egg, appears as a rounded body and possesses tufts of cilia for swimming, and likewise has a flagellum in front. The body then lengthens and develops 7 circlets of cilia, the resemblance between the young tooth shell in this guise and an embryo worm being unmistakable. Then the shell is formed by the mantle as before, and the cilia form a velum as the upper extremity of the body. the young condition of the bivalve being closely imitated at this stage. The shell, at first open below, unites by its lower edges to form the tooth-like structure of the perfect animal, and with the further growth of the internal organs, dentalium becomes the mature animal. There cannot exist a doubt that, as the lowest gasteropod and as a poor relation of the higher whelks and snails, dentalium's life history shows, as might be expected, the closest approach, firstly, to animals of lower grade than mollusca, and secondly, at a more advanced stage than that of the veliger, to the bivalves themselves. Equally interesting is the chronicle of development which those little limpet-like animals, the chitons, present to our view. These latter forms are found adhering to the rocks and stones at low water, like the neighboring limpets. They agree with the limpets in being gasteropods, but their structure is, if anything, lower than that of the familiar mollusks just mentioned, and their shell is not univalve, but composed of no fewer than 8 pieces, arranged one after the other on the animal's back. No definite head, however, is found in the chitons, this lack of front extremity being, as before, a proof of lowness and democracy in the scale of gasteropod society. The general aspect of a chiton is unquestionably more like that of an articulated or jointed animal than of a mollusk, in which latter we do not expect to see segments of any kind represented. It is likewise a fact of much interest that these chitons are a remarkably ancient group of the gasteropod class. They may, it is true, be regarded by the strict rules of comparative anatomy as lower organisms than the whelks and their relations. But if antiquity of origin be esteemed in the gasteropods, as it is in higher circles a criterion of respectability, then the chiton race may claim a superior rank to many of their neighbors, and may maintain that, when the univalve race was but in the infancy of its development, they possessed a stable and well-founded family connection. The chitons begin their fossil history in the lower Silurian rocks, and appear at the present time with but little variation from their past structure. They are, therefore, unquestionably an ancient series of beings, which have most probably sprung from a far-back rootstock, whence the gasteropods themselves and other mollusks likewise may have branched off to become the superior shelled races and tribes of today. What then is the course of chiton development? As we should expect, it is much more primitive, much nearer the type of the worms and of dentalium development than that of other univalves. The researches of Lovin have made us acquainted with the early history of the chiton group. From the egg, the infant chiton issues forth as an oval speck, possessing a circle of cilia surrounding its body near the front extremity, and likewise bearing a tuft of cilia on its head. The likeness between the young chiton and the young cockle is clearly traceable. An eye spot soon appears on each side of the ciliated circlet, and the body next becomes annulated or ringed in appearance, such an aspect reminding one most forcibly of the young stages of the worms. Even when the young chiton exists in this free, swimming state, the segments of the shell begin to appear, and correspond with the rings into which the larval body is divided, whilst subsequently the broad foot is developed, and the animal settles down into a sedentary and placid existence on the rocks and stones of the coast. Chiton development thus tells a tale of early origin and of alliance with the worm stock. In this respect it forms a worthy companion to dentalium itself. The development of the familiar pond snail, Limnaeus, as studied by Professor Ray Lancaster and others, may render us acquainted with normal gasteropod development in its higher and most typical phases. The eggs of the pond snail are to be found in June deposited on the undersurface of the leaves of water plants, enclosed in capsules containing a white jelly-like matter. The egg undergoes complete yolk segmentation, and then the gastrula stage, with its 2 layers, repeated in all animals from sponge to man, appears. The mouth of this sac closes as the young form passes to enter the veliger stage, in which the body is oval and possesses a ciliated ridge. This latter stage has also received the name of trochosphere. Ultimately, the foot is developed, then the shell appears, and in due time the snail form is assumed. In the pond snail, as a high form of mollusk, we unquestionably find a velager stage, reminding us of the similar phase in other and lower univalves and in bivalves. It is a noteworthy fact that the land snails and slugs do not show the velum, notwithstanding their apparent nearness to the pond snail. The suppression of the velager stage here does not surprise us. On the contrary, we are fully prepared for such lapses and omissions in development by the consideration already enforced that altered ways of life must inevitably produce a changed life history. Such omissions, in fact, exactly answer the expectation of the evolutionist, and their absence would indeed prove a veritable stumbling block to his hypothesis. In the top shells, Trochus, familiar enough as native species, it may be mentioned that the velager stage, or that of the trochosphere, is well represented, whilst in this stage the embryo is also marvelously like the young of certain worms, and also resembles that of some of the rotifera of wheel animalcules. Later on, the velum of the trochus grows larger and becomes more prominent, and as the shell develops, the larva assumes the likeness of the young top shell. Such a life history is worth recording even in a cursory fashion, if only to emphasize the fact that, even in some undoubted univalves, the likeness to lower worms is remarkable. Certain other univalves of somewhat different structure from those whose development has just been described may now be noticed. These latter are the so-called naked gasteropods, in which a shell is either rudimentary or wanting altogether. But the curious fact remains that, whether a shell is present or not, these animals invariably possess that structure in their embryonic state. This shell, which is thus never destined to be developed, is an illustration of rudimentary organs, which, like the teeth of the unborn whalebone whale, possessing no teeth whatever in its adult state, have a reference to a past state of things. These teeth in the rudimentary shell are heritages derived from ancestors which had well-developed teeth and shells, respectively. Otherwise, and on any other theory of nature, their mere existence is a hopeless and insoluble puzzle. The shell-less univalves to which we refer are often familiarly named sea slugs, sea lemons, and the like. By naturalists they are placed in such genera as Doris, Aeolus, Aplysia, etc. Other examples of these mollusks are included in the genus Bulla, or that of the bubble shells, possessing a delicate shell, and Aplysia, or that of the sea hares, famed of old as an ingredient in classical poison cups. Bulla and the sea hares possess each a thin shell, which, however, is a secondary growth, and does not represent the true shell or that developed in early life. Now, in these naked gasteropods, there is a well-marked velager stage. Moreover, if the development of such a form as Aeolus, or its neighbors of the sea lemon tribe, be studied, the young form is observed at one stage of its career to present a singular and highly characteristic appearance. It possesses a velum consisting of two well-marked lobes, richly ciliated, and by means of which it swims rapidly through the sea, whilst the animal's foot and its shell are also readily observable. Far away in the northern seas, the Arctic voyager may sometimes sail for days, or rather for nights, through water which may be discolored by the innumerable myriads of small organisms floating on its surface. Each of these beings is of very small size, certainly under an inch in length, as a maximum measurement, and each paddles or flaps its way through the sea by means of a pair of wing-like fins attached to the sides of the neck. Such are the sea butterflies, or pteropoda, already mentioned as a class in the molluscan group. Their title to be regarded as shellfish rests on the fact that, besides agreeing with other molluscan characters, they may possess a delicate glassy shell. But this structure may at the same time be wanting, and a head may also be indistinctly represented, the latter fact indicating, as we have seen, a position of inferiority in the molluscan scale. Now, when a pteropod is even cursorily regarded in the possession of its wings or fins, borne on the sides of its neck, its resemblance to the young of some of the naked gasteropods, such as Aeolus, is both close and unmistakable. In their development, the pteropods possess a velum, like most univalves. This velum is believed by good authorities to remain developed and to constitute the wings or fins of these animals. By other authorities, their fins are believed to represent certain side lobes of the molluscan body, and as such are regarded by this second theory as secondary developments. However, that the pteropods represent a rudimentary or primitive set of beings, no one may doubt. Let us bear in mind that they run through the same early phases of development as gasteropods, and that not only is the velum or veliger stage represented in their history, but that certain members of their class present the cilia-girdled appearance, proper to the early phases of worm development. Let us also reflect that the pteropod seems to have been arrested in its development at or a little beyond the veliger stage, and we may readily understand the position of those naturalists who, comparing the young of the naked gasteropod with the adult pteropod, see the closest affinity and relationship between them. The pteropod in this view represents a permanent larval or arrested gasteropod. Both have arisen, if the story told by development is worthy of credit, from a common rootstock, of which the veliger stage is the transient representative. Both have developed in parallel, or it may be, in corresponding and similar grooves. But the gasteropod has been evolved beyond its veliger stage to assume a higher place in the animal series, whilst the pteropod has been arrested in its development at this stage, and has assumed, with possibly a little fixation of its characters, a larval condition as the badge and mark of adult structure. Passing last of all to a lower group of mollusks, that of the brachiopoda, or lamp shells, we may find through these latter forms a passage to the still lower and more primitive stock from which the molluscan group may be presumed to have originated. The brachiopods form a scarce group of shellfish in our present seas, but in past epochs of this world's history they were abundantly represented. The Silurian rocks, to mention but one group of formations, literally teem with their fossil representatives, whilst the paucity of these shells in existing waters is matter of zoological notoriety. These lamp shells are, therefore, an extremely ancient group of living beings. That they are inferior in many phases of structure to the common bivalves, such as our oysters and cockles, is matter of fact. Hence, the development of these lamp shells may be presumed, on a priori grounds, to be fraught with meaning and information as to the descent and origin of the mollusca at large. Let us therefore endeavor to follow out the researches of Morse on the development of these singularly interesting forms. Studying one species, Terebratulina, the common lamp shell of the American coast, the first free-swimming stage is that of an elongated body, which divides itself crosswise into 3 rings or segments, the front one of which becomes provided with long, actively moving cilia. Eye spots also appear on the front segment, and the likeness of the young lamp shell to an embryo worm is at this stage plainly apparent. Nor is the likeness lessened when the middle segment is found to develop 4 bundles of setae, or bristles, such as appear in the worms. Then succeeds the stage of fixation. The young brachiopod now attaches itself by its lower segment, and the middle segment increases greatly in size, so as to form a kind of hood enclosing the front segment in part. Then the front segment decreases in size. The middle portion originates the bivalve shell, which soon comes to enclose the body, the lower or third segment being represented by the disc or stalk of attachment. The technicality of the subject prevents our following out for the reader the later stages of lamp shell growth, in which striking likenesses are presented not merely to brachiopods now extinct, but likewise to the young stage of those plant-like animals named polyzoa, and of which the sea mats, flushtri of our coasts, are good examples. Hence we conclude that the brachiopods present us with a group which has sprung from a worm-like stalk, along with the sea mats, thus showing us the possibility of higher mollusks having had a similar origin. End of section 29. Chapter 11, The Evidence from Development, concluded. 3. The Development of Molluscs, Amphibians, etc., Part 1. Section 30 of Chapters on Evolution by Andrew Wilson. This LibriVox recording is in the public domain. Chapter 11, The Evidence from Development, concluded. 3. The Development of Molluscs, Amphibians, etc., Part 2. The early history of the worms themselves, belonging to the annulose type, forms a concluding phase in these investigations into the history of the molluscan race. If we study the development of one of the true sea worms, such as Aranicola or Nereus, we shall find a striking reproduction of some features with which our molluscan researches have already made us familiar. The young worm makes its first appearance as an active, free-swimming, barrel-shaped body provided with cilia, disposed in various fashions in different groups of the class. Thus, in some embryos, there is a first band of cilia around the body in front of the mouth. A second band exists at the opposite extremity, and tufts of these cilia may also be developed at the extreme front of the body. In other cases, numerous bands of cilia encircle the body at its middle portion only, whilst a third set of cases exists where a broad zone of cilia occupies the middle region with or without a tuft at the head extremity. Out of such larval forms, the young worms are gradually developed, the head and front segments appearing first in the order of growth. Certain of these sea worms, which, like Serpula, live in tubes of lime or other matters which they fabricate from the minerals of the seawater, possess a development equally characteristic with that of their free-living neighbors. In the larvae of these tube-dwelling worms, the head is provided with cilia, disposed chiefly in two rings, one at either extremity of the body. Soon, tentacles are developed from the head portion, the body becomes segmented, and the tentacle which, under the name of the operculum, is destined to form a stopper to the mouth of the tube, may likewise be discerned. At this stage, with its segmented body, the young tube-dwelling worm resembles the permanent condition of its free-living neighbor of the sand. Hence, when we discover that the tube-dweller finally secretes a tube, and lodging its body therein becomes a stationary form, we conclude, rationally enough, that both kinds of worms have arisen from one common stock, and that the tube-dwellers represent the more modified race of the two groups, whilst they likewise may be regarded as degraded forms when compared with their free-living neighbors. We have thus had presented to view a series of developments extending from those of the mollusks through the lamp shells, and finally ending with that of the worms themselves. Is there evidence at hand to show that something more than a theoretical conception of the connection between these apparently dissimilar forms is a warrantable thought? The answer to such a question depends on the credence we place on what development teaches. If the truth of the axiom that development repeats descent be not admitted, it is worse than useless to invite comparison between the larva of a chitin and that of a worm. Unless the mind has been prepared to discover in development the shifting and progressive past history of a species, there can be no benefit of an intellectual kind in comparing the likeness of the young brachiopod with the early stages of the worm. But conversely, when it is admitted that all development is meaningless unless some idea of its use, purport, or cause is afforded, and when in the study of the phases of an animal's growth we are led to see prospects of tracing its past evolution, the likenesses and analogies of development become forcibly plain and valuable. Primarily, it may be said that a very large part of the reasonableness of evolution depends on its rational interpretations of development. Without development and its lessons, evolution would be well nigh unprovable. Conversely, without the idea of evolution, the development of animal or plant is a meaningless piece of natural transmogrification and change. Insofar as the life histories at which we have just glanced are concerned, the general conclusions to be drawn from their study lie on the surface of the subject. Beginning with the worms and their transformations, we find a type of larva presenting a rounded body with variously disposed cilia, which simply becomes segmented and with little further change becomes the worm. From the worms to the lamp shells is an easy transition, for in the development of the latter, we find the clearest reproduction of the features of the young worm larva, in the body divided into its three segments and exhibiting its cilia and eye spots, whilst, as Huxley remarks, the resemblance to the worm larva is increased when we find the young lamp shell developing bundles of bristles, such as the worm possesses on the middle joint of its body. From such resemblances, Huxley is more than justified in remarking that, whilst the lamp shells bear a likeness in development to the plant-like sea mats and their neighbors, their development, quote, no less strongly testifies to their close relations with the worms, unquote. Thus, the evolution of a race of lower shellfish from a worm stock is plainly enough taught by development, and such a fact testifies directly enough to the possibilities of other molluscan developments having had a similar origin. Coming next in order to the mollusks themselves, we find two classes, the bivalves and the gasteropods, in each of which certain primitive forms of development may be traced. The veliger stage may be regarded as common to both groups, and the common origin for both classes may reasonably enough be argued for and maintained on this ground alone, and apart from any plain agreement in structure. It is, however, in the lowest members of each group that we may expect to find the most marked likeness to the primitive type and rootstock from which these classes have been derived. Hence it is to chitin and dentalium that we turn for aid in solving the problem before us. The young tooth shell is unmistakably a worm. Its barrel-shaped body, its circlets of cilia, its end tuft of these appendages are all characters which reproduce before us the embryo worm. Nor is the early history of chitin materially different from that of the tooth shell. The young chitin leaves the egg, as we have seen, with a ciliated girdle in the middle of its body and a long tuft of cilia on its head, whilst this embryo seems to proceed even further on the worm track when we find its body to become segmented or divided as in the worms, these divisions becoming the shell plates of the mature chitin. Thus chitin may be regarded without exaggeration as a worm form existing under a molluscan guise. And when we arrive at the higher gasteropods with their veliger stage and trochosphere, we see produced before us simply a later modification of the worm stock. The life history of a sea butterfly or pteropod, in fact, takes up the narrative where the development of chitin ends it. Chitin led us to the worm larva stage, and thereafter branches off on its lower molluscan path. But the pteropod may, as we have seen, begin life as the worm, and proceeds not merely to develop its veliger stage, but remains permanently therein, flapping its way over the surface of the sea by means of the permanent velum in the form of the fins or wings. Last of all, a gasteropod like Aeolus presents us with a multum in parvo of the whole process of gasteropod and molluscan evolution. Here we take up the story at the stage where the pteropod history concluded. Aeolus and its neighbors, or Limnaeus, passing through the pteropod stage, each with its velum, develop onwards to become the higher and shelled gasteropod, and represent the furthest evolution of the race. Thus, from the worms to the lamp shells on the one hand, and to the chitins and tooth shells on the other, from these latter in turn to the pteropod and thence to the bivalves and gasteropods, the track of development seems plainly marked. The whole story it tells is that of a shifting panorama of the modification of the animal form, phase succeeding phase, and each new succession of forms obscuring, or it may be intensifying, the development of the preceding classes and groups. But clearly marked or obscure, understood fully or only suggested to the mind, the whole process of development reveals to us the operation of a great law of evolution and progressive change, manifested through those wondrous cycles and transformations which nature seems never weary of exhibiting to the earnest mind and seeking eye. If, finally, one might be tempted to inquire into the origin of these ciliated worm larvae themselves, we may find that speculative natural history is not unprepared with a reply. We are reminded that, as the early stages of egg segmentation are not peculiar to the mollusks, so neither are the veliger stages the special belongings of that group of animals. The velum, or its representative ciliated girdles, appears before us equally in the development of the echinoderms or starfish group, of the worm, of the wheel animalcule or rotifer, and of the mollusk. The zoologist would further remind us that these ciliary bands often remain in adult animals, and are represented by certain stable possessions, such as tentacles or feelers, gills, the arms of lamp shells, and like structures. It is probable enough, says Professor Ray Lancaster, quote, that all the ciliated bands of invertebrate embryos, even of adult organisms, can be explained as derivatives of one primitive organ, unquote. If this thought be fully worked out, it contains a veritable philosopher's stone for the zoologist, inasmuch as it enables us to account for the forms and structures of animals on a rational basis. That is to say, the particular form and structure of an animal or class are due to the fashion in which the original ciliated bands of the larva and the embryo itself have been modified by the external and internal forces which now, as of old, operate on living things. Professor Lancaster has suggestively worked out this idea of the derivation of all existing embryos from a type form to which he has given the name of architroche, a form represented by deputy, so to speak, in certain worms and in the CMAT class as adult organisms. Such a theory explains to us, on a basis of a reasonable nature, how different forms may arise from a similar root larva. And it may be added that should any objection be urged to such views on the ground that they are entirely hypothetical, one may retort that to all other explanations of the past of nature, whether theological or scientific, exactly similar opposition may be offered. Further, we must reflect that in any case, we have to choose between filling up from our observation of nature the gaps in our knowledge which a philosophical necessity entails, or allowing these gaps to yawn unsatisfactorily and permanently unfilled. The rational mind is not likely to hesitate in its choice of alternatives. And if, lastly, it be borne in mind that, so far from being merely shadowy theories, such ideas of the origin of animal forms are based on close observation of nature, often the work of many concentrated lifetimes, the logical standing of a theory which connects the facts of nature and by so connecting explains them needs no justification, as it fears no honest and unbiased criticism. Turning now to the vertebrate animals, we may find in the class of frogs and newts, amphibia, material for illustrating some of the most important phases in normal development, and in altered life histories as well. The life history of a frog has already been alluded to in a previous chapter in connection with the evolution of lungs. It is needful, however, again briefly to refer to this life history as a starting point for the due understanding of other and allied classes of development. The frog begins its existence as a tadpole, breathing first by external and then by internal gills, and possessing a two-chambered heart, resembling that of the fish. Sooner or later, the hind limbs begin to appear, then the forelimbs are developed, and the frog's lungs likewise begin to make their appearance. At this stage, the animal resembles its neighbors, the proteus and axolotl, which are tailed and which breathe throughout life by both gills and lungs. Later on, the gills disappear entirely. The tail becomes rudimentary, and the frog, leaving the water, becomes the terrestrial lung breather with which we are so familiar. To repeat Huxley's words in reference to the case for development as a guide to the history of the race, quote, "If all living beings have come into existence by the gradual modification, through a long series of generations, of a primordial living matter, the phenomena of embryonic development ought to be explicable as particular cases of the general law of hereditary transmission." On this view, a tadpole is first a fish, and then a tailed amphibian provided with both gills and lungs, before it becomes a frog, because the frog was the last form in a series of modifications whereby some ancient fish became an urodele or tailed amphibian, and the urodele amphibian became an anurus or tailless amphibian. In fact, the development of the embryo is a recapitulation of the ancestral history of the species, unquote. That there are ancient fishes, still represented by living species, which may have served as the starting point of the frog race, is matter of zoological fact. Quote, "Various features in the anatomy of the tadpole," says the late Professor F.M. Balfour, "point to its being a repetition of a primitive vertebrate type. The nearest living representative of this type appears to be the lamprey." Unquote. This author also points out how close are the resemblances between the mouths of the tadpole and lamprey, and a still more remarkable fact consists in the observation that many of the peculiarities of the skull of the tadpole are reproduced in the skull of the lamprey. Whilst, as Professor Balfour remarks, these resemblances must be due to deeper causes than mere adaptation to similar habits, there are yet, quote, no grounds for supposing that the lamprey itself is closely related to an ancestral form of the amphibia, unquote. The more feasible opinion is that which would assume that both lamprey and tadpole are descended from a common and still more primitive stock. It would seem, indeed, that the ganoid fishes, of which the sturgeon, bony pike, and the fossil forms of the old red sandstone are examples, together with the allied Lepidosiren and Ceratotus, possess an allied origin from the common root of lamprey and tadpole. The facts already detailed in Chapter 6 concerning the development of lungs in these latter fishes would of themselves seem to support this idea of their origin. Just as along one line of descent the gilled tadpole race has developed its lungs as the frogs of today, so starting from the same ancestry, but developing along a different pathway, the Lepidosirens and their neighbors, as if animated by like air-breathing tendencies, have developed lungs likewise. Similar tendencies towards a certain goal in development, in other words, have produced like results in the evolution of two branches of the vertebrate tree. An interesting fact may be added to these considerations, namely that one tadpole form, that of Dactylothra, presents the closest resemblance to certain fossil fishes of the old red sandstone period. These fishes belong to the ganoid type already mentioned, and the Dactylothra tadpole, whilst resembling the ganoid stock, also shows affinities to the shark and dogfish type. The latter fishes are nearly allied to the ganoids, and both appear in the geological record at once as the oldest of fossil fishes and vertebrates. This curious tadpole probably represents a period in the evolution of the frog race, after that race had been specialized from the lamprey stage, and had already advanced somewhat on its amphibian pathway. It therefore requires no stretch of the imagination, but the exercise of sober reason, to note, firstly, that as all the amphibian class, frogs, toads, newts, and their less familiar neighbors, tailed and tailless, together begin life as tadpoles, and secondly, that as they end, some like the frogs, tailless and gill-less, others like the Proteus are axolotl, possessing both gills, lungs, and tails, the assumption remains clear that these animals have sprung from a fish ancestry. It is further matter of fact that their development has followed two pathways. In the one case, the frogs and toads have passed towards a pure air-breathing existence and have emerged from their development as land animals, pure and simple. In the other case, the lower stock of the class, represented by the Proteus and axolotl, etc., have retained many of their lower characters, most notably gills and tail, and have accordingly taken a lower and less modified position than the frogs and toads. The familiar tailed newts, which though living in water and beginning life as gill-bearing tadpoles, breathe as adults by lungs alone, represent a middle term in the series, in that they still retain the larval tail of early life. Whilst the ordinary course of amphibian development runs as has just been described, there are certain exceptions of extreme interest from the evolutionist's point of view. Firstly, there are certain cases of curious development amongst frogs themselves, which deserve a passing notice. There are peculiarities, for instance, in the carrying of the eggs, which are eloquent enough in their testimony to the singular modification of structure and habits which may accompany alteration of surroundings. Thus the tadpole form of Pseudus paradoxa attains a very much larger bulk than the adult. Such a circumstance points either to some nutritive condition affecting the larva, or shows that the larva reproduces some ancestral form which was larger than the living frog. The female of Nototrema marsupiatum, a tree frog inhabiting America, carries her eggs in a large pouch which underlies the skin of the back and opens behind. The larvae of Nototrema are said to want external gills. If correct, this circumstance points to high modification in the development of this frog. A like feature to the method of egg carrying found in Nototrema is seen in Opisthodelphis, another American frog, and Hylodes, likewise an American tree frog, lays its eggs in the axils of leaves, that is, in the angle between leaf stalk and stem, the water needful for their development being found in the chance drops resting in that situation. The male of Elytis obstetricans of Europe winds the long chain of eggs laid by the female round his thighs, so that he seems to possess trunk hose and puffed breeches, as Mr. St. Mivart remarks. Dropping in due course into the water, the young burst forth from the egg coverings and swim away, leaving their father frog once more unencumbered and free. Another frog, Rhinoderma darwinii, a denizen of Chile, exhibits another curious modification of a different kind. Rhinoderma, like the edible frog of Europe, possesses certain vocal sacs or bags placed within the mouth, whereby the resonance of the mouth and the loudness of the croak are increased. It is interesting to find, however, that Rhinoderma has come to use its vocal sacs as nests, the newly laid eggs being thus received into the male parent's pouches and the young remaining therein till they attain a considerable growth. We certainly know of male fishes in the seahorse genus, Hippocampus, which carry the young in a pouch, and another male fish, Arius physis, like the Rhinoderma, carries the eggs in his mouth and therein hatches them. In Rhinoderma, the vocal sacs are greatly enlarged, and in fact extend onto the flanks and belly of the animal. From 5 to 15 tadpoles were found by Espada in each sac, the smallest being at the bottom. The largest was about half an inch long and had well-developed legs. Neither the old nor the young tadpoles had any traces of gills, and from their full development, the conclusion that the young are in some way nourished in these sacs seems by no means far-fetched. The Rhinoderma presents us, therefore, with a case in which the organization of the male has become curiously and permanently altered to a decidedly new way of life, so much so, indeed, that the skeleton has become modified from the pressure of the curious egg sacs of the mouth. More curious still, on account of the very singular modification which must have produced the feature in question, is the female Pippa americana or Suriname toad, the skin of whose back becomes soft at the breeding season. The eggs are pressed by the male into this skin, which grows over them and encloses each in a kind of cell. Very curious it is to find that in the cells of the maternal back, not only the tadpole stage, but the whole metamorphosis of this toad is passed. The young toads develop a long tail within the egg, this appendage being absorbed before they are hatched, whilst the useless gills disappear at a very early period in larval existence. Over 120 cells have been counted in the back of this toad, and from these cells the young emerge as miniature facsimiles of the parent. Another noteworthy case of altered development is that of the Hylotis martinicinus, which passes through the whole of its metamorphosis within the egg, and emerges, as do the young of the Suriname toad, a perfect frog, which otherwise would require to pass several weeks in water to complete its development. End of Section 30. Chapter 11. The Evidence from Development concluded. 3. The Development of Molluscs, Amphibians, etc. Part 2. Section 31 of Chapters on Evolution by Andrew Wilson. This LibriVox recording is in the public domain. Chapter 11. The Evidence from Development concluded. 3. The Development of Molluscs, Amphibians, etc. Part 3. Now, to what conclusions do such facts lead us respecting the modification and alteration of development? It is perfectly clear that, as frogs and toads are normal tenants of the water in their early and tadpole stages, and are provided with gills as aquatic forms, those species which pass the whole of their development in the back of the mother, or even within the egg, must represent the most modified members of the frog class. We are therefore entitled to take their case as illustrating the best marked of the tendencies to alteration which the race presents. A frog which, like Elytis, carries the eggs but drops them into water when they are ready to leave their primary abode, represents the first stage of modification. We are led a little farther on the way towards a suppression of metamorphosis by the case of Hylotis, which lays its eggs in the axils of leaves, where moisture is relatively scarce, but where development is nevertheless undergone in due course. More advanced is the Suriname toad, where the young pass their entire metamorphosis within the egg and in the mother's back. The Hylotis martinicinus being but a further development still, seeing that in this frog the whole development is carried on within the egg, and metamorphosis is therefore practically hidden and unseen. We may not doubt, therefore, that the amphibian class exhibits thus a tendency towards direct development, or that without metamorphosis. Imagine the result of the later stages of such a modification of reproductive habits and customs. Hylodes martinicinus, for instance, is now practically in the position of an animal which undergoes all its changes within the egg, and which in all probability will, in time, further shorten and condense its life history. If such changes and modifications are occurring before our eyes today, is it unreasonable to regard all ordinary and direct developments, and amongst others, those of fish, reptile, bird, and man, as in reality abbreviated and brief chronicles of once extended chapters in animal histories? A fish or bird passing through its development within the egg undergoes a metamorphosis, it is true, but shortened and condensed as compared with that of the frog. There is no reason against the supposition, but every circumstance of life favoring it, that once upon a time fish development and descent could have been as plainly seen from the outside world as the frog's descent is traceable before our eyes today. Higher development and progressive tendencies invariably tend to shorten and condense the early stages of growth. Hence the value of such cases as those of the frogs and their neighbors, which through mode of life, habits, and other and unknown conditions have retained much of their original way of life, and have revealed to us, through a literal byway of development, the original and primitive phases of that of all other animal forms. The conditions which favor or retard such developments are often obscure or very frequently unknown. The presence of water or its absence, for instance, would favor or retard the continuance of the metamorphosis in the frog class. We must also bear in mind that geological changes, the rising and sinking of land and the like, the conversion of swamps and morasses into dry land, and similar physical changes are powerful factors in producing modifications of habit in aquatic animals, and, through change of habit, of affecting variations in structure and form. It is possible to prove the existence and operation of such changes from many points of view, both from the zoological or biological side and from that of geology itself. The importance of such alterations of the Earth's surface can be proved. This aspect of the subject finds appropriate illustration in works devoted to the facts of geographical distribution and their explanation, whilst we may not neglect to observe the strictly utilitarian points involved in such abbreviated life histories as those we have been discussing. It has been noted that as we ascend in the scale of animal and plant life, development becomes more and more condensed and abbreviated. On a posteriori grounds, we might argue that, from the fact of such condensation accompanying higher life and progressive development, some obvious advantage in the struggle for existence was thereby gained. The nature of such advantage is not difficult to discover. The more prolonged and exposed larval or early existence is, the more likely are the young forms to succumb from loss of food, change of surroundings, or from the attack of enemies and numerous other conditions. On the contrary, with an abbreviated infancy, the animal obtains a distinct coin of vantage. There is less risk of early death and a greater prospect of an earlier and stronger maturity. Thus, the selected races are those which possess the shorter and more condensed life history, and these races, therefore, come to the front in the universal struggle for existence which besets and surrounds the living host today as of yore. As Sir John Lubbock remarks when speaking of the shortening of the insect's life history, quote, "The compression and even disappearance of those embryonal stages which are no longer adapted to the mode of life, which do not benefit the animal, is a phenomenon not without a parallel in other parts of the animal or even the vegetable kingdom. Just as in language long compound words have a tendency to concision and single letters sometimes linger on, indicating the history of a word like the L in alms or the B in debt, long after they have ceased to influence the sound, so in embryology, useless stages, interesting as illustrations of past history, but without direct advantage under present conditions, are rapidly passed through, and even, as it would appear, in some cases, altogether omitted." Unquote. We may here refer to the case of the Mexican axolotl, on account of its peculiar development, and also from its bearings on that of another member of the frog's class, the black salamander, Salamandra atra of the Alps, and its curiously modified life history. The axolotl is a Mexican eft or newt, which retains the gills of early life along with the lungs of the adult stage. it breeds freely in captivity and hence was long regarded as a mature and adult animal. But in 1867, some axolotls were observed to emerge from the water in their Jardin des Plantes at Paris, to cast their skins, and to become transformed into a gillless newt, long known as an American genus and named Amblystoma. Such a change was almost equivalent to that whereby a frog could be metamorphosed into a toad, and hence it excited no small surprise in the zoological world. By careful experimentation, a lady naturalist, Fraulein von Schaven, showed that by gradually inuring the axolotl first to a life amongst damp moss, and then to an existence entirely removed from the water, it could be made to assume the amblystoma form, with its black skin and yellow spots. Weismann states that the transformation occupies 14 days, and Dumeril states the period of metamorphosis as 16 days. Fraulein von Schaven states in her account of the axolotl's metamorphosis that her experiments were begun on June 12, 1874, with 5 larvae about 8 days old. At the end of June, the front legs had appeared in the healthiest specimens, and on July 9th, the hind limbs were developed. Towards the close of November, one of these larvae appeared to remain constantly at the surface of the water, and from this sign, Fraulein von Schaven concluded that the proper and natural period had arrived for the assumption of the amblystoma form. This specimen was accordingly placed on December 1st in a vessel in which its existence was divided between a water life and a terrestrial one. The water being gradually diminished, the gills began to shrivel, and on December 4th, the animal left the water and remained on the earth and moss in the vessel. At this period it molted its skin for the first time. Then also, between December 1st and 4th, the dorsal crest or fin shriveled in addition to the gills, and the tail became rounded like that of the amblystoma. The original grayish-brown color likewise changed to black, and the spots of the amblystoma became apparent. The gill clefts were open on December 4th, when the animal left the water, but in about 8 days these slits were entirely closed. In the other specimens experimented upon by Fraulein von Schaven, the period occupied in the metamorphosis varied somewhat, the greatest differences being due, apparently, to the nutrition of these forms being less active than in those specimens in which the transformation was speedily accomplished. The general conclusion arrived at from these experiments is that, quote, axolotl larvae generally, but not always, complete their metamorphosis if, in the first place, they emerge sound from the egg and are properly fed, and if, in the next place, they are submitted to the necessary treatment for changing aquatic into aerial respiration. It is obvious that this treatment must be applied very gradually and in such a manner as to not overtax the vital energy of the amphibian, unquote. Weismann concludes that, quote, most axolotl larvae change into the amblystoma form when, at the age of 6 to 9 months, they are placed in such shallow water that they are compelled to respire chiefly by their lungs, unquote. The axolotl does not, so far as is known, become converted into the amblystoma form in its native region. In the Mexican lakes it appears to be perpetually and only known as the gilled axolotl. Professor Cope also states that these Mexican animals, when bred in captivity in America, reproduce their like and do not show any tendency towards transformation. Yet in France and elsewhere, as already remarked, the axolotl becomes transformed into the amblystoma in its domesticated or captive condition. But it is necessary to remark that the exact species which become metamorphosed in France was either the Cyrodon lichenoides of Baird or some allied form, and not the Cyrodon mexicanus of Mexico. Baird states that the former species, which occurs 7,000 feet above the sea level in Wyoming Territory, becomes transformed into the amblystoma mavertium, whilst the first amblystomas obtained by Dumeril from the Parisian axolotls appear to agree with another species of amblystoma, A. tigrinum. If these details be taken into account, whilst they do not in the least affect the curious nature of the transformation, they would seem to indicate that more than one species of axolotl undergoes metamorphosis, and this result is exactly that which the naturalist would be led to expect. The general condition probably affects the whole axolotl race and is not confined to any one species. Regarding the amblystomas themselves, it has been already remarked that these newts are well known in America. Over 20 species are known to inhabit North America, and there can be no doubt that these animals live and breed as true amblystomas. As Weismann remarks, quote, "There are therefore true species of Ceratodon which regularly assume the amblystoma form under their natural conditions of life, that is, develop into amblystomas from eggs laid by amblystoma parents, and which propagate in this form. While, on the other hand, there are at least two species which, under their existing natural conditions of life, always propagate as Ceratodon," unquote. That is, develop axolotls from eggs laid by axolotls. Observations by Professor Baird on the development of amblystomas show that, as might be expected, the young gilled larvae arising from amblystoma eggs present a close likeness to the axolotl race. The case of the axolotl illustrates powerfully the effects of a change of surroundings in metamorphosing a species. A succession of dry seasons, operating in the past, has most likely been the active origin of the amblystoma race from the axolotl stock. Presumably, the axolotl, as the gill-bearing form, is the primitive stock, the amblystomas being a derived race, but nevertheless representing a true species of which the axolotl, conversely, may be termed the larval form. To this relationship, however, reference will be subsequently made. The shriveling of the gills seen in the experiments on the axolotl, it is noteworthy, was probably due to a mechanical cause, that of dryness of the surroundings. Once established, the new race of amblystomas would be propagated amidst the condition which best suited them, whilst the axolotls have flourished amid their own aquatic environments. This case of modification of species, however, leads to a much more typical one in which the female of the black salamander of the Alps, a gillless newt or eft, retains her eggs within her body and hatches them, the young likewise undergoing development and casting their gills therein, just as do the young of the modified frogs already described. Furthermore, out of some 40 or 60 eggs, only 2 young are developed, the latter devouring the remaining eggs as food. Thus, whilst the young of the spotted salamander, a neighboring species, number 40 or 50 at a birth, those of the alpine species number but 2. Yet the 2 species are equally numerous, a fact showing powerfully how one animal, despite disparity of numbers, may equal in vitality an apparently more prolific race. For the 2 young of the alpine salamander, when born, are large and active, have passed completely through their development, and possess strong, acrid skin secretions, whilst those of the spotted species are comparatively helpless when born, and have not got rid of their gills. Hence the latter are subject to a greater mortality, and the proportion of adults to young is therefore relatively small. On no rational theory of nature could it be believed that a young newt was provided with gills, and that thus furnished it was destined to be developed within its parent's body. The 2 facts of the presence of gills and the development of the alpine salamander within the parent body are in utter opposition to each other. Further, we know that when taken from the parent body, long prior to their natural period of birth, and placed in water, the young of the black salamander live and breathe by their gills, as was undoubtedly the original habit of the species. Placed in water, the young beings live for weeks, and ultimately develop from their water life into land salamanders. But in this latter experiment, the full development of the young occurs weeks after the time when they would have been moving actively on the Alps, had they been left to their development within the parent frame. Thus we see, firstly, that the modern development of this animal is clearly acquired. Even the curious habit of the 2 larvae eating the other eggs clearly proves as much. And secondly, we again come face to face with a case of shortened and condensed development, favoring at once an early maturity and the increase of the race. Probably a rise of land carrying these salamanders farther and farther from water was a direct cause of the altered mode of life of the alpine salamander. We know that this new adaptation is of relatively ancient origin, for the gills of the salamander placed in water shrink by a natural and vital process of absorption, and not through mere drying and shriveling as in the axolotl. The acquired process of gill absorption has become, in other words, an inherited matter, has become part and parcel of the animal's constitution. As therefore their watery pools were left below by the rise of land, the salamanders would gradually acquire the habit of retaining the young within the body for more and more lengthened periods, and in due time the present state of matters was evolved, including limitation of numbers and acceleration of development, along with the novel condition of utilizing the remaining eggs as a food supply. An important and interesting feature in connection with the preceding cases of altered development consists in the observation that the Mexican axolotl, apparently a mature form, was able to reproduce its species. It may perhaps prove a truer conception of the case if we regard the axolotl as a, quote, permanent larval form, unquote, which has acquired the power of producing young and which has therefore assumed the form, life, and constitution of a species. Analogy supplies us with a valuable series of parallel instances from the records of natural history science. The example in question of a larva acquiring reproductive powers is by no means singular or unique. We have seen that practically a pteropod or sea butterfly is essentially the larval form of the gasteropod, which has had its immature character fixed, and which has acquired the power of producing young. Other cases of this peculiarity are readily found within the confines of the insect class and in other divisions of the animal world. Thus we know that the larva or maggot, itself an absolutely immature form of a fly, Cicedomyia, produces other larvae like itself, and these in turn produce others, which finally, becoming males and females, produce normal young through eggs. There is another insect, Chironomus, of which, as Grimm has shown, the chrysalis lays eggs, and we know of cases in which, as illustrated by aphides or plant lice, and by the queen bees, perfect young may be produced by the one insect alone. So likewise the common newt, Triton cristatus of our ponds, may occasionally, when immature, produce young, and another species, T. alpestris, has been seen to reproduce its kind when it is still in the tadpole stage. Amongst zoophytes, such features are still more plainly marked, for a plant-like animal colony gives origin to jellyfishes, which swim freely in the sea, and later on produce eggs, from each of which a zoophyte in turn springs. These facts were formerly included under the head of alternation of generations, but under whatever name we denote the phenomena, the lesson they teach is uniform and clear. Such cases as these of the insect larvae and the immature axolotls and newts producing young, contrary to the rule that only adult animals reproduce their species, prove to us that, if conditions be favorable, a young animal's development and constitution may be so modified and intensified that it may, whilst still under its larval guise, produce young, and thus assume the likeness and functions of a new and distinct species. Such facts further impress the idea that the young being, equally with the adult, is liable to modification and change, and they therefore teach us that the starting points of new species and races do not always lie within the domain of mature life, but may take origin from stages in development prior to the full period of growth. Given an ultimate independence of the young form, together with the power of producing beings resembling itself, and we may readily conjecture how a new and very different species or race may in comparatively rapid fashion originate from a well-known stock. Mr. Darwin gives us an example of this possibility, the case of the beetle Sitaris, of which the first larvae are active and minute, and possess 6 legs, 2 long feelers, and 4 eyes. Quote, "These larvae are hatched in the nests of bees, and when the male bees emerge from their burrows in the spring, which they do before the females, the larvae spring on them and afterwards crawl onto the females whilst paired with the males." Unquote. Then ensues the laying of eggs on the surface of the honey in the cells by the female bees, the Sitaris larvae devouring the eggs. Then the latter undergo a metamorphosis. The eyes disappear, and the legs and feelers become rudimentary, whilst they feed on the honey. At this stage they more closely resemble ordinary insect larvae, and after further transformation emerge as the perfect beetles. Now, adds Mr. Darwin, quote, "if an insect undergoing transformations like those of the Sitaris were to become the progenitor of a whole new class of insects, the course of development of the new class would be widely different from that of our existing insects, and the first larval stage certainly would not represent the former condition of any adult and ancient form. We can see, adds Darwin, how by changes of structure in the young in conformity with changed habits of life, together with inheritance at corresponding ages, animals might come to pass through stages of development perfectly distinct from the primordial condition of their adult progenitors." Unquote. On this reasoning, the axolotl's later history cannot be expected to coincide with that of the Amblystoma. It is a larval form, which, apparently arrested in development, has nevertheless contrived to develop the lungs which mark the full growth of all amphibia, whilst it likewise retains the gills of early life. The relationship between the axolotl and Amblystoma presents, besides, one of the most effective refutations of that common but ignorant remark that no one has yet adduced any proof of the direct transmutation of one species into another. In the case before us, not merely is the transformation one in which one genus of animals apparently becomes another, but the near relationship of two thoroughly distinct forms is thus proved to lie within the province of exact zoological observation. It should be added that Dr. Weismann of Freiburg, who has devoted much attention to the metamorphosis of the axolotl, maintains that the case in question is one not of sudden advance in a species, but of reversion to a lower stage. He believes that, quote, "those amblystomas which have been developed in captivity in certain instances from Cerodon mexicanus, S. pisciformis, as well as from the Paris axolotls, are not progressive but reversion forms. I believe," concludes Dr. Weismann, quote, "that the axolotls which now inhabit the Mexican lakes were amblystomas at a former geological or better zoological epoch, but that owing to changes in their conditions of life, they have reverted to the earlier perenniabronchiate, permanently gilled stage." Unquote. One of the most interesting facts which lend support to this view of the backward development of the axolotl is the discovery that the axolotls possess a rudimentary intermaxillary gland, furnishing a glutinous secretion, and which serves to aid the capture of insect prey. Now, as this gland exists in a perfect shape in all land amphibians, but is absent in gill-possessing forms, its presence in the gilled axolotls would certainly seem to indicate that these animals retain the gland as a legacy from the higher or amblystoma stage, from which they are believed by Weismann to have descended and retrograded. In whatever light we regard the case of axolotl, the bare facts of its curious development remain unaltered. It seems justifiable enough, notwithstanding Dr. Weismann's opinion, to regard the axolotl as a permanent larval form, and as representing an arrest of the development of amblystoma, producing a literally new race of animals able to reproduce their like, and thus evolving a new group of animals by an easily understood modification of an existent species. The presence of the intermaxillary gland may represent the initial stage or beginning of that gland's development in the axolotl race, instead of a degeneration from the perfect gland of the amblystoma. Inheritance alone might account for the development of this structure, but indeed, whether we adopt Dr. Weismann's view of the axolotl as a case of reversion from amblystoma to its lower stage, or whether we regard the axolotl races as representing larval forms permanently settled to form a distinct race and species, the influence of surroundings in evolving new forms of life receives an apt illustration. Arrest of development, an altered way of life, change of surroundings, and allied conditions are seen to operate powerfully on animals and plants, and are found to effect exactly those changes in the constitution of the living world which evolution postulates, and which meet the biologist at every turn. One typical case of similarity in early development, as suggestive of a near or common origin from the group of birds, may merit mention in the present chapter. Mr. A. R. Wallace points out in an interesting fashion how the hummingbirds of the New World, placed of old side by side with the Old World sunbirds, were in 1850 separated from the latter forms and placed by Prince Lucien Bonaparte near the swifts in his system of classification. That this arrangement was correct, that is, was based upon natural affinities and not merely upon superficial resemblance, is easily provable. Thus the breastbone of a hummingbird and that of a swift are marvelously like. It is not notched behind in either bird, whilst this bone in the sunbird bears 2 depressions. In the color and number of the eggs, swifts and hummingbirds agree, and they also present close resemblances in the arrangement of their feathers. Both have 10 tail feathers and 16 true quill feathers, and in both the first quill is longest. But whilst the bill of a swift is short, broad, and flat, the gape wide and the tongue flat, the hummingbirds have a long, slender, cylindrical bill and a tubular tongue which can be protruded to a great extent, and which is used for drinking up the nectar of flowers. We shall allow Mr. Wallace to tell us of the striking resemblance between these 2 groups of birds, revealed by a study of the hummingbird at an early stage of growth. Quote, "When on the Amazon," says Mr. Wallace, "I once had a nest brought me containing 2 little unfledged hummingbirds apparently not long hatched. Their beaks were not at all like those of their parents, but short, triangular, and broad at the base, just the form of the beak of a swallow or swift, slightly lengthened. Thinking, erroneously, that the young birds were fed by their parents on honey, I tried to feed them with a syrup made of honey and water. But though they kept their mouths constantly open, as if ravenously hungry, they would not swallow the liquid, but threw it out again, and sometimes nearly choked themselves in the effort. At length I caught some minute flies, and on dropping one of these into the open mouth, it instantly closed. The fly was gulped down, and the mouth opened again for more, and each took in this way 15 or 20 little flies in succession before it was satisfied. They lived thus 3 or 4 days, but required more constant care than I could give them. These little birds were in the swift stage. They were pure insect eaters, with a bill and mouth adapted for insect eating only." Unquote. Such an interesting recital once again illustrates the maxim that the likeness between living beings, imperceptible in the adult stage, may yet be plainly enough apparent in the earlier phases of development. As with the crustaceans, where we find a shrimp and a barnacle utterly unlike as adults, beginning life under an essentially similar guise, so with the swifts and hummingbirds. Their likenesses, masked by differences in habits of life, are nevertheless traceable without difficulty in the young state. Mr. Wallace especially reminds us that certain of the sunbirds themselves resemble the hummingbirds in respect of their long bills and tubular tongue, adapted, like those of the latter birds, to feed upon flower juices and upon the insects that infest flowers. He emphasizes the need for distinguishing clearly between characters or likenesses which are structural, that is, are part and parcel of an animal's being, and those that are purely adaptive, that is, arise from a similar mode of life, independently of the origin of the species. The former are transmitted from ancestors, the latter are the products of recent modification. The former indicate the true nature of the animal because they are part of its inheritance. The latter often suggest false resemblances due to similarity of habits and not to community of origin. Thus, whilst the hummingbirds and swifts possess structural and inherited likenesses, the former and sunbirds are related only through similar adaptive characters. The skull of a cuttlefish, to select another example, is comparable in its functions to that of a low vertebrate animal, but on no theory of nature are these 2 groups connected together. They have arisen, like the similarities of sunbirds and hummingbirds, entirely independently, in respect probably of similar conditions, and not of inheritance from a common ancestor. The inherited characters which mark real resemblances are not, as we have seen, always apparent, and the adaptive characters through which the life of the species is carried on may entirely mask and conceal them. As Mr. Wallace puts it, we arrive at, quote, the seeming paradox that the less of direct use is apparent in any peculiarity of structure, the greater is its value in indicating true, though perhaps remote, affinities, while any peculiarity of an organ which seems essential to its possessor's well-being is often of very little value in indicating its affinity for or to other creatures. Thus we are led to the conclusion, favored again by development and its lessons, that the hummingbirds, quote, are essentially swifts, profoundly modified, it is true, for an aerial and flower-haunting existence, but still bearing in many important peculiarities of structure the unmistakable evidences of a common origin. Unquote. End of section 31. Chapter 11. The evidence from development concluded. 3. The Development of Molluscs, Amphibians, etc., Part 3. Section 32 of Chapters on Evolution by Andrew Wilson. This LibriVox recording is in the public domain. Chapter 12, The Evidence from the Life-Histories of Insects, Part 1. When the development of an animal or plant is duly studied, one or two chief aspects of such a subject fail to be considered by the biologist. Either the young organism has been converted directly into the likeness of its parent, or it has assumed the parental form indirectly and through a series of transformations more or less distinctly marked. In other words, the young form has emerged upon the stage of life in the guise of its parent, or it has appeared first in a shape and under an appearance not recognizable as belonging to the race it has sprung from. In the latter case, changes of greater or less extent convert the young being into the likeness of its progenitors. And when such transformations occur in the life history of an animal or plant, it is said to undergo metamorphosis. Everyone, for instance, knows that the butterflies of the garden do not emerge from the egg as winged insects, whilst common information is able to assert that they pass through the larval or grub stage and also through the chrysalis form before becoming the perfect insects. So also the flies begin their life as maggots, and the bees and beetles with other insects exhibit like stages to the butterflies in the course of their development. Furthermore, a frog, as we have seen, practically begins life as a fish, breathing first by external and then by internal gills. Sooner or later, however, limbs are developed, the gills are replaced by lungs, the tail disappears, and the tailless condition of the frog race is finally assumed with its emergence upon the land. Insects and frogs, not to speak of other animals such as crustaceans, whose history has been already discussed in a previous chapter, are therefore said to undergo metamorphosis. Sundry questions not unnaturally rise in the mind which attentively considers such phenomena in the animal world. Firstly, there is the plain question, why do some animals undergo metamorphosis and others not? Then, secondly, may be asked, what is the meaning of metamorphosis, or more primarily, can any meaning be assigned to this process? As we have frequently had occasion to point out, such questions receive no aid or solution from that philosophy which maintains, as an article of unquestioning faith, that the living belongings of this world came forth fashioned in all their excellence, or, it may be added, in all their frequent and apparent imperfections, at the behest of some sudden creative fiat. There is no need to assume development at all on this hypothesis of things, which for the man of science has been slain long ago, though traces of its influence are not unknown in regions removed from the active currents and tides of culture. On the reverse side of matters stands the theory broadly denominated evolution, which, seeing the promise of reading a past and progressive history in the developments which pass in panoramic review before our eyes today, asserts that a law of progress has guided and still guides life's courses and ways. On this theory, we can understand why development takes place, namely, because it is a law of life that the progress and growth of the race should be represented in and carried out through its individual histories. And we can also conceive why development should run in the grooves marked out so conspicuously in many life histories, such as those of insects and crustaceans. This latter fact is explicable when it is repeated that we see in an animal's early growth the lines and stages along which the development of its race has passed. By the very idea of evolution, we expect variety and change to be represented in the development of living beings, for such change is the one great condition which has made this universe what it is. Agreeing as to the main reasons for development and its ways, we should find little difficulty in comprehending how these ways and paths have been followed. As we have already impressed upon the reader, the picture is not always clearly limbed, and its outlines are often meager enough. Still, what we do see and know of its form convinces us of the correctness of the broad deductions of evolution, which deductions, being scorned and denied, leave the whole course of nature a tissue of inexplicable absurdities. In the present instance, dealing with the meanings of metamorphosis, we intend to direct attention to certain details which, for lack of space, have been omitted in previous chapters, and which, dealing with matters of special interest to the student of evolution, may logically enough claim attention in a separate section. Such subjects as the general nature of metamorphosis and how that process is modified by surroundings and other circumstances, as well as the narration of some life histories which illustrate very aptly the general conclusions of evolution, may therefore fitly engage our consideration in the course of our developmental studies. Firstly, then, the general question of metamorphosis demands notice. Whilst it is perfectly true that, broadly speaking, only such animals as insects, crustaceans, and frogs, exhibiting very marked and apparent change of form in passing from the young to the adult stage, may be said to undergo metamorphosis, it would be far more logical, because more true, to assert that the histories of all living beings, without exception, illustrate the process in question. This remark has been made in reference to the developments we have already studied. For example, there is not, after all, such an immense difference between the development of an insect and that of a fish, or, for that matter, between that of a frog and of man himself, when the facts of development are fairly faced and duly understood. No animal or plant is suddenly transformed into the perfect likeness of its parent. On the contrary, it has not merely to grow, but it has to be formed from that which is formless, to become organized by the development of that which has no structure at all, and to advance along lines of development during which it successively assumes a transient likeness to the forms of other and lower beings. Thus a quadruped, whilst undergoing development within its parent's body, in reality passes through as strange and startling a metamorphosis as does a frog outside its parent's body, and external to its egg likewise. A quadruped is really at first like a fish and reptile. So alike are the young of all vertebrates in their early stages that recognition of the nature of any particular form may be an impossibility. Metamorphosis thus occurs in quadrupeds as in frogs, in snails and oysters as in insects. The great and prevailing difference simply exists in the fact that the insect or frog leaves the egg in an imperfectly developed condition, and at an early stage of its career, passing the remainder of its development as an independent being. In the quadruped or fish, or in the bird and reptile, the young animal does not quit the parent body or egg at such an early period, but remains within its primitive shelter to undergo its full development, or at any rate to emerge upon the world of active life tolerably well prepared for the struggle of living and being. Even amongst the quadrupeds, as in well nigh every other group of animals, and as in the plant world likewise, there may be great differences in the degree and stage of perfection at which the young organism is ushered into active or independent existence. No better instance of this could be found than in the case of the kangaroos and their allies, in which, as lower quadrupeds, internal development ceases at a very early period compared with that at which higher quadrupeds are born. The newly born young of a kangaroo, which when full grown stands 6 or 7 feet high, measures about 1 inch in length at birth, and resembles a little red worm much more nearly than a kangaroo. At birth it is transferred to the characteristic pouch of the mother, wherein for weeks it is protected and nourished by the milk secretion. If we consider the effects of growth on such an organism, we may well feel assured that a metamorphosis of very complete kind must be required to transform the imperfect and feeble being just described into the giant quadruped which takes its leap of 20 feet with the utmost ease. So also we find in the development of birds well nigh infinite variety in the stage of perfection at which the young animal is thrown upon its own resources. Of old, naturalists were wont to divide the birds into those which could run about and forage for themselves immediately on leaving the egg, and those which, as mere fledglings, required parental care and attention for a longer or shorter period after bursting the shell. A young chicken is a much more independent being than, say, an infant thrush, and numerous other comparisons might similarly be instituted, with a like result of showing variations in the development of even the animals of a single class. It seems therefore correct to say that the term metamorphosis is one of very considerable latitude, and one admitting, in fact, of no rigid definition at all. At the best, its value is merely relative, and those animals may be regarded as really most metamorphic, so to speak, which leave the egg in an immature state, and which, through circumstances which it is our business to trace in this chapter, have to pass through a definite or well-marked set of changes in form, shape, and often of size also, before assuming the likeness of the parental form. If we reflect that every living being springs from a mere speck of protoplasm, devoid of all structure, which we call germ or egg, and which contains the potentialities of becoming what its parent now is, or if we further consider that from this speck of albumin there is developed in a few days, as in the case of the chicken, a creature rejoicing in the possession of a complex system of bone, muscle, sinew, brain, nerve, and sense organs, we may well feel inclined to consider such a transformation and development as thorough an example of metamorphosis as a far higher development than that of the insect which attracts our notice simply because it is more evident to our eyes. Another striking proof that metamorphosis must be, after all, a comparative term lies in a knowledge of the fact insisted on and illustrated in a previous chapter, namely, that the eggs of all animals, from sponge to man, pass through the same stages up to and including a given point, at which each group branches off, so to speak, on its own pathway towards adult and specific perfection. Thus, why one animal undergoes those changes of form we see in the insect, and why another does not, are circumstances, to come to details, depending firstly on the size of the egg from which it is developed, and concurrently on the amount of nourishment the egg contains, and secondly upon the varying circumstances and surroundings of its life, as well as on the life and history of its race, as temporarily represented by its parent. Thus a large-sized egg with a big yolk will, ceteris paribus, produce an animal in a higher and more perfect stage of development than a small egg in which no provision exists for the nutrition of the embryo. So much, indeed, may safely be predicted of the causes which retard or favor an early escape from the egg. In the latter case, of course, let us bear in mind that the young will not resemble the parent animal, and we naturally expect to behold changes of form or metamorphosis in its further development, and ere it attains to the parent size and likeness. But we must not neglect to note an equally important cause of alteration in form which, acting subsequently to the escape of the immature animal from the egg, will direct its footsteps in different channels, and clothe its form with varied guises. The surroundings of an animal's life necessarily affect that animal, and in time its race, viewing individual and race as consisting each of an adult being and beings. This much is the plainest of plain truths, but it is equally true that surroundings and varying conditions of life must also affect the young stages of animal existence. Even more marked and powerful must be the effect of outward conditions on the young organism whose frame and constitution, not yet fully formed, are infinitely more plastic and facile than those of the adult. All we know of the effects of environments on living beings teaches us this lesson. We know something of the effects of heat and cold, of a change of medium, and of numerous other circumstances which materially alter the development of both animals and plants. Natural history records teem with examples of these facts. A young rosy feather star, Antedon, may be hurried through its larval stage, and may be made to gallop post-haste through its metamorphosis, if it be supplied with pure sea-water. If, on the other hand, such a larva be kept at a low temperature, and in water not frequently changed, and consequently on a more meager dietary, it will delay in its larval progress. Its development may not merely be greatly protracted and prolonged, but it will attain to a higher state of independent development than before. So also with many insect larvae, and so with zoophytes. The effects of varying conditions on the young and developing animal are plainly traceable. It remains for us to discover what light such reflections throw on some well-marked and familiar cases of metamorphosis around us. The insect world teems with examples of metamorphosis at once striking and interesting. It also, however, illustrates a previous remark that in one and the same class we may find great variations in development and metamorphosis. For instance, we may find no metamorphosis at all in some insects. The lice, the bird lice, and the springtails, Thysanura, thus come from the egg resembling in every respect, save in size, the perfect insects. They simply cast or shed their skin at each successive stage of growth, but no change of form is represented in their development. So also with many insects of higher rank. A kind of dayfly, Coleon, is described by Sir John Lubbock as undergoing no fewer than 20 moltings of its skin during its metamorphosis, which is not, however, of marked or distinct character, since the organs of the young animal are simply and gradually changed into those of the adult insect. Even in insects which undergo a much more typical metamorphosis than the dayflies, the gradual conversion of the larval parts into the organs of the adult may be witnessed. A young cricket becomes the adult very gradually, and the days of its infancy are not markedly separated from those of its youth, nor are these latter in turn sharply defined from the period of adult life. Turning, however, to actual details, we find a butterfly, fly, and beetle respectively to exhibit the so-called perfect form of metamorphosis. Each begins life, that is, comes from the egg, after the preliminary stages common to all eggs, as a grub, caterpillar, or larva, which spends the first part of its existence in the guise of a worm, eating voraciously and increasing, as a rule, many times its original size in bulk. Next, this voracious grub settles down and becomes the chrysalis or pupa. Here, quiescence is the order of the day. Sometimes within the larval skin, or it may be, as in butterflies and moths, within a special case or cocoon, the chrysalis passes its existence, which, however quiet and apparently unimportant, externally viewed, is nevertheless marked by a wonderful activity inside. There the elements and nutrient parts of the larva, accumulated during its season of epicurean enjoyment, may be practically broken down and rebuilt to form the body of the perfect insect, as in some flies, or more gradually changed into the adult organs, as in the butterflies. As Sir John Lubbock succinctly puts it, quote, "The change from the caterpillar to the chrysalis, and from this to the butterfly, is in reality less rapid than might at first sight be supposed. The internal organs are metamorphosed very gradually, and even the sudden and striking change in external form, from the chrysalis to the perfect insect, is very deceptive, consisting merely of a throwing off of the outer skin, the drawing aside, as it were, of a curtain, and the revelation of a form which, far from being new, has been in preparation for days, sometimes even for months." Unquote. In the metamorphosis of certain of the flies, for example the flesh flies, the changes are in reality much more sweeping than in the butterflies, although perhaps less apparent than in these brilliant members of the class. The body of the maggot or larval fly contains, when it leaves the egg, a number of curious rounded structures named imaginal discs. Some 12 of these are placed in the young insect's chest region, 4 in each segment, and 2 are situated in the front part of the maggot's body. No change is perceptible in these discs during the caterpillar or larval stage of the fly's life, but when the maggot encloses itself within the last of its skins, which serves it as a chrysalis case or cocoon, the discs begin to undergo a marked development. Each of the lower discs, placed in the insect's chest, develops a leg and half of the segment of the body bearing the leg. The upper discs of the joint give origin to the upper halves of the segment and to the wings or their representatives, and the 2 foremost discs are responsible for the development of the head and mouth parts of the perfect fly. As development proceeds, we find a complete physiological breakdown of the chest and head organs of the maggot to be represented. A literally new creature, as to chest and head, is produced and built up from the imaginal discs, the tail or abdomen of the fly consisting, however, of a mere extension and growth of that of the maggot. There is thus witnessed, in the development of the fly, a much more complete series of changes than in the metamorphosis of a butterfly, and this notwithstanding the fact that the changes undergone by the latter appear to be of more sweeping character than those exhibited by the former insect. Let us bear in mind also the fact, already noted, that the developmental changes in insects may be reduced to a minimum in respect that many lower insects do not undergo any metamorphosis at all. Even in the cockroach, belonging to the Orthoptera, or grasshopper and locust group, an insect familiar enough to warrant its special mention in the present instance, the young possess eyes, feelers, jaws, and legs before they are hatched. They further leave the egg as minute but active insects, whose organs are really molded upon the type of those which the perfect cockroach possesses. The young insect then undergoes 7 moltings or changes of skin. Its first molt occurs when it leaves the egg, and its second takes place about a month afterwards. This second molt being performed, no further shedding of skin takes place until a year afterwards, and as but an annual molt subsequently occurs, the insect does not attain maturity till its 5th summer. Thus, in the cockroach, metamorphosis, in the sense in which that term is used as regards the butterfly, does not occur at all. The male insect, it is true, develops wings at a late stage of development, but there is no chrysalis stage and no quiescence, as in the butterfly or beetle. How then, it may be asked, are the differences between the metamorphoses of insects to be accounted for? On the theory that the development of the individual recapitulates the evolution of the race, it may be asked, do not the facts and differences of metamorphosis in insects seem to present very grave difficulties? There is not that general likeness seen, for instance, in the young of different crustaceans, nor the similarity in development witnessed in the echinoderms or starfish group. These apparent difficulties, however, become greatly lessened or may disappear entirely if we bear in mind the fact, already insisted on, that as adult animals vary and alter, and so evolve new species, so the young and developing forms are even more subject to modification whilst in the process of growth. In other words, let us clearly understand that the changes an animal or plant may undergo are 2 in number. Firstly, there are developmental changes, or those we have been tracing in previous papers, which belong to the animal as part of its inheritance, and which cause it to travel along the line of its ancestry towards the likeness of its parent. Then there are, secondly, changes which must be named adaptive, which arise from the operation of surrounding circumstances, heat, cold, food, etc., and from the action upon the living being of external forces. These latter are changes adapting it to, it may be, new ways and walks of life, differing from those of its parents and ancestors, remodeling its frame in a novel guise. The young insect, in truth, may be described as living between 2 sets of forces or conditions. One set may be named centripetal or center-seeking, for want of a more descriptive term. These are developmental changes which tie it to its type and which cause it to travel along the beaten track of its race. Then there are the centrifugal or adaptive forces, which tend to make its development erratic, which may cause it to fly off at a tangent, so to speak, from its normal way of growth, and which necessarily cause it to differ materially from its type and race. Says Darwin, in speaking of development at large, quote, "Many insects, and especially certain crustaceans, show us what wonderful changes of structure can be effected during development." Unquote. A little later he proceeds to remark that whilst similar organs in the young of different animals, quote, "often have no direct relation to their conditions of existence," unquote, for example, the gill arches of a quadruped, a bird, a frog, and a fish, the case is, quote, "different when an animal, during any part of its embryonic career, is active and has to provide for itself." The period of activity, says Darwin, may come on earlier or later in life, but whenever it comes on, the adaptation of the larva to its conditions of life is just as perfect and as beautiful as in the adult animal. In how important a manner this has acted has recently been well shown by Sir J. Lubbock in his remarks on the close similarity of the larvae of some insects belonging to very different orders, and on the dissimilarity of the larvae of other insects within the same order, according to their habits of life. Owing to such adaptations, continues Mr. Darwin, the similarity of the larvae of allied animals is sometimes greatly obscured, especially when there is a division of labor during the different stages of development, as when the same larva has during one stage to search for food, and during another stage has to search for a place of attachment. Cases can even be given of the larvae of allied species or groups of species differing more from each other than do the adults." Unquote. Now these are weighty words because they sum up the reasons why, admitting a general similarity of early development in insects, we should find so much variety in the later development we name metamorphosis. They direct our attention to the fact that adult life is not the only period when changes in the constitution and form of the living being occur, and they emphasize very clearly the further fact that to changes occurring in the young stages of an animal are due many of the most characteristic and curious details of animal form and growth. If we wish for examples of unlike larvae of insects belonging to the same order, we may find any number of such instances amongst the beetles. Some beetle larvae are footless grubs, others are well provided with legs. Some have feelers, others want feelers, and variations in form are very numerous indeed. Or among the Neuroptera, an order including the dragonflies, dayflies, white ants or termites, and a host of other insects, the larvae differ somewhat. But the pupae or chrysalides are exceedingly varied, some being quiescent, others active, and others again being at first motionless and afterwards moving about. It is not difficult, moreover, to show how very perfectly adapted to varied ways of life different larvae have become. The worm-like form of those larvae which live parasitically in the interior of other animals or in plants may attract our notice as an adaptive feature. Such forms are well represented in the young of the botflies, which pass their existence either within the digestive system of the horse or within the tumors they form on the backs of cattle. Witness, on the other hand, the strong-jawed, weak-legged larvae which burrow in wood, or the well-developed legs of those which feed on leaves and which forage for animal matter. Compare with these features, again, the degradation and modification causing those larvae which are fed by parents or nurses, for example young ants and bees, in the cells of their hives to become fleshy, footless, inactive grubs. Whilst as a feature of highest interest, it may be noted that the bee grubs do possess at one period of development rudiments of legs, which, however, soon disappear. The fact, as Sir J. Lubbock remarks, quote, seems to show, not indeed that the larvae of bees were never hexapod or six-legged, but that bees are descended from ancestors which had hexapod larvae, and that the present apod or footless condition of these larvae is not original, but results from their mode of life, unquote. The changes which have converted bee larvae into footless grubs are, in other words, not developmental, but adaptive. End of section 32, chapter 12, The Evidence from the Life-Histories of Insects, Part 1. Section 33 of Chapters on Evolution by Andrew Wilson. This LibriVox recording is in the public domain. Chapter 12, The Evidence from the Life-Histories of Insects, Part 2. To follow out in detail the full history of insect metamorphosis would be a task lying far beyond the scope or limits of the present chapter, in which other details of varied developments have yet to be noted. The keynote of metamorphosis and its explanation is struck when the great fact of modification of the young, as well as of the adult, becomes patent to us. Anything which may be said further regarding metamorphosis is in reality an enlargement and illustration of this thought. But we may, nevertheless, glance briefly at one or two points in connection with the history of insects by way of rendering clear the probable lines along which the production and evolution of metamorphosis has taken place. We have seen that the changes which an insect undergoes have reference not so much to its future form or adult state as to its more immediate wants and to the exigencies of its life when undergoing development. We have noted likewise that the insect, like every other animal, is developed and exists between two sets of conditions, namely, those which tend to keep it in its ancestral grooves and those which tend to alter its constitution through the influence of new surroundings. Insects are known, further, to pass through every gradation of development, from slight change, limited to the molting of the skin, to that which is illustrated by the dissolution of the larval body and the rebuilding of its frame to form the adult. Is there any information at hand, it may next be asked, which affords us any clue as to the original stock from which the insect type, in all its fullness and variety of form, has been derived? Assuming it to be a probable and consistent view of the case that the mere metamorphosis of insects is a matter which, as already explained, is adaptive and secondary rather than original, what of the parent stock? And what does the study of metamorphosis, closely viewed, teach us concerning that root form? How is it, we may lawfully inquire, that such characteristic features of an insect as its wings and its mouth parts were evolved? It may facilitate our comprehension of these matters if we firstly begin with wings and mouth, and finally direct attention to the probable origin of insects as a whole. There are two main types of mouth in insects, one illustrated by the butterflies and moths, in which all the organs are modified to serve as a suctorial apparatus for drinking up the nectar of flowers, and the other typically represented in the beetles, where we find a high development of jaws adapted for mastication and prehension. Intermediate between the suctorial and the biting mouth, we find that of the bees and wasps, where jaws coexist with a tongue or proboscis. It may be said, however, that there is but one type of insect mouth, all the forms of this apparatus being merely modifications of the one type form. Very curious, however, are some of the changes which the mouth parts undergo in the course of their development. For example, a caterpillar begins life as a biting insect and is provided with powerful jaws, a fact which its ravages on leaves fully endorse. Ultimately, as the butterfly, its mouth is wholly suctorial, its chief organ being the long antlia or proboscis, used for drinking up the flower juices, and in reality corresponding with the second pair of jaws in a beetle. There is a clear aid to our thoughts on this matter when we discover that the varied mouths of insects are thus all really built up on one type. Our difficulty, therefore, is not that of accounting for the origin of new structures, so much as that of saying how one phase of an organ becomes modeled to form another phase of the same type. An acquaintance with the broad facts of natural history study reveals modifications quite as wonderful in other groups of living beings. It is even more curious to find the arm of man, the wing of the bird, the foreleg of the horse, and the wing of the bat built up on the same type, than to discover a change of type in one and the same insect's mouth in the course of development. If we go back to insects in which the mouth parts are simple and possess jaws of elementary pattern, we may as readily conceive of these jaws becoming altered to form suctorial organs as of the same type of limb being modified in one case to walk and in another to fly. The alteration of ways of life and living and changes in food would be sufficient causes for the modification, which, proceeding slowly and gradually, would in time become naturally repeated in the life history of the race. Or further, as Sir John Lubbock suggests, the young insect might have access to or even be compelled to eat different kinds of food at different periods of its existence. Every variation of mouth has a reference, like the form of larva, to the life and food of its possessor. Is there, after all, any great difficulty in conceiving that the varying forces and conditions, which include in their work the production of very different larvae in even a single group of insects, should have likewise altered and transformed the mouth parts of these animals? In truth, alteration of mouth is simply a part of a transformation which becomes the more wonderful as our view of its scope enlarges. Nor does the consideration of the origin of the insect mouth fail to lead us incidentally to discuss the meaning of the pupa or chrysalis stage. Granting, then, says Sir John Lubbock, in speaking of the modification of the biting to form the suctorial mouth, quote, the transition from the one condition to the other, this would no doubt take place contemporaneously with a change of skin. At such times we know that, even when there is no change in form, the softness of the organs temporarily precludes the insect from feeding for a time, as, for instance, in the case of caterpillars. If, however, any considerable change were evolved, this period of fasting must be prolonged and would lead to the existence of a third condition, that of the pupa, intermediate between the two. Since the acquisition of wings is a more conspicuous change than any relating to the mouth, we are apt to associate it with the existence of a pupa state. But the case of the Orthoptera, cricket or grasshoppers, is sufficient proof that the development of wings is perfectly compatible with permanent activity. The necessity for prolonged rest is in reality much more intimately connected with the change in the constitution of the mouth, although in many cases, no doubt, This is accompanied by changes in the legs and in the internal organization, unquote. The same authority expresses the opinion that whilst the biting mouth can be modified to form the suctorial, a change witnessed in every developing moth and butterfly, the originally biting mouth of the beetle could not have been directly modified, contrariwise, to form a sucking apparatus, quote, because the intermediate stages would necessarily be injurious, unquote. More probable is it that both types have sprung from some more primary form of mouth, which, partaking of the character of neither, has been therefore capable of modification in either direction, quote, by gradual change without loss of utility, unquote. That such a form of mouth, united to a body of equally convenient primitiveness, is to be found still represented in the ranks of living insects, we shall shortly discover. Meanwhile, the question of wings awaits a brief notice. The nature of an insect's wing, discussed in reply to the question, "What is it?" throws some light on the question of its origin. The physiology or use of a wing is, of course, to serve as an organ of flight, but the use or function of an organ may be, and often is, a secondary and adaptive matter, and may be very far from revealing the original condition of the structure in question. Authority in matters entomological assures us that the wings, as appendages of the insect's body, are in reality parts of the animal's breathing system. They contain branches of the breathing tubes and expansions of the blood vessels likewise. Hence, says Packard, quote, the aeration of the blood is carried on in the wings, and thus they serve the double purpose of lungs and organs of flight, unquote. But we must note that many insects are absolutely wingless. The lice, springtails, and fleas, and even the plant lice and neuter ants belonging to winged groups are destitute of these organs. No doubt the wingless condition in the latter cases is to be explained on the theory of disuse causing the disappearance of these organs. But the most primitive insects are without wings, and we may therefore reasonably conclude that wings are not original belongings but late developments of the race. Furthermore, many insects of relatively high rank, such as the crickets, grasshoppers, etc., quit the egg without wings, and this although they are extremely active in every respect. A wingless state is on all grounds, including the evidence of development, to be regarded as the original condition of the insect class. We have seen the intimate connection which exists between the wings and the breathing of insects. Of the two functions, breathing is, of course, much more primary and essential to life than flight. Hence we may well conclude that as many insects, especially the most primitive, breathe and live without wings, whilst others develop wings and utilize them for breathing as well as for flight, the breathing function, and not that of flying, was the first use to which the earliest insect wings were put. The first beginnings of wings probably existed as we see the thin skin folds of the water-living young of some insects to exist today, that is, as primitive organs adapted for breathing air from water. One singular little water larva, that of Chloion, one of the Ephemeridae or dayflies, possesses side expansions for breathing, which are moved by muscles, as are the wings, and from what is known of other insect larvae inhabiting water, it seems highly probable that a pair of these flat gills to each joint of the body may have originally been developed. The next stage in the evolution of the wing from this side gill, within which, be it noted, the breathing tubes branch out, would consist in these gills being employed as agents of aquatic flight, that is, flight under water. In time, the hinder gills would alone be devoted to breathing, whilst those of the middle of the body, being the most advantageously placed for locomotion, would become the wings. Probably the first insect wings were used to propel their possessors under water. Such a state of matters is now seen in Polynema natans, which Sir John Lubbock discovered in 1862. Thereafter, to movements under water would succeed movements on the surface, and as the muscular developments progressed, the beginnings of aerial flight would be simply a matter of time. The late acquirement of wings in the developing insect of today is thus a fact not without its due significance. Such an event clearly enough shows us, firstly, that flight was a power superadded to insect locomotion long after the evolution of the race from some primitive wingless type, and secondly, that wing power was evolved through the intermediate stage of gills, still represented in the water-living larvae of our dayflies and their near kith and kin. As Gegenbauer remarks, the wings correspond in nature with the gill processes just described, quote, for they do not only agree with them in origin, but also in their connection with the body and structure. It is quite clear, the same authority continues, that we must suppose that the wings did not arise as such, but were developed from organs which had another function, such as the tracheal gills. I mean to say that such a supposition is necessary, for we cannot imagine that the wings functioned or acted as such in the lower stages of their development, and that they could have been developed by having such a function." Unquote. That this speculation is a highly probable one is proved by the curious fact that one insect, Pteronarcis regalis, belonging to the Orthoptera inhabiting damp places, retains its gill-bearing organs throughout life. The mere possibility of the aquatic origin of insects is therefore placed beyond doubt by such an observation, whilst the fact that Pteronarcis belongs to the ancient order Orthoptera shows its alliance with a primitive type of the insect class. The consideration of the probable original or type form of the insect class now demands attention. The tyro in natural history knows that insects, along with spiders and scorpions, centipedes and crustaceans, form a great division of the animal world, to which the name of arthropoda, jointed-legged animals, is given. The latter group in its turn forms a division of the great articulate type, of which group the possession of a jointed body, seen equally well in the insect's body, in the centipede's frame, or in the lobster's tail, is a chief characteristic. Now, the origin of the arthropoda from some lower and worm-like stock is not a matter which involves any very great draught upon the speculative faculty. From some such stock the tribes of spiders, insects, crustaceans, and centipedes have probably originated. There exists, indeed, a curious animal known as Peripatus, which is in many respects entitled to be considered as a primitive arthropod. From some such form as Peripatus, it is not improbable that at least the insects, centipedes, and spiders were evolved. We have discussed in a previous chapter the nature of the form which has probably, through its evolution and development, given origin to the crustacean hosts and legions. This form is the Nauplius, which in the development of highest and lowest crustaceans alike reappears as the root and stock of the class, and whose modifications form the puzzles of the philosophical naturalist of modern times. Now, what is so clear in the case of the Crustacea is well nigh as patent in the history of insects. We certainly do possess in existing groups of insects forms which appear to fulfill the conditions incidental to the purpose of serving as a generalized type from which insect evolution may have taken place. Such groups are those known as the Thysanura, or tuft-tailed insects, and the Columbola of Lubbock, both of which orders may be found on examination to present us with the natural rootstock of higher insects. A brief inquiry into the characters of these latter insects may appropriately bring this chapter to a close. Professor Huxley, in a recent Manual of Comparative Anatomy, speaks of the cockroach as an insect without metamorphosis, a fact already noticed, and remarks upon the obvious difference which exists between such a form as a butterfly with its resting chrysalis and the young cockroach active throughout its whole development. It is obvious, continues Huxley, quote, that a metamorphosis in this sense, for example the butterfly or moth, is a secondary complication superinduced upon the direct and gradual process of development exhibited by such insects as the cockroach. Unquote. It is also laid down as an axiom of zoology that insects which, like butterflies, undergo a complete metamorphosis are more differentiated and better specialized, in a word, are the products of a higher phase of evolution, than those which undergo no metamorphosis. So also we are duly warned that insects, quote, which never possess wings are less differentiated or more embryonic than those which are winged. And finally, insects with the parts of the mouth in the condition of ordinary gnathites or jaws are less differentiated than those in which such gnathites are changed in form and function or become confluent. Unquote. Now, on this view of matters, a butterfly is bound to be regarded, as we have seen on the grounds of its development, as a highly modified insect, far removed from the primitive type. On the other hand, quote, the insects which, in this view of their morphological relatives, occupy the lowest position in the group are the Columbola and Thysanura." Unquote. To these we may perhaps add the true lice and bird lice, Malophaga, because these also undergo no metamorphosis and possess no wings. What, then, are these Columbola and Thysanura, in whose personnel and development we may expect to find the primitive form of the insect type? The Thysanura, of which the Lepisma and Campodia are good examples, are small insects living in dark situations, such as amongst damp moss and under stones. The body is either hairy or, as in the Lepisma, covered with minute scales, which constitute objects used for testing the defining powers of microscopes. On the whole, the Thysanura very closely resemble the young of the cockroach. The tail or abdomen is composed of some 10 segments and bears paired appendages from 7 to 9 in number. They possess breathing tubes, but as already remarked, want wings and exhibit no metamorphosis. The Columbola differ from the preceding group in possessing a tail consisting of 6 joints only, and a curious tube or sucker, by the viscid secretion of which they attach themselves to fixed objects. Their popular name of springtails, derived from the presence of appendages formed on a spring and catch principle, and by means of which they are enabled to take leaps of considerable extent, indicates another peculiarity of the group. Only in one genus of the Columbola, likewise, are breathing tubes found. The jaws or gnathites in Campodia and Columbola are not very markedly developed. As Sir J. Lubbock remarks, the jaws, quote, "are far from strong, but still have some freedom of motion, and can be used for biting and chewing soft substances." Unquote. Of these lower insects, the genus Campodia is particularly interesting, inasmuch as it seems to combine in its person all the primitive characters which give to its neighbors their extreme interest in the eyes of naturalists. Campodia, which occurs in loose damp earth, has an elongated cylindrical body, long and many-jointed antennae, with paired appendages on the first 7 joints of its tail, and long tail appendages likewise. Now, if we compare the young or larva of Campodia with the adult, we find little or no difference save in size. Its whole organization reminds us forcibly of the young stage in such insects as the cockroaches and other Orthoptera, whilst there are larvae in other groups of insects to which Campodia and its neighbors bear a close resemblance. Furthermore, the larva of the dayfly, Colion, which possesses the gill appendages already referred to, is exceedingly like this Campodia, whose mouth parts appear equally capable of further development to form the jaws of the beetle, or of modification to become the suctorial apparatus of the butterfly. Thus, on all grounds on which it is possible or necessary to look for resemblances between Campodia and the young of higher insects, such likenesses are discoverable, and the conclusion is thus rendered highly probable that existing insects have been evolved from an ancient Campodia-like stock, that is, from an animal form with a jointed body, 3 pairs of legs, weak mouth parts, 1 pair of feelers, and a tail provided with jointed appendages. Hence a mental forecast is prepared to see an insect like the young Colion, or the water larvae already described, with their side gills into winged and higher races. Or in another direction, and through less modification perhaps, we may in our mind's eye behold Campodia growing in time into the stock whence the Orthoptera, our existing crickets, grasshoppers, and locusts, themselves a primitive group of insects, have sprung. Backwards, on the other hand, in the scale, retrograding from Campodia, we may even conceive of the stock from which that insect itself has sprung. Campodia within the egg must pass through the stages common to all animals at a like stage of development. There is a stage in the arthropod type when the young of the insect or crustacean is little else than a footless, imperfectly developed worm. There is even a worm-like larva of an insect allied to the gnats, which corresponds to such a description. And such low insect larvae become in turn obviously related in form to certain low creatures allied to the worm kith and kin. One of these low forms is Lindia. This legless organism is related to the well-known bear animalcules and rotifers or wheel animalcules. Its jaws resemble those of the larval flies. It has a ringed body, and in other respects exhibits a close likeness to the young of many insects. Possibly, therefore, in some such primitive route common to a whole host of animals, we may find the dim, ill-defined starting point whence, led towards Parapatus and by Campodia, the insect tribes have grown into the brilliance and aerial grace which mark their ranks today. It may not be unprofitable at the close of our investigation into insect history to remind ourselves of the great problem which their development has lent its aid in part to solve. At the risk of apparently unnecessary repetition, let us keep in view that every such history, however its individual terms are to be accounted for, forms a link of greater or less importance in demonstrating the great law of evolution, modification, and adaptation as the true method whereby nature has wrought out the endless variety of the children of life. Especially useful and important, moreover, is the history of the insect as illustrating the changes which the adaptation and modification of the young form may effect in the history of a species. So far from the chrysalis or pupa being a stage in the ancestry of the insects, we have seen that it represents merely a secondary and acquired phase of their development. As Fritz Müller has succinctly formulated it, quote, "The historical record preserved in developmental history is gradually effaced as the development strikes into a constantly straighter course from the egg to the perfect animal, and it is frequently sophisticated by the struggle for existence which the free-living larvae have to undergo." Unquote. These words sum up the reason why insects in their metamorphoses exhibit all gradations and shades, from mere molting of skin to complete change of form through a chrysalis state. Primarily, they undergo a metamorphosis because they happen to leave the egg at a relatively early period of development. But they share metamorphosis, using the word in the broad sense, with every other living being. It is this plainly discerned series of changes which has chiefly given to the study of entomology its fascination in the past. One may, however, well be regarded as enunciating a veritable truth when it is stated that the new light which evolution throws on the why and how a butterfly develops and a Campodia remains inert is likely to invest insects, and indeed all other forms of life, with an interest far surpassing that which past years could have imagined or conceived. End of section 33, chapter 12, The Evidence from the Life-Histories of Insects, part 2. Section 34 of Chapters on Evolution by Andrew Wilson. This LibriVox recording is in the public domain. Chapter 13. The Evidence from the Constitution of Colonial or Compound Animals. Part 1. Amongst the many aspects in which the biologist is accustomed to view the universe of life, few possess a greater interest than that which deals with the nature of animal and plant personality, and with the structural philosophy of the living frame. It is not sufficient for the due investigation of living structures that the forms of animals and plants be compared, and their more obvious differences and peculiarities noted and recorded in scientific annals. Such details and such procedure suffice perfectly for the ordinary run and course of biological work, and form, no doubt, the source of the everyday knowledge on which natural history science grows and progresses. But a higher era of scientific thought intervenes when philosophy, in its search after relationships and causes, steps forward to correlate and utilize the knowledge observation has acquired. The higher questions of cause and origin are not solved by observation alone. It requires and demands the power of placing facts in appropriate light and shade ere the mutual relations of these facts can be determined, and before their place in the systema naturae can be definitely ascertained. Judged by this criterion and standard, there are some topics of biology which altogether belong to the region of the abstract and the transcendental. Patient industry may discover, for instance, that a crayfish within the egg repeats, as a stage in its development, the likeness of a form represented today by the adult state of some lower crustacean. But it requires philosophy of a transcendental kind to see what that fact means, and what such a discovery implies to the universe of life around. One may perfectly appreciate by ordinary observation that a horse walks on the single toe of each foot, and that its two splint bones represent useless rudiments of other two toes. but it is through an exercise of abstract science alone that we can form the concept of a single-toed horse having arisen from a three-toed one, and from the latter phase of development extend a like thought to that of other living beings. The applications of philosophy to the facts of nature remind one strongly of the most singular and mysterious work of that nature in the production of the living thing itself. In the performance of that function, we require a certain quantity of the substance called formative material by the learned in biology and protoplasm by the single-minded amongst us. This material contains all that is required for the formation of the living frame insofar as the material of that frame is concerned. But in protoplasm alone, we do not find all that is demanded for the growth of the new being. We require likewise activity of some kind, potential or real, chemical, physical, or vital, or all three combined, and we depend upon this activity for the combination of the elements of our germ and for the power whereby that germ will in time blossom into full fruition. So is it, in truth, with the application of knowledge and with the evolution of the wisdom which arranges our knowledge in its due array. The knowledge we gain is, after all, in itself pure material, on which the potential power of philosophy must exert its influence ere the results of seeking and finding wisdom be fully appreciated. The evolution of a natural fact or set of facts to take its place in the array of knowledge we name a science is therefore matter of higher development than that which merely discovers the facts themselves. Only when philosophy has touched the inert mass of detail does the harmonious and arranged system spring into view, with its power of truly adding to man's knowledge of the universe around and overhead. Only when the search for causation has begun can our intellectual gains be fully appreciated in our labor of untwisting all the chains that tie the hidden soul of harmony. Such a topic as presents itself to view in the individuality of animals belongs, it may be, with all truth affirmed, to the domain of the philosophy which applies knowledge rather than to the sphere of mere fact and observation itself. This declaration might sufficiently prejudice the subject in the eyes of readers who might be given to view with suspicion any opinion which apparently lowered fact in the scale of credence. But the philosophy we eulogize bases its existence on the facts we value. It is the mint stamp of knowledge, which impresses fact with its popular and received value, inasmuch as, without such impress, the fact itself, however valuable, fails to relate itself to its neighbor truths. Hence, if in the present chapter we may venture somewhat within the domain of transcendentalism, it may readily be shown that from the sober basis of facts all our philosophy in reality takes origin. By way of at once illustrating this latter proposition, as well as of laying the foundation stone of our present study, we may enter upon a recital of the facts of individuality as represented in the living series around us. A superficial acquaintance with the facts of natural history serves to demonstrate the truth of the axiom that every animal originates, directly or indirectly, from that reproductive body we term an ovum or egg. As the result of the development of that egg, the animal body becomes the adult, and of the plant the same truth holds good. The seed or germ undergoing development and passing through stages which are, as a rule, of well-defined nature, at last appears before us as the perfect plant, which in its turn will produce blossom and fruit, and will finally lead us back once more to the seed and germ. One marked and very obvious difference between high animals and low animals is found to exist in the different results to which development leads. The lower animal's growth ceases, and its adult condition is attained at a stage when the development of the higher being has barely begun. It takes but little trouble on nature's part, so to speak, to convert the matter of life of a low animal or plant into a form like itself. On the other hand, the development of a higher animal means time and trouble, to use a familiar expression, and entails the elaboration and building of a complex body from that which is invariably in its first stages uniform and simple in structure. Such an animal form as a Gregarina, for instance, presents us with a good example of that simplicity of development and that primitiveness of personality which marks the lower fields of animal life. A Gregarina is a minute speck of protoplasm found inhabiting the digestive canal of worms, insects, and crustaceans. as an internal parasite. Each Gregorina lives what may be described as the simplest form of existence. Existing in the digestive system of its host, it literally lies bathed amidst the nutriment which that host is elaborating for the repair of its own tissues. Possessing no traces of any of the organs belonging to higher animal existence, the Gregorina lives by the absorption of the digestive fluids of its host, and save for the slow contractions which are sometimes seen to pass in waves along the surface of its body, no movements can be observed whereby its animality might be popularly confirmed. The course of Gregorina development is by no means complex. The body itself, in lieu of an egg or germ, will sooner or later become of globular shape. The little solid body or nucleus, seen normally in its interior, will vanish by a kind of physiological necromancy, and the body substance itself will break up and divide into spindle-shaped masses for which the thickened rim or margin of the body forms a covering. Then this globular body margin ruptures. The little spindles of protoplasm escape therefrom, and finally each develops, with but little change, into a Gregorina like that from which it was derived. Now, such a life history as this is instructive, especially when viewed from the standpoint of animal individuality. The single Gregorina is seen to break up into numerous other Gregorini, each of which repeats at first the single state, and then the process of division into particles which characterized its parent. Each Gregorina, then, may in natural history language be named a persona or person, that is to say, it is a single or individual animal, representing in itself, even as does each of the higher animals, a defined and component element of the animal world. A like remark might be made of many other lower forms of animal life. An amoeba, which differs from a Gregorina chiefly in that it possesses an active power of locomotion by pushing out its body substance into long processes, is likewise a single individual animal, which represents, as an oyster or a bird does, a well-defined unit quantity in the sum total of the living series. There is, however, one important epoch in the life of both Gregorina and amoeba, when each organism, for both exhibit essentially the same course of development, shows a tendency to lose its individuality in the division of its body to form other individuals. At one stage in its development, namely when filled with the miniature spindles or protoplasmic particles into which it has divided itself, the Gregorina or amoeba in reality becomes a colony or aggregation of beings. But such a tendency is at the most transitory, and the temporary colony speedily resolves itself into a diffused and separated mass of young organisms whose individuality, and indeed whose whole existence, is due to the destruction of those of their parent. In another sense, the amoeba may occasionally show this tendency to lose its single and defined individuality in that of the compound colony. For occasionally particles or offshoots of the amoeba's protoplasmic body detach themselves therefrom, and pass away like precocious emigrants from the parent frame to assume all the functions of amoebae on their own account. In this way, and through the exercise of the simplest reproductive process we know of, namely that of fission or simple division of an animal's body into two or more new beings, the amoeba body converts itself from a single individual into a mother colony, with offshoots and emigrants seeking a life and existence of their own. And last of all, in the Gregorina itself, we may find certain important variations in structure which seem to threaten the destruction of the individualism of its body, and to merge the individual in the crowd. For we know not merely of Gregorini, which consist apparently of but one mass of protoplasm, as already described, but of others which exhibit a division of body into two or even three compartments. What the significance of this tendency to division or segregation may be is yet matter of conjecture, but at first sight its meaning would seem to foreshadow the same destruction of individual constitution which in their development these organisms unquestionably exhibit. Even in the lowest animals, each consisting of a minute mass of protoplasm, there is thus observed a tendency at some period or other of their life history to depart from the single state and by division, or as it is named, segregation of their substance, to form a colonial or compound organization. But even in the lower confines of animal life, which harbor the amoebae and Gregorini as typical tenants, are represented states and phases of organization which are purely and typically colonial. Thus, that low form of life known as Mixodictyum normally exists as a collection of protoplasmic particles, such as would be exactly imitated if a number of amoebae banded and fused themselves together. It is equally interesting to note that the vast majority of the foraminifera, or chalk animalcules, are to be regarded as exhibiting a compound constitution. For in these animalcules, which are as a rule of compound nature, the growth of new divisions of the shell takes place by a process of budding, and through the production of new protoplasmic units, which remain organically connected with the original mass. Nor are the lowest plants to be left out of consideration in this recital of primitive colony making. The cryptogamic botanist well knows certain green specks of microscopic size, each called Chlamydomonas, which swim freely in fresh waters by means of two long cilia or miniature eyelashes projecting from one extremity of the body. Now there exist in stagnant waters certain other curious bodies, long known as globe animalcules, before they were ascertained to be lower plants. Each of these bodies is scientifically named a volvox, and appears to consist of a hollow globe or sphere, covered with innumerable little specks of bright green, and swimming freely through the water by the waving action of the fine cilia which fringe its body. More minutely examined, this rolling globe is found to consist of a collection of little green bodies, each of which, in all essential details, exactly resembles a single Chlamydomonas. The filaments fringing the volvox are in reality pairs of cilia like those of Chlamydomonas, and are attached to the little green bodies aforesaid. Thus volvox, so far from being an animal, is firstly a rootless lower plant, and secondly, so far from being one plant, volvox is in reality a colony of the lowest members of the vegetable world. There are many other algae, or lowest plants, which resemble volvox in their compound nature, and thus the beginnings of plant life appear to present us with a tendency towards colonization, similar to that which faces us on the threshold of the other series of living beings. In the curious group of sponges, we may find our next convenient halting place in our researches into animal individuality and its variations. From forming the bête noire of the naturalist of former years, who was troubled in his mind as to the animal or plant nature of sponges, to occupying a singular and anomalous position in the animal classifications of today, this group of organisms has attained a well-merited celebrity. The living parts of a sponge, that is to say, the parts which form and make the sponge framework, and which alone concern us in our present investigation, consist of masses of protoplasm, which are in their way strictly comparable to the minute bodies or cells of which our own tissues are built up. A sponge, as to its living parts, is a mass of protoplasmic cells, quote, some of which, as Huxley puts it, have all the characters of amoebae, while others are no less similar to monads, unquote. These latter being microscopic masses of protoplasm furnished, like Chlamydomonas, with two waving cilia. The comparison of a sponge to a kind of submarine Venice, with its canals, along the banks of which the inhabitants, or masses of protoplasm, reside, and through which flow the water currents bringing particles of nourishment to these denizens, is therefore seen to be fully justifiable in one sense. Still more justifiable and appropriate would such a metaphor be could we prove that the sponge was in reality what the simile indicates, namely, a colony of animals, seeing that the comparison of the sponge to the Adriatic capital derives its whole force from the assumption that its personality, like that of the city, is compound, and not simple and single, like that of the element or unit. As we shall hereafter see more plainly, the sponge must be judged, like every other living being, not by its appearance or by what it simulates, but by what it originated from. As an apparent collection of organisms, it might well be regarded as a veritable colony. On other grounds, the sponge might appear as rightfully entitled to be considered as single and undivided an animal unit as a man. The grounds on which these opinions are based need not now be specified, but the history of how a sponge grows finds its appropriate place at this stage of our inquiry. The most typical sponges, as already shown, grow each from an egg, which passes through characteristic stages of development, and finally becomes a cup-shaped body possessing a double wall, the cavity of the cup opening outwardly by a distinct mouth. Then pores or openings are formed in the wall of this cup, placing its interior in a new fashion in communication with the outside world. The outer wall of the cup and the inner wall likewise consist of cells, and those of the inner wall finally come to possess cilia, which by their constant motion cause currents of water to flow into the inside of the cup through the pores and outwards by its mouth. The nourishment of a sponge is subserved by these water currents, bringing food and oxygen to its living cells, and the simple or cup-shaped sponges, of which many species are known, exhibit a history resembling that of which the outlines have just been sketched. The horny sponges, the skeletons of certain species of which we use in our domiciles, may and do develop into organisms of a more complex character than the cup sponges present, and they may also originate from buds as well as from eggs. The common green freshwater Spongilla, found growing on the sides of canal locks and in similar situations, illustrates the former method of development. This species propagates its kind by veritable buds, whilst it also produces eggs. And another curious fact, possessing a significant bearing on the individuality of the sponges, consists in the observation that when two spongillae are placed in contact, they merge together into one. They may also be divided artificially or may separate spontaneously into two or more organisms, each of which will lead an independent existence. The sponges, then, may be hereafter referred to as a group of animals which, whilst originating from eggs, as do higher beings, yet retain much of that tendency to segregation and separation into distinct and elementary parts, which we may reasonably maintain is probably a primitive and fundamental character of all living beings. Nearly allied to the sponges are the little freshwater polyps named hydrae, and the marine plant-like organisms familiarly known as zoophytes. Here we at once enter the domain of animal colonies, and find intensified and illustrated in the plainest fashion those tendencies towards division and segregation of body which, at the best, are but dimly marked in lower organisms. The hydra, existing as a little green tubular body, attached by one extremity to a water weed, and exhibiting at the free end a mouth and tentacles, at certain seasons exhibits a growth of small projections on its sides. As these projections increase in size, they grow into the likeness of young hydrae, each developing a mouth and tentacles, and possessing, so long as they adhere to the parent body, free communication with the interior of the latter. These budded hydrae may in their turn produce buds, and a veritable genealogical tree may thus be viewed, in that 3 generations of polyps remain connected as they were produced by the parent stem. The hydra thus converts itself normally into a compound colony through this process of budding. But this state of matters is, at the most, transitory and temporary in hydra existence. The budded individuals, sooner or later, break contact with the parent body, and pass to seek a new lodgment and to begin life on their own account, leaving the parent single as before, but connected, as we shall presently note, to the free offspring by ties which our transcendental philosophy makes clear and plain. It may lastly be remarked that, in respect of structural constitution, the closest similarity exists between a cup sponge and a hydra. Both possess tubular bodies, and both consist of 2 cellular layers. Modern zoology has emphasized this likeness by placing the sponges in the same great group, Coelenterata, which contains the hydra and zoophytes. It is conceivable enough, indeed, that a hydra is simply a specialized sponge form possessing its compound and colonial nature somewhat disguised beneath an apparently single personality. The constitution of a zoophyte is mere matter of repetition after the recital of the hydra's peculiarities. The plant-like sertularian or sea fur, which we dredge by the hundred, growing on oyster shells, or the flustra or sea mat of higher organization than the sea furs, but presenting likewise the aspect of a marine plant, present us each with a veritable colony of more or less similar beings, united in the bonds of close relationship. Thus the sea fir, as the type of the true zoophyte, bears on its branches hundreds of little cups, each of which contains an animal strictly corresponding in structure to a hydra. This multitude of animal bodies is bound together in intimate union, The stem and branches are hollow, and each little mouth and body, digesting the food its tentacles have captured, transmits that food to swell the general stream of nutriment circulating through the tree-like fabric. Thus we find the principle of cooperation herein illustrated in plainest guise. Each little animal derives its own share of nutriment from the general store it has helped to manufacture, and the exercise of the principle in question is all the more perfect in that its practice is free from those petty jealousies and personal inducements to infringe the duty of equal and harmonious work which usually beset the cooperative societies of higher existence. The remaining points which call for notice in the history of the zoophyte may be shortly summed up. The little members of the colony are continually dying off as a result of their life work, but their place is supplied and the colonial loss repaired by the production of new buds. As leaves fall from a tree and are replaced by the growth of new buds, so the zoophyte units wither, fall, and in like fashion are represented anew in the constitution of the organism. Then, lastly, the origin of the zoophyte in an egg is worthy of note. Each zoophyte originally springs from an egg, which, passing through the changes common to the early development of all ova, produces an embryo which settles down and attaches itself to some fixed object. This first embryo next assumes the likeness of a single little hydra-like unit of the zoophyte colony. Then the process of budding commences. Bud after bud is produced, each growing into the likeness of the primary one, and all adhering together as parts of a connected organism, until we find reproduced before our eyes the tree-like form with which our research began. Thus a hydra and a zoophyte are very nearly allied, the chief difference between these organisms consisting in the fact that, whilst the buds remain permanently connected together in the latter, they are intended to seek an independent existence in the former. True, there are buds produced by the zoophyte which in many cases detach themselves and swim freely in the sea under the guise of jellyfishes, and which, apart from the zoophyte, mature the eggs from which new generations of these plant-like animals will spring. But these floating jellyfishes, despite their freedom, are in reality buds of the zoophyte. They are connected by all the ties of blood relationship with their plant-like parent, and are essential parts of the zoophyte colony, even when separated from the parent organisms by many leagues of sea. End of Section 34, Chapter 13, Evidence from Colonial or Compound Animals, Part 1. Section 35 of Chapters on Evolution by Andrew Wilson. This LibriVox recording is in the public domain. Chapter 13, The Evidence from the Constitution of Colonial or Compound Animals, Part 2. In all zoophytes, the component units of the colony belong to one type. Whatever their function, they are modeled on the type of the hydra, and on that of the ordinary nutritive members of these animal trees. Even the jellyfish buds just mentioned are but modifications of the hydra type. This interesting and important feature in their history is proved by the fact that, when their generative functions have been discharged, they may revert to the form of the nutritive members of the colony. We know, lastly, of cases in which a zoophyte colony may number no fewer than 7 apparently different types of members. These units, notwithstanding the diverse functions they perform, exhibiting a fundamental agreement in type and structure. There is seen, therefore, a close parallelism between the repetition and modification of parts in the colonial zoophytes, and the vegetative repetition of the leaves and buds of the tree. The flustras or sea mats illustrate a slightly different phase of colonial relationship in animals from that presented by the zoophytes. We have seen that each member of the zoophyte colony exists in intimate structural relationship and connection with every other unit of the compound organism. But in the sea mats, each of which presents us with the appearance of a piece of pale brown seaweed, bearing on either side its hundreds of little cells, each containing a little tenant, the individual animals of the colony do not communicate with each other. On the contrary, each member of the sea mat colony is perfectly distinct from all its neighbors, and lives enclosed in its separate domicile. But for the union of its cell wall with the walls of other cells, each little sea mat unit is a thoroughly independent being, and even the so-called colonial nervous system, which was long believed to connect the members of the fraternity in a common bond of sensitiveness, has been proved to be non-existent. It is highly interesting, therefore, to find that compound animals may, like the zoophytes, possess their individual or component units in close structural harmony and relationship, or may, on the other hand, like the sea mats, exhibit a collection of animals, each of which is thoroughly independent of its neighbors. That such differences have not originated in any haphazard fashion, but that they are a veritable result of the tendencies of development, is readily enough proved. For whilst each member of the zoophyte stock is in free and full nutritive cooperation with its neighbors, each CMAT unit preserves within its own cell not merely a perfect digestive apparatus, but a nervous system and reproductive or egg-producing organs as well. The independence of the CMAT's members has been accompanied by the development of a much higher organization than is found in the interdependent zoophyte units, although, of course, such a statement of fact still leaves the origin and cause of the independence of the higher CMAT units an open question. But in its manner of growth, the latter colony resembles the zoophyte. Each unit has the power of adding to the colony by the process of budding already described, whilst each member of the colony possesses, likewise, the power of giving origin to eggs. Each egg, undergoing its full development, produces first one primitive unit, and thereafter and from this unit develops, by budding, a whole colony, with its hundreds of component and similar beings. There exist in the ranks of that curious class of beings, the internal parasites, certain interesting examples of the compound animal form. A tapeworm, for instance, inhabiting the digestive tract of some warm-blooded quadrupeds, and attaining a length, it may be, of many yards, consists of a very minute head, a slender neck, and many hundreds of so-called joints. At first sight, these joints might be regarded as resembling in their nature those of the ordinary worms, and as therefore possessing no distinct individuality on their own account, or separate from that of the organism of which they form part. But the examination of the joint of a tapeworm shows us that in reality it preserves a separate and apparent individuality of its own. In other words, it is not merely a part of one animal in the sense that the joint of a backbone is part of a fish or bird. It corresponds, on the contrary, with a member of the zoophyte or CMAT colony, in that it represents a highly specialized and individualized unit of an organism, that organism being of compound nature. Each joint of the tapeworm contains a complete set of egg-producing organs and presents other indications of its semi-independent character and constitution. Connected to its neighboring joints by water vessels as well as by nerve cords, the joint is in intimate union with the other units of the colony, but it is nevertheless a distinct unit after all, and the tapeworm is not a single animal, but, like the CMAT and zoophyte, a colonial organism. Amongst other and true worms, however, we find curious instances of development which, in our consideration of the origin of the conditions we are studying, may serve to elicit some valuable hints concerning the causation of colonies at large. The little river worms, known as the Naididae, occasionally exemplify certain peculiar modes of reproduction which deserve careful study. A naus may be seen to exhibit a slight constriction towards the posterior part of its body. As this constriction deepens, a new head, eyes, and tentacles are seen to be formed at the spot in question, and a second naus is thus viewed budding from the hinder extremity of the original individual. This new being, produced thus by the division of the parent body, sooner or later becomes detached therefrom and seeks an independent existence. Cases have been observed in which as many as 6 new individuals have been produced from a single naus. In Serhatula, another worm genus, Müller relates that he found 3 new individuals adherent in one length. The mother, he remarks, quote, had 30 pedate segments. The youngest daughter, or that nearest the mother, had 11, but the head was not yet developed. The most remote had 17 rings, with both head and eyes, and, moreover, the tail of the mother. The middle one had 17 segments and a head. Unquote. It is matter for remark that no egg-producing organs exist in the new individuals thus budded, which may therefore be named neuters, like the workers among the bees. The last formed individual, however, in the naus, develops reproductive organs, and thus the continuance of the species in time is duly provided for. In connection with the production of like parts by budding, a process known as that of vegetative repetition of parts, and producing what is known as the serial homology of animals, it is interesting to note that the 20 joints or so of which an anima like the lobster is composed are constructed irrespective of size or function upon one and the same type. The same remark holds good of an insect, of a centipede, of a spider, or other articulated animal. Very striking is it to find that a lobster's feelers really correspond in nature with its legs, that its eye stalks agree with part of the appendages of its tail joints, and that its jaws are simply the feet of the head, so to speak, modified for chewing. These varied organs arise from a common type, just as the joints which bear them exhibit a singular uniformity of structure. Hence a lobster or other articulate animal gains the best possible title to be named colonial, in that it is not merely composed of visible units, but also in that these units are modifications of a common and single plan. In connection with the curious phases of worm growth observed in the Naiadides, we may note that the individuals of the centipede class increase in size and add new segments to their bodies in a somewhat similar fashion. When a young centipede or galleyworm, Julis, is attaining its full growth, new joints are seen to bud out between the last segment but one, and the joints in front thereof, so that the last formed joints in a young centipede are placed towards its tail extremity. If we could imagine that some of these last formed segments developed ahead and separated themselves from the parent frame as a new being, we should possess an exact imitation of the process whereby the young naus originates from its parent form. An interesting biological speculation has arisen in connection with the personality of those familiar animals, the starfishes. Here we find a central body or disc with, in the common species, 5 rays or arms, containing each an exactly similar arrangement of the organs of the body diverging therefrom. Haeckel's ingenious speculation that, quote, each arm of the starfish essentially corresponds in its organization with an articulated worm, unquote, is objected to by some naturalists, and amongst others by Huxley, who agrees that the starfish, or Echinus, may have arisen from a worm stock, but argues that both the starfish and sea urchins owe to secondary modification their characteristic form. Haeckel, however, is supported by authority so eminent as Gegenbauer, who remarks that, quote, there is a certain amount of independent organization in each arm of a starfish. Its organs have exactly the same position as the homologous organs of an annulate worm. If, then, we compare each of the budding arms with a worm-like organism, we must regard the starfish developed by this process of gemmation as corresponding to a multiple of such organisms. And further, we must recognize in this phenomenon the same process of gemmation or budding as that which takes place in other lower animals, for example, in the compound ascidians or sea squirts. It is a process, says Gegenbauer, in which several separate animals are simultaneously budded off. The process does not go on till these animals are completely separated, but stops in such a way as to keep them connected together as an individual of higher order, unquote. We know, as just remarked, of allied cases amongst the sea squirts where several beings are budded in star-shaped fashion, Botrytis, to form a colony. And when we reflect that, as every sea beach shows, a starfish may be deprived of all of its arms, and as one arm may not merely live an independent existence, but will in time reproduce the other 4, Haeckel's idea that a starfish is really a collection of worm-like beings is seen to be so far supported by comparative anatomy and by the analogies of development as well. The list of animal classes in which a colonial constitution is developed may appropriately enough be concluded with the brief recital of the process whereby the aphides or plant lice which devastate our plants and the bees themselves propagate their race, the latter forming social colonies which in their essential nature may be deemed analogous to the zoophyte stocks of lower life. The single and undivided personality of a bee or an aphis would at first sight seem to admit of no question. Each presents itself to view as an active being possessing no structural connections with neighbor organisms and evincing all the apparent marks and characters of an ordinary individual. But our philosophy relies, as already remarked, more on the determination of what an organism has arisen from than upon what its apparent constitution may be. Hence, the consideration of a bee's origin contains the answer to the question of its true nature. In the reproduction of the bee race, certain of the eggs are impregnated or fertilized while the others are allowed to develop without the performance of this process, rightly deemed of essential nature to the propagation of both animals and plants. Now, those eggs of a queen bee which she lays in an unfertilized condition invariably develop into drones or male bees, whilst the fertilized eggs become females or queens or neuters, the latter being merely imperfect females on whom devolves the whole work of the hive. In the plant lice, the eggs normally produced by both sexes in the autumn lie dormant all the winter, and then give rise to wingless female aphides alone. These latter produce in viviparous fashion a winged or wingless progeny, which in turn repeat the fertility of their parents. As Huxley remarks, quote, "The number of successive viviparous broods thus produced has no certain limit, but, so far as our present knowledge goes, is controlled only by temperature and the supply of food. Aphides kept in a warm room and well supplied with nourishment have continued to propagate viviparously for 4 years." Unquote. Now, close research has disclosed other cases of this apparent violation of the ordinary rules of reproduction in the animal world. We know that in certain sawflies, some of the female insects will, of themselves, lay unfertilized eggs, which develop into male sawflies. In some insects, Kermes, Coccus, no males have been discovered. There are also certain caterpillar-like females among the butterflies and moths, for example, Psyche and Solenobia, which lay unfertilized eggs, giving origin to female insects like themselves, whilst from fertilized eggs, the two sexes are developed in nearly equal numbers. It may be conceded that in the case of the bees, as insects of specialized type, we are dealing with insects in which true unfertilized eggs develop simply into drone or neuter insects. But in the lower plant lice, the process is more nearly related to the budding of the zoophyte. Each aphis, produced viviparously from the parent body, grows from a structure which, whilst it resembles a true egg, does not pass through the development of that body, and is therefore called a pseudovum. Gradually, this pseudovum grows into the likeness of the aphis, which, after birth, will develop within itself like bodies, and thus carry on the work of continuing the species in time. If we suppose that the aphides remained connected together instead of preserving a distinct structural identity, we should reproduce in this insect tribe an exact facsimile of the zoophyte colony, with its budded branches and its ever-increasing wealth of members. For plant lice reproduction is in reality a process of budding, and the colonial constitution of the insects is really veiled and masked by their freedom from the parent stock. They may, in truth, be compared to those free-swimming jellyfish buds which the zoophyte develops upon and liberates from its branches, but which remain, nevertheless, in the gaze of philosophy, essential parts and constituent units of the animal tree which gave them birth. Lastly, let us bear in mind that the egg itself is merely a reproductive bud, and that there are gradations thus to be witnessed leading from the true egg with its normal development after fertilization to the pseudovum with its bud-like career, and finally to the bud itself, which, as we shall see, never attains, let its development be what it may, to the rank of a true individual animal. A glance will serve to show the correspondence between the development of aphides, zoophyte, and plant. In each case, the bulk of the compound organism is provided for by a process of budding, whilst as the colony reaches its higher development, the production of new and independent individuals, through eggs and seeds, respectively, is witnessed. Ressemblons des faits pour nous donner des idées, taking the term ideas as synonymous with that philosophy the praises of which have already been sufficiently extolled. From the array of facts through which we have progressed, what ideas or inferences concerning the origin of animal colonies can be reasonably derived? And firstly, let us inquire what definition biology is prepared to offer as the criterion of animal or plant individuality. it is perfectly clear that some such test of an animal's nature is demanded, for instance, by the very diversity of form and constitution which the animal kingdom presents. An individual animal we may readily define, in respect of its structural constitution, as one in which all its parts and organs exist in such intimate relationship that interference with one organ or series means the disorganization of all. Close and intimately connected structure forms in reality the plainest criterion of the individual animal viewed from that side of biology which regards morphology or structure as the basis of its philosophy. The integral constitution of its material parts is thus the plain test of an animal's individuality from the structural point of view. On such grounds, the man or the dog is obviously a much more typical individual than a newt, which can part with its tail or legs and yet live and develop new members in the place of the injured parts. And the newt, in turn, is a truer individual judged by its structural interdependence than the zoophyte, whose buds as they fall are replaced without material disorganization of its constitution. Professor Asa Gray well sums up the structural view of the individual when he remarks, quote, "The idea of individuality which we recognize throughout the animal and vegetable kingdoms is derived from ourselves, conscious individuals, and from our corporeal structure and that of the higher brute animals. This structure is a whole form which no part can be abstracted without mutilation. Each individual is an independent organism, of which the component parts are reciprocally means and ends." Unquote. But another method of viewing the personality of the animal is found in the deductions of physiology. Not what it is, but from what it has originated, is the test of physiological individuality. That alone, in physiological eyes, is an individual animal, which is the total result of the full development of a single egg. Whatever a single egg becomes, in other words, represents the individual animal or plant. Testing some of the examples already noted by this criterion, we may readily enough distinguish the true individuality of the animal races we have passed in review. With respect to the personality of the higher animals, this test is susceptible of the plainest illustration. Each quadruped, bird, reptile, fish, oyster, etc., springs from a single egg. When each of the bodies in question has been formed, we know that the full development of the egg or germ has been attained. Hence, each of the aforesaid animals is an individual, pure and simple, when judged by the standard of its representing the total result of a single germ development. With the other illustrations, the case should be equally clear. A zoophyte and a seamat spring each from a single egg, and the process of budding gives to each the plant-like form and the colonial organization familiar to us in these beings. Hence the whole zoophyte and the seamat in toto are individuals. What then, it may be asked, are the separate members of either colony? Not individuals, for they merely represent parts of a single egg's development, but zooids is the biological reply. Comparable it may be to separate organs and parts in the higher animal, but not constituting of themselves individual personalities. The cases of the Gregorina and sponge are each resolvable without difficulty on the premises just indicated. The single Gregorina, arising from a true process of development, is a single individual, but the divided Gregorina represents a compound personality. The whole sponge, arising as it does from an egg, is an individual, and if each of its protoplasmic units be held to be not merely a cell, but a semi-independent and amoeba-like organism, the sponge is a compound individual in addition. So also with a tapeworm or other allied organism. The whole worm is one compound personality or one individual because it has arisen from a single egg, and because it represents the full development of that body. So likewise with the hydra. Arising from a single egg, it gives origin by budding to other hydrae which break away from the parent organism and live an independent existence. But as these buds, although independent of the parent body, nevertheless represent part of the development of the single egg, we see that the hydra individual is not the parent hydra alone, but that parent plus all the buds or hydrae which are produced by it. The next individual existence begins with the production of an egg. Till that event happens, all the hydrae produced by budding or otherwise are merely parts of an individual and have of themselves no distinct personality. With the zoophyte and the hydra, therefore, the case for the individual existence as represented by the compound animal, that is, by the single animal plus its buds, seems clear. Quoting Professor Huxley once more, we may say that, quote, the multiplication of mouths and stomachs, unquote, in a zoophyte, as the result of the budding of new members of the colony, quote, no more makes it an aggregation of different individuals than the multiplication of segments and legs in a centipede converts that arthropod into a compound animal, unquote. The zoophyte, continues the voice of authority, quote, is a differentiation of a whole into many parts, and the use of any terminology which implies that it results from the coalescence of many parts into a whole is to be deprecated, unquote. The plant lice are to be viewed in precisely the same light, for, as Professor Huxley remarks, quote, no doubt it sounds paradoxical to speak of a million of Amphibians, for example, as parts of one morphological individual, but beyond the momentary shock of the paradox, no harm is done. On the other hand, if the asexual, that is, the products of the pseudova aphides, are held to be individuals, it follows as a logical consequence not only that all the polyps on a cordylophora or zoophyte are feeding individuals, while the stem must be a stump individual, but that the eyes and legs of a lobster are ocular and locomotive individuals. And this conception is not only somewhat more paradoxical than the other, but suggests a conception of the origin of the complexity of animal structure which is wholly inconsistent with fact, unquote. End of section 35, chapter 13, The Evidence from the Constitution of Colonial or Compound Animals, Part 2. Section 36 of Chapters on Evolution by Andrew Wilson. This LibriVox recording is in the public domain. Chapter 13, The Evidence from the Constitution of Colonial or Compound Animals, Part 3. The point to which our inquiries have led us may be summed up in the conclusions, firstly, that animals exist either as simple or as compound individuals, the former typified by the higher animals at large, and the latter by the zoophyte and the tapeworm tribe. A second inference deducible from our study is that the personality of an animal is in reality the direct result of its development and of the manner in which its parts and organs are structurally related to each other. And a third deduction follows from our biological experience, namely, that the separate parts or zooids, as we term them, of a compound individual are not necessarily connected by structural ties to the parent or primitive form. On the contrary, like the detached buds of Hydra, the free jellyfishes of the zoophytes, or the apparently free and independent members of the plant lice fraternity, the zooids which make up the personality of the true individual may be scattered far and wide from the parent organism, and be yet tied by firm transcendental bonds to the stock of which they are really intimate parts. But a further question still besets us, namely as to the origin and meaning of the variations which animal individuality thus presents to view. If the true function of philosophy be that of affording a clue to the meaning of this world's phenomena by placing facts in their due relationship to each other, it follows that the higher knowledge of the varying individuality of living beings must resolve itself into an explanation of the causes through which such personality has been acquired. Such philosophy is necessarily founded upon that view of the order of nature which regards the universe as an arena of constant modification and progressive change, as opposed to the theory of its originally and inherent stable constitution. It is the theory of evolution, as opposed to that of specially designed ways and means in nature, which presents itself as the exponent of animal individuality and its causes. On the former hypothesis alone is the question of the individuality of living beings debatable, since the idea of stability in living organisms presents a dead wall to the further discussion of the present as well as most other biological topics. Hence, the data of evolution and progressive descent, with modification, must in the present instance be used as a pathway along which our explanatory steps are to be pursued. That every living being begins life in a simpler guise than that in which it spends its adult existence is a kind of home truth in everyday life, as it is a dictum of biological science. The practical difference between a low and a high animal lies in the fact that the former does not advance much or anything beyond its primitive condition, whilst the latter in time exhibits an infinite complexity on its early structure. A Gregorina or an amoeba are lower than an oyster because development leaves the two former with bodies but little more complex at the end of life than at their birth. The oyster, on the contrary, beginning as an amoeba-like germ, takes farewell of development as an organism of high complexity and as one whose frame exhibits a marked differentiation of its organs, parts, and tissues. Now, if the body of a higher animal be analyzed out into its constituent parts, we may microscopically speak of it with the greatest possible exactness, as a collection of cells and fibers, or more simply as a collection of cells, for the fibers arise from and are developed out of cells, so that even the complex frame of humanity is truly resolvable into groups of cells which, however varied in structure they may be, arise in their turn at the commencement of development, first from exactly similar cells, and more primitively from one and a single cell, the ovum or egg itself. Thus true it is that all the higher forms of life are aggregates of such morphological units or cells variously modified. But development teaches us something more. Every animal above the rank of the amoeba and its kind, and even these latter may be included in the statement, passes in the course of its personal progress towards maturity through a stage in which the original substance of the single primitive cell or egg breaks up into numerous other cells, through the subsequent arrangement of which the body of the organism is in due course developed. This epoch our developmental studies have familiarized us with under the designations of segmentation and the morula stage. In other words, there is an early tendency on the part of every animal and plant to depart from the single-celled stage and to exhibit a compound or collective structure. The egg, at first one cell, thus divides to form a colony. Nor may the transcendental glance cease at this stage of matters. If a colonial aggregation of cells at a very early stage of development be a reality of life, if some animals, sponge and hydra for example, are but collections of primitive cells, a no less stable fact is expressed in the statement that in the adult body of the highest animals, such colonial aggregations are still to be traced. Each tissue of the human frame, in its most vital phase, is a colony of cells, a compound cellular individual, numbering its units by the thousands, and possessing the power of growing and reproducing new cells as truly as the zoophyte by budding repairs the constant loss to which its component parts are subject. And there may further exist in the highest animals cells or units which exhibit well nigh as complete an independence of the frame in which they occur as do the animalcular hosts outside. Thus the white corpuscles of the blood of all animals exactly resemble amoebae in structure, size, and movements. They are known to pass through the walls of blood vessels, to roam through the body at will, and are seen to exhibit an utter and complete independence of all the tissues of the body. More curious still, these white corpuscles have been seen to ingest solid particles, exactly as an amoeba or allied form receives its particles of food. It is not more wonderful, if we think the matter over, to find in our own bodies many true colonial aggregates of cells, than to discover that certain of the cells thereof have developed an independence and freedom of motion equal to that of an animalcule living in its native haunts, and carried out through movements of exactly similar nature to those performed by the amoeba itself. Thus a first halting place in our philosophy of individuality may readily be found in the declaration that the colonial or compound body is in reality the normal constitution of all animals, save the very lowest. With the advance of life there has been exhibited a progress in complexity, and this progress has found structural expression in the conversion and multiplication of the original unit of the germ into the colonial and compound state. We ourselves are compound individuals in the sense that our physical personality is not single in any sense, but markedly multiple. Our individuality may be named doubly compound in the sense that, whilst each tissue may be held to represent a zooid or colonial member of the body as a whole, the tissues are in their turn made up of cells, each of which is a distinct morphological unit. If the above deduction be correct, founded as it is upon strict anatomical detail, it remains to discuss those cases of colonial aggregations in which the separate units are plainly recognizable, as in zoophyte, sea mat, and tapeworm. Such cases will be found to differ not in kind, but in degree only, from the higher colonial organizations we have just described. The zoophyte and the highest animal are separated by a gulf not impassable or fixed, when the aid of broad generalization in comparative anatomy is invoked. For there are, firstly, gradations and stepping stones connecting the two extremes, and there exists, moreover, a general principle of development whereby the differences between the colonial nature of the higher and that of the lower form may be aptly expressed. Thus the sponge illustrates a case in which the colonial nature of the highest organisms is plainly enough foreshadowed. A sponge or a hydra advances but a tithe of the developmental journey which a bird or quadruped has to pursue, and as a result of its early arrest on the developmental pathway, its component units evince but little elaboration on their primitive and animalcular state. If a sponge is a mass of amoebae, as to its living parts, it exists in this simple condition because there was no further need for a more intimate relationship between its various units. The fact already mentioned that two freshwater sponges placed in contact unite into one shows the ill-defined nature of the individuality in a case like the present, where the units are merely placed in apposition, so to speak, and united simply by the common skeleton they elaborate. In a zoophyte, which is in reality but little removed above the sponge in the animal series, development and its attendant conditions, whatever these latter may have been, have together produced units as thoroughly distinct as those of the sponge, but nevertheless connected in the work of nourishing and repairing the colony. In the sea mats, we see a stage of colonial development in an animal form which more nearly approaches the condition of the higher animals, but which likewise lacks all the intimate features of connected interests seen therein. The sea mat colony is an aggregate of units, each of which we have seen to be perfectly independent, save for external connections of its neighbor units. There must thus exist a certain and not distant parallelism between a sea mat's constitution and that of higher beings, inasmuch as both are colonial, and in both the units exist in a relative but by no means corresponding degree of independence. Analogies are thus plentiful enough in showing us the stages which intervene between the dependence and connection of the units in higher life, and the comparative independence of those in lower life. But the cases of the gneiss or river worm, as well as those of the plant lice and bees, show us plainly enough the amazing possibilities of highly organized animals becoming colonial organisms, even with complete separation and detachment of the units of the colony, which, however, in the case of the bees, as social insects, is again reconstructed in the institution of a cooperative life and existence. In the gneiss, we see illustrated a tendency towards repetition of zooids which may be viewed as leading towards an appreciation of the manner in which an originally jointed animal, itself colonial in one sense, advances towards the condition of the plant lice and bees with free and separate units. It is not more surprising, we may repeat, to find the insect individual with its separated and detached units than to discover in the higher bird or quadruped the same colonial structure, but one likewise which is closely combined and intimately related as to its elementary parts. The possibilities of life are facts indeed, which in the present case cut both ways, demonstrating, even if leaving the main collateral facts unexplained, how in the higher spheres of animal society the independence of an animal colony may perfectly coexist with the interdependence of its original units. But there exists for the biologist a final and authoritative court of appeal in the matter of the origin of the colonial constitution and its modifications, in the facts and teachings of development. The general tendency of any organism undergoing development is, as we have seen, one leading it towards differentiation and division of its primitive and originally simple substance. Even in the lowest confines of life, we witness this tendency towards segregation and multiplication of its parts. The Gregorina exhibits such a process, and the early stages of all living beings are marked by the segmentation and division of the germ. Conversely, as we ascend the scale of being, we witness as marked a tendency towards concentration and amalgamation of at least the superficial aspects of the organism. The higher animal or plant is not so markedly colonial as the lower organism. Externally, indeed, there may be no trace in the higher organism of compound nature, whilst, as we have seen, the intimate constitution of its tissues fully reflects its colonial constitution. Then also, arrest of the process of development seems to increase the tendency towards the colonial organization. The tapeworms may, on good authority, be regarded as animals whose development has been arrested at an early stage of that process. We may readily enough conceive that, but for such arrest, these animals might have progressed towards that higher type of worm structure seen in leech, gneiss, or earthworm, in which the separate joints practically represent the elements of a colony in close and inseparable union. Thus, a leech or earthworm, like the higher animal, is colonial. It represents the transition stage between a low colony with loosely aggregated units, such as the sponge typifies, and the higher colony in which the units have become closely merged together, as in the bird or quadruped. This view of the intermediate place of these animals is not merely supported by their position in the animal tree, but likewise by the fact that each apparently closely connected joint of a true worm accurately represents the structure and functions of every other joint of the body, save, indeed, the specially modified segments of head and tail. The worms and their allies thus become interesting in our eyes from the fact that they present us with examples of that degree of development which, whilst leading towards union of the original units of the organism, yet leaves their identity sufficiently distinct to permit their ideal separation and the realization of their originally colonial nature through the exercise of a free philosophy. Thus we again conclude that the primitive and earliest condition of structure in the living series is the colonial and compound condition. We arrive at this conclusion from a survey of the teachings of development, which shows us, firstly, that everywhere the germ in its earliest state tends to division and multiplication. Secondly, we note that many organisms, such as the lower colonies of protoplasmic forms, or even the mere primitive sponges themselves, remain permanently in a colonial condition, which would naturally enough represent permanent arrest of development in the early stages of egg development. Thirdly, we learn that arrest of development, even at a later stage, may produce the colonial organizations of higher types. This latter view meets the case of the tapeworms and of the true worms likewise. In the latter, as represented by the gneiss, we see the hereditary tendency towards colony making reproduced as accurately in the buddings of new individuals from the parent body as in the perpetual budding of the zoophyte. Last of all, we see in the highest animals the same innate and fundamental constitution on the basis of the colony. The human frame, morphologically viewed, is a collection of cell colonies produced by segregation of more primitive collections of units, and primarily, if the story told by development be true, by the modification first of one cell and secondly of one original series of cells. The fundamental constitution of the living worlds thus appears to be of colonial nature. It remains for us to discover how the compound constitution has merged into these united and single personalities we regard as the highest members of the animal and plant series. In a word, how the colony has become the individual, the highest type of which we recognize in ourselves. If varying conditions have operated to produce the diverse constitutions of animals and plants we see displayed before our waiting eyes today, we may justly assume that a more complex series of causes than we are able to determine is responsible for the origin of those higher natures of which we ourselves form part. Yet here and there clues to the understanding of the problem are not wanting in the considerations which the study of even lower grades of life disclose to view. The apparently single nature of the germ from which high and low organisms alike spring may best be explained, perhaps, on grounds connected with the husbanding of vital power, and on the idea that the apparent unity and singleness of the germ naturally reproduce the constitution of the single cells or units of the compound organism from which they spring. The egg or germ, in a word, reflects in its first stage the constitution of the particular unit from which it was derived. In its secondary stage, it repeats the colonial condition of which its parent unit formed part, and the features of which it is destined in due time to reproduce. As, however, we survey the fields of animal and plant existence, we discover plainly marked tendencies of development which fully account for the advance from the true colonial constitution of zoophyte, tapeworm, and social insect to the marked and apparently single personality of higher life. The higher we rise in the organic series, the less marked becomes the tendency to devote the energies of life to the perpetuation of the species or race, and the more perfectly do the powers which concentrate, ennoble, and advance the individual interests become developed. It is a self-evident fact that in lower life much of the bodily energy is occupied with the development of new individuals, or in the case of an animal colony, with increase of the colonial membership. One has but to glance at the zoophyte races to find clear proof of this latter statement. Imitating the plant creation in the fullness of their vegetable growth, the tribes of zoophytes and the tapeworm race, with its millions of ova and indefinite reproductive power as well, unquestionably possess as their chief end the perpetuation of the race. How changed is the physiological prospect in higher existence! There the energies are devoted to the improvement, sustenance, and development of the individual. There is less devotion to the species as compared with what obtains in lower forms, and the colonial interests, whilst still represented and conserved, are limited in their scope and direction to the development of new tissue matter. The higher animal, in short, is not obviously colonial in the sense that a zoophyte or a sea mat is compound, because the energies and forces, as well as the material which in the lower being reproduces readily the form of the organism, are devoted to other functions. Life in the lower and compound organism is made up of one common interest, namely, the increase of the colony and species. In the higher animal, life becomes a far more personal matter, and its aims are more distinctly individualized. Existence in the colonial zoophyte is passed, so to speak, in marriage and giving in marriage, and the interests of the race are bound up in the work of its own extension. In the higher organism, individual interests in the life of the single organism occupy the greater part of its energies, so that, to use an expressive dictum, quote, the organism is like a society in which everyone is so engrossed by his special business that he has neither time nor inclination to marry, unquote. There is abundant illustration at hand of the view that the cultivation of individual interests destroys, by concentration of energy, the colonial organization. Such an opinion finds its confirmation in the details of higher animal existence, and in the disappearance of those powers of bodily separation after injury which characterize lower life. The organic republic or colony in which every unit is as good as its neighbor is typically and perfectly represented in the zoophyte. But this thoroughgoing republicanism is as impossible of continuance in higher physical existence and in spheres biological as it is found to be incompatible with the political development of nations. That is to say, as in the life political, here and there special developments cause men to shoot ahead of their neighbors and to distance their competitors in the struggle for existence by individual strength and excellence. So in the life biological, there is the same tendency to development of individual faculties and powers over the common interests, and the same conversion of the colonial organization into the concentrated structure and functions of the individual organism. In the plant world, there is a similar tendency towards concentration as the concomitant of higher life. The colonial nature of many of the lowest plants, for example, volvox, which consist of aggregated masses of protoplasm, is undoubted. But in the highest plant life also, the colonial nature is far more strongly marked than in many animals of by no means the highest grade, where the leaf type represents itself indefinitely, where bud resembles bud, and where there is witnessed the gradual transformation of leaf type into flower type and of flower into the full fruition of plant life, there is presented to our mental view an exact picture of the budding zoophyte with its series of similar units. Here and there these units become modified, now for this function, now for that. but exhibiting the closest parallelism with the plant in that its reproductive bodies are but modifications of the ordinary members of the colony, as the flower, in turn, is but the last term in the modification of the leaf. Thus, as Asa Gray well puts it, quote, "In the ascending gradation of the vegetable kingdom, individuality is, so to say, striven after, but never obtained. In the lower animals it is striven after with greater, though incomplete success. It is realized only in animals of so high a rank that vegetative multiplication or offshoots are out of the question, where all parts are strictly members and nothing else, and all subordinated to a common nervous center. It is fully realized only in a conscious person." Unquote. End of section 36. Chapter 13. The Evidence from the Constitution of Colonial or Compound Animals. Part 3. Section 37 of Chapters on Evolution by Andrew Wilson. This LibriVox recording is in the public domain. Chapter 13. The Evidence from the Constitution of Colonial or Compound Animals. Part 4. Yet whilst the plant world has not as a whole advanced towards the higher phases of individuality, we may discern here and there within its limits signs of that universal progress which evolution postulates and which biological research reveals. Here and there we witness among plants a progression from the prevailing colonial organization towards singleness of type. The composite race of plants derive their name from the fact that each flower of the order is not a single flower, but a collection of florets. A thistle or a daisy head, for example, is not one flower in the sense in which a buttercup or lily is single, but is an aggregation of small stalkless flowers, closely packed together on one main stalk. If we examine the thistle head, we shall find it to consist of numerous little flowers, of similar appearance, each containing the essential organs and parts seen in other single flowers. In the centauries of our waysides and cornfields, we witness the same composite structure of the flower head, but here the outermost florets of the head have begun to develop into petal-like organs and have lost their stamens and pistils. The centaury, in other words, has developed the beginning of a low individuality. It is losing its completely compound nature and is advancing towards the singleness of type of ordinary flowers. Thus in Centaurea nigra, these outer florets vary in size. They may resemble the inner ones in size or may be larger, and they may want both stamens and pistils. In another species, C. scabiosa, stamens and pistils never occur in the outer florets, and in Centaurea cyanis, likewise, these florets are useless for reproduction and are passing towards the type and function of ordinary petals. So also in the familiar dandelions we may witness a stage in advance of the thistle, for whilst the latter plant has its florets similar and inconspicuous, the dandelion has added to its similar florets the bright corollas, which serve to render this wayside plant so conspicuous to insect eyes as well as to our own perception. When the dandelion appears with its outer florets expanded, while the inner florets have still to unfold, the flower bears no inconsiderable resemblance to the ordinary type of single flower. Far more advanced, however, towards the individuality of other plants are the marigolds, daisies, and their allies. Here the likeness of the single flower deceives the non-botanical observer into supposing that each daisy in reality corresponds to each buttercup or primrose in its constitution. For the outer florets of the daisy and marigold have developed, as those of the centauries are developing, into long petal-like organs. Moreover, these outer florets are losing the reproductive organs they still possess in the dandelion. The stamens have disappeared in the outer white and yellow flowers of the daisy and marigolds respectively, leaving the pistil alone represented, whilst the yellow central florets possess both stamens and pistil, and are therefore the true producers of seed. It is foreign to our present inquiry to notice how this arrangement of the flower parts, by placing the brightly colored parts on the outside, imparts to these plants their conspicuous nature, and thus, by attracting insects, gives them a very marked advantage in the struggle for existence, through securing more frequent fertilization. How or why this greater attractiveness has been acquired is immaterial. That which is all important for us to note is that concurrently with a conspicuous dress, there is, being developed in such flowers as the daisies and marigolds, a return to that singleness and individuality which was in all probability once represented in their race, before the work of aggregating once separate flowers to form one flower head had begun. The thistles remain types of a true flower colony. The dandelions and centauries lead us from the thistles with similar florets to an intermediate type, wherein we see being developed those features which, along with the abortion of part of the outer florets, are causing the compound flower to assume the dress of its simple neighbor. Whilst in the daisies, specialization has advanced a step further, and has developed a very marked likeness to the simple flowers around. If these modifications progress in the future, as in the past, we may naturally expect the flores vitae and ride of Chaucer and their allies will develop a still more marked individuality, and will leave the lower compound nature of their race further and further behind. It may be, lastly, interesting to note that the crowding together of flowers on a flower head seen in the daisies and their neighbors is susceptible of explanation through a study of the modifications and gradations witnessed in the arrangement of flowers on their axes. From cases in which we find flowers situated each on a distinct stalk of its own, as in the corymb and the umbel of botanists, to the condition of the flower head we can pass by easy gradations. If we cut short the stalks of the umbel, and thus crowd the separate flowers on the end of a common stalk, we obtain a fair idea of the possible origin of a flower head by abortion of the flower stalks of an umbel or allied floral arrangement. The fact that such crowding of flower heads on a common stalk is not limited to the Compositae or daisy tribe, but occurs in other plant orders, argues powerfully in favor of its acquired nature as the result of common modifying conditions. Thus, a head of clover essentially repeats the condition of the thistle or centaury. We can obtain a fair idea of the effect of modification by the disappearance of flower stalks if we look at a simple umbel seen in the cherry, or a compound umbel seen in the fool's parsley, and by crowding the flowers together, minus their stalks, imagine their growth in one stalkless group to represent the flower head of the daisy or thistle. Summing up our studies in organic individuality, we may say that, firstly, the original and primitive condition of all organic beings is a colonial condition. This phase is exemplified primarily in the segmentation of the egg and in the cell multiplication of plant germs, two features of so universal occurrence that we may lawfully claim for them a great importance in the evolution of the organism and a high antiquity in the history of living things. It is likewise imitated in the so-called asexual reproduction of the lowest animals, represented by the Gregorini and Amoebae. A second conclusion that follows from the teachings of development may be expressed by saying that this tendency to division of substance is most typically seen in lower organisms, where, as exhibited in the sponges, zoophytes, and their allies, the constitution of the individual is undeniably compound, and where its advance is marked merely by the multiplication of new types of colonial and connected units. We discover, thirdly, that the tendency to degradation and retrogression may likewise plainly develop the compound and colonial state. It is highly probable that the tapeworms, the ordinary worms, and even the articulate animals themselves illustrate cases in which a primary development of like segments or colonial units through arrest of growth and through simple bodily division and repetition of like parts has paved the way for succeeding modification of the colonial type. If the evolution of the centipedes, insects, spiders, and crustaceans from a lower worm type be accepted as proved, or even as probable, the characteristic features of these animals must have been fundamentally derived from those colonial tendencies we see exhibited in the worms of today. A fourth conclusion teaches that the plant world is markedly colonial even in its highest types. The vegetative repetition of bud, leaf, and flower is simply a pure indication of colonial constitution exhibited in all that perfection of detail which has escaped the more forcible modification of the animal series. A fifth inference directs attention to the essentially colonial constitution of even the highest animals, as exhibited in their cellular structure and more especially in the independent constitution of many of their component cell elements. And a sixth and final conclusion is deducible from our studies, namely, that concentration of structure and function, and the metamorphosis of the colony into the true individual, is at once a cause and a result of the progressive tendency of life at large. The higher we rise in the scale of being, the more united and specialized do structure and function become. Such a tendency is represented, as we have seen, even amongst plants, in which the colonial and compound type tends to resolve itself into the simpler and more individualized phase. At the same time, we must recognize that, despite the functional unity of the highest animals, there remains in their relative cellular independence the traces of a colonial constitution, once universal, and still linking them by real as well as by transcendental bonds to lower and antecedent phases of existence. The topic of the personality of living beings, like most other biological subjects, relates itself more or less indirectly with matters personal and ethical, which are far beyond the scope of the present study. But it is permissible in a closing sentence to remark that many of the characteristic traits of the life of the higher animals, including man himself, may perchance be traceable to an unconscious perpetuation of habits and customs which find their beginnings and germs in the lower colonial organisms whose history has just been discussed. The nervous acts of man and the higher animals generally, for instance, convince us that many of the functions of the brain and the automatic actions of the body, depending on the independent constitution of our nerve centers, may be legitimately explained by referring them as regards their origin to an originally colonial constitution and to a primitively colonial ancestry. Even a glance at the serial repetition of the bones or vertebrae in the spine of man or other backboned animal eloquently enough testifies to the apparent colonial constitution of these forms. There is a striking analogy, which has not escaped biological notice, between the arrangement of these segments in the vertebrata and the similar disposition of parts in the articulata or worm and centipede type. However the vertebrate's serial arrangement has originated, it may perhaps be held as legitimate evidence of compound nature, just indeed as the colonial nature of vertebrate tissues demonstrates that nature in another fashion. And so also with other phases of human relationship and functions. As the various detached buds of a hydra or the free-swimming buds of a zoophyte are still part and parcel of the individual constitution, or as the plant lice and bees, apparently of distinct personality, are in reality only parts of the connected colony, so in the sphere of human relationships, the origin of the tribal connection or of the family constitution, itself the most expressive of all human institutions, may perchance be found to exist in germ form in the hidden transcendental bond which the philosophy of the lower animal individuality discloses. The deep-seated affections and relationships which, collectively, we term the family and society, respectively, may have had their first beginnings in the connected series of interests which even the zoophyte series discloses to view. In other words, we are constituted as we are, gregarious, social, and ethical, because we are physically colonial by constitution, and because in our origin we are essentially of colonial and compound nature. And if such a thought be regarded as too improbable for realization, it should be borne in mind that our structural beginnings themselves are of the lowliest and simplest description. If the structural germs of the highest life begin, as they certainly do, under an animalcular guise, is it overstepping the possibilities of natural facts to suggest that the social traits and characteristics to which that germ attains may likewise have had a lowly and material beginning? Such an idea, so far from possessing any elements of impossibility, is grounded on a rational basis, namely, on that opinion which teaches that community of origin may, and often does, entail similarity of results. Sufficient has been said to show that in human existence reign many of the colonial traits of lower spheres, and if, perchance, some dim echoes of such lowly traits may linger in the scientific mind when contemplating the highest existence of all, the mind will regard such similarity as founded upon no chance basis, but as having originated from that continuity of cause and effect which runs unbroken through the warp and woof of the universe of life. End of section 37. Chapter 13. The Evidence from the Constitution of Colonial or Compound Animals. Part 4. Section 38 of Chapters on Evolution by Andrew Wilson. This LibriVox recording is in the public domain. Chapter 14, The Fertilisation of Flowers, Part 1. Few subjects, if any, are better calculated to awaken a lively interest in the investigation of natural laws and the phenomena of life at large than the study of those processes of development whereby the races of animals and plants retain their hold upon the world and maintain a continuous and unbroken round and cycle of existence. In such studies, more than in any others, we seem to gain near glimpses of nature's ways and methods in fashioning the varied universe of living beings. Whilst the lessons such topics are well calculated to enforce, respecting the order of nature as a whole, form not the least important result of these investigations. The study of even the most commonplace object may, under the newer phases of research, be made to yield an amount of sweetness and light for which we might be wholly unprepared. The day of the Peter Bells and of uninquiring minds and tenses, if not altogether a thing of the past, is happily already in its twilight stage. The schoolboy with a primer of botany in hand understands things at which the previous generation simply wondered. And even if the results of botanical study may occasionally be expressed by the hackneyed Wordsworthian idea of thoughts beyond tears, the modern student of plant life has ample reason to congratulate himself on having attained the mastery of many ideas, which in past years were included under the poetic category of expressive silence. The primrose still grows by the river's brim, in truth, but it is no longer merely a yellow primrose. On the contrary, the flower is in greater part understood. The mechanism of its life is well nigh completely within our mental grasp. And best of all, its study has led in the past, as it leads even now, to the comprehension of wider ideas of nature and more extensive views of plant life than those which formerly met the gaze of the wayfarer in scientific pastures. The appreciation of what is involved in part of the life history of a primrose may thus serve as a starting point for more extensive research into the phenomena of plant fertilization at large, and this latter topic, in its turn, falls naturally into its proper niche in teaching us plain lessons respecting the manner in which the wide domain of life is regulated and governed. By the fertilization of a plant is meant to be indicated those actions or processes in virtue of which those little bodies named ovules, developed in the seed vessel, become seeds, and through which they are fitted to develop into new plants. The unfertilized ovule is incapable of producing a new plant. When set in the ground, it would simply decay, as if it were a leaf or other detached and dead portion of the plant economy. When, on the contrary, it is duly fertilized, the ovule, becoming the seed, has become possessed of the powers and properties in virtue of which it is capable of evolving the form of the parent plant from which it was derived. So much for the very necessary botanical distinction between ovule and seed. The process of fertilization is thus seen to be that on which the continuance of plant existence depends. More closely regarded, it is known to be that which is capable under certain conditions of giving origin to new races or varieties of the plant species. When the horticulturalist, taking the pollen from one species or variety of plant, applies this fertilizing matter to the ovules of another variety or species, the characters of the two different races are combined and united in the hybrid progeny. Our gardens and conservatories, and as we shall strive to show hereafter, the natural plant creation at large, have benefited immensely in beauty from a knowledge of the changes in color, form, and size which this cross-fertilization may produce. For instance, the finest of our rhododendrons are crosses in which the characters of Indian and American species have been thus blended. The union of the common heart's ease with a large-flowered foreign pansy has produced a new stock in which the excellences of both species are found. The pelargoniums of our conservatories represent hybrid stocks and varieties which cross-fertilization and cultivation have together produced from the small-petaled species of South Africa. Such results, among countless others, would seem to suggest that beneath the subject of cross-fertilization, or even underlying that of ordinary fertilization, there lies hid a mine of knowledge respecting the causes which have wrought out the existing variety of plant life. For the plain and unfettered understanding of the subject in its less technical phases, or to lay the foundations of knowledge respecting an interesting field of natural history study, no better subject could be selected than the history of even the most commonest flower, such as a primrose. Rightly comprehending what is included in the phases of primrose life, we may hope successfully to read some of the more abstruse problems presented by the wider aspects of plant existence at large. Quote, "The ruth of primrose that forsaken dies, and the cowslips when that hang the pensive head," unquote, afford us delight even when we are living in all the simplicity of botanical ignorance. It is not too much to say that their systematic study may lead to the higher delights and more cultured joys included in the knowledge of some phases of natural law and in an understanding of the hows and whys of living nature. The elementary botany of a primrose is a matter of few words. Like every other perfect flower, it consists of 4 parts or circles of organs placed one within the other. Outside we perceive the circle of fine green leaves, which we name the calyx, each green leaf of this organ being named a sepal. In the primrose or campanula, the sepals are united, although in many other flowers, for example buttercup and wallflower, we should find them free and separate. The calyx of all flowers is for the most part colored green, its obvious use being to form a protective envelope for the other organs of the flower. Within the calyx we descry the corolla. This is the circle of petals or leaves which, par excellence, we call the flower, because it constitutes in the vast majority of flowers the bright and showy portion thereof. A flower might botanically or physiologically be perfect enough minus its corolla, although the eye, missing the bright petals, would be apt to regard such a plant as wanting the first and chiefest element of the blossom. The common nettle, for instance, appears to possess no flowers in the popular and accustomed sense of the term, but when we examine the plant, we readily discover that it possesses parts corresponding to the flowers of other plants. In the greater nettle, the flowers of one plant are essentially different in that they possess stamens alone from those of another plant which possesses pistils only. But in the lesser nettle or in the oak, these distinct flowers are found on one and the same plant. No vestige of color appears in either, however, and when we study the flowers in question, we find that a corolla is wanting, although a calyx is present. Again, in the willow, which like the greater nettle has its stamens and pistils on different plants, there appears to be no flower in the ordinary sense of the term, and the calyx as well as the corolla is found to be wanting in these trees. The stamens, just mentioned, form the third set of organs proper to the perfect flower. Looking at buttercup, wallflower, saxifrage, or campanula, we readily see the stamens. They exist as stalked organs, each consisting of a stalk or filament and a head called the anther. The head is hollow and contains the fine yellow dust termed pollen, which at the time of ripening is usually found scattered conspicuously about the interior of most flowers. The fourth and central set of organs found in the flower constitute the pistil, or seed-producing structure. This organ is composed of one or more parts called carpels. Each carpel consists in turn of a lower distended part called the ovary, within which the ovules are produced, of a neck or filament, the style, and of a head borne on the style and named the stigma. The style or stigma may be absent, but in the great majority of flowers both parts are present, the ovary being, however, the essential part of the pistil. In the head of a poppy, for instance, there is no style, the bulk of the head consisting of the ovary containing numerous seeds, and the flat cap or lid representing the stigma of the poppy pistil. As a final observation concerning the parts of the flower, it may be noted that the separate pieces or carpels of which a pistil is composed may either be free and distinct or closely united and adherent to each other, whilst a second fact of importance in the general description of flower structure consists in the declaration that the ripe and mature pistil is the fruit in botanical parlance. True, there may be, as in the strawberry, be found united to the ripe pistil certain other parts which constitute the edible and desirable portion of the plant. The true pistil in the strawberry consists of the little yellow carpels, usually called seeds, which are embedded in the fleshy mass of the fruit formed by the expanded top of the flower stalk. But the aesthetics of taste may be neglected in the strict descriptions of science, and that alone is the fruit, in the eyes of the botanist, which is formed by the ripened pistil, or central organ of the flower. All parts of the flower, it must be observed, are not of equal value in the eyes of the botanist. Those organs, stamens, and pistil, which produce and elaborate the seed, are physiologically more important than the circlets or whorls of leaves which, in the form of calyx and corolla, surround and protect them. Yet the latter organs play their own part in the production of seeds, and in some cases serve as the actual means whereby special modes of fertilization are primarily induced and carried out. As the sequel may show, indeed, the calyx and corolla, which in previous years were deemed mere floral envelopes, being credited, as such, with a merely protective function, have largely risen in importance in the estimation of the botanical world. Since on the form, color, size, etc. of the corolla especially largely depend the working of those mutual relations which have been formed between the insect world on the one hand and the world of flowers on the other. Peculiarity of a corolla implies, botanically as a rule, peculiarity of fertilization, and the importance of the blossom becomes plainly apparent to us when we discover that in place of the somewhat limited function formerly assigned to it by the unscientific philosopher, namely, that of affording delight to man by its beauty, it subserves the truer and more logical mission of aiding materially the increase of the race to which it belongs, and of which it forms such a characteristic part. Turning to the primrose for practical illustration of the foregoing precepts, we may readily enough find in its structure plain instruction in the build of the flower. The circle of green leaves placed outside the yellow blossom is, of course, the calyx. This green cup consists of 5 leaves or sepals united in the primrose, but free and easily separable in the buttercup or wallflower. The blossom or corolla of the primrose exhibits similarly a united condition of parts. We can tell that it consists of 5 petals or leaves by counting its prominent lobes or projections. When we tear the corolla in two, longwise, we readily perceive the 5 stamens, which, however, in the primrose exhibit a somewhat peculiar position, in that instead of arising from the end of the flower stalk, like the other organs of the flower, they spring from the sides of the united petals. If we seize the corolla of a primrose by its upper portion and pull it gently upwards, the entire blossom with its attached stamens will become detached from the flower stalk, leaving the calyx and pistil on the latter organ. Then, tearing or cutting away the calyx, we may be favored with a clear view of the pistil itself, seated on the extremity of the flower stalk. In the pistil, we behold a body consisting below of the swelled or rounded structure already mentioned, and named the ovary. This, being cut across, is seen to contain numerous seeds or ovules, as the case may be, arranged around a central pillar named the placenta. From the upper part of the ovary arises a long stalk, the style of the pistil, and the style, in its turn, is capped by a flat head, the stigma. In the pistil of the primrose we therefore see the 3 typical parts, already noted as constituting the central organ of the flower. The pistil, in this case, it may be remarked, consists of 5 carpels, so closely united that it is only by the aid of the law of symmetry, or that demonstrating the general correspondence of numbers in the flower parts, that we can determine its composition. 5 is the ruling number in the calyx, corolla, and stamens. Hence we conclude that the pistil of the primrose in its composition will conform to the type of the other whorls of the flower. The physiology of the flower naturally follows the consideration of its structure. Living action, in other words, forms the natural corollary to living machinery or structure. Hence we may fitly inquire into the manner in which the work of fertilization is carried on in the economy of the primrose. Leaving for after treatment the more special features of fertilization, the general scope of the function whereby, as we have seen, the immature ovules are converted into seeds, each capable of developing when planted into a new primrose, may be readily appreciated. The stamens, each possessing as its essential part the anther or head, develop the yellow dust or pollen as one of the two elements concerned in the work of plant development and reproduction. Sooner or later, the anthers of the stamens open in one way or another so as to allow the pollen to escape, and viewed under the microscope, the pollen grains are seen to vary greatly in size and form in different species of plants. The grains of pollen may be round or oval in form. In the evening primrose and fuchsia, they are of triangular shape. In the hollyhock and melon, they are spinous, and in the orchids, they are united to form masses called paullinia. The pollen grains being conveyed to the stigma of the pistil, they are there attached by the aid of a glutinous secretion which may likewise be credited with a specific influence on the pollen grains in that it appears to stimulate the curious development they next evince. This development consists in the rupture of the outer of the two layers of which each pollen grain consists. Through the ruptured outer coat, the inner layer begins to grow in the form of a long tube, the pollen tube, which penetrates the tissue of the style and grows downwards to reach the ovules contained in the ovary. In some plants, the pollen tubes emitted from one pollen grain may be very numerous, although as a rule, only one tube grows from each grain. Now, the essence of fertilization, that is, the production of a seed fitted to produce a new plant, appears to consist in the contact of the pollen tube with the ovule, so that the viscid matter, called fovula, contained within the pollen grain may be applied to the structures of the ovule. The most important part of the ovule itself is a small cellular body called the nucleus, enveloped in a couple of coverings. The hollow interior of the nucleus is named the embryo sac, and an opening called the micropyle also exists in the coats of the ovule. Through this opening, the pollen tube passes, gaining admittance thereby to the nucleus, and thence to its hollow body or embryo sac, wherein the fovula, or contents of the pollen grain, are discharged. Such is the work of fertilization, and such are the processes in virtue of which the ovule becomes the seed. As the result of these processes, the embryo or young plant is duly formed within the embryo sac, and thus, even before the seed is planted, development has already proceeded to a certain extent. In the seed of a pea or bean, for instance, we readily perceive the rudiment of the stem, the beginning of the root, and likewise the first appendages or seed leaves which that stem will develop. The process of fertilization thus described in its essential nature involves in the case of certain plants some curious details, the mere mention of which may stimulate to an independent research into botanical lore. Thus often the pollen tubes may require, from the length of the style of the pistil, to grow to a large relative extent. In the crocus, the pollen tube requires to grow to a length of 3 inches before it can reach the ovules in the ovary. The number of pollen grains in flowers may be apparently in excess of all reasonable proportions, a fact to be accounted for on the well-founded idea that the pollen of a flower is not usually limited to that particular flower's wants, but may be destined to serve for the fertilization of others of the same species. In the great flowered cactus, Cactus grandiflorus, Morin says there are about 500 anthers, 24 stigmas, and 30,000 ovules. Assuming that each anther contains 500 pollen grains, this will give a total of 250,000 grains to each flower, and the interval or space between the stigma and the ovules of this plant is about 1,150 times the diameter of the pollen grains. Nature appears exceedingly lavish in her development of pollen, if the Tennysonian aphorism that of 50 seeds she often brings but one to bear be true, as it unquestionably is. The apparent overproduction of pollen grains is even more remarkable, although we have to take into account the fact just noted that the development of pollen bears a relation rather to the species and race than to the individual necessities of the plant. Otherwise, Fritz Müller's estimate that in a single flower of Maxillaria there are developed 34 million grains of pollen must present itself as an inexplicable fact of botanical science. Even the wheat plant produces about 50 pounds of pollen to the acre. The pollen of the cone-bearing plants, coniferae, such as the firs, larches, pines, or that of the catkin-bearers, Amentiferae, is often borne through the air as showers of yellow sulfur-like dust. This dust, falling in regions where the elements of botany are unknown, cause perturbation amongst the unlearned, and result in the penning of epistles to Mr. Editor by way of inquiry whether or not the sulphurous shower is a portent or grave omen of coming disaster or impending peril. The phenomena of fertilization just detailed take place in our primrose as in all ordinary plants, but whilst there exists a uniformity in the details of this process, there is also found a literally amazing variety in the fashions whereby pollen is conveyed to the stigma of the pistil. Once placed in the natural position for fertilization, the growth of the pollen tube follows as a matter of course, but the means whereby the pollen reaches the stigma and the various fashions in which it may gain its ultimate position on the pistil constitute features in which are bound up some of the most important issues of plant existence. To rightly comprehend the bearing of fertilization, a glance at our wallflower, primrose, foxglove, or buttercup will suffice as a starting point for further investigation. Within the primrose and the buttercup are situated, as we have seen, the two sets of organs, stamens and pistil, necessary to secure the production of seed and the continuance of the race. Hence it might form a very natural and reasonable inference that the pollen from the numerous stamens of a buttercup flower should be used to fertilize the ovules of the pistil of that flower. Such a process, that in which a flower's own pollen is used to fertilize its own ovules, is termed self-fertilization. Looking at the vast majority of our flowers and plants, which possess each a perfect array of stamens and pistil, the normal course of things seems strongly suggestive of self-fertilization. Hence, in the early days of botany, self-fertilization was undoubtedly believed to be the rule of nature. Now there can be no question whatever that self-fertilization does occur in nature, but there is as little doubt that it is the exception and not, as botanists from the days of Linnaeus well nigh to our own day have maintained, the rule of plant life. There can be little doubt, for instance, that many small species of the buttercup order Ranunculaceae, for example, Ranunculus hederaceus, are self-fertilized, because we find the stamens to arch over the pistil and to shed their pollen on the carpels. In Agrimonia in the same order, the stamens at first curved outwards curve inwards, so as to bring the pollen within easy reach of the stigmas. So also in a species of Malvaceae, Malva rotundifolia, Müller has demonstrated that this plant is self-fertilized, since stigmas and anthers actually intertwine and are thus placed in the most favorable position for the fertilization of the ovules. Some species of Geraniaceae, for example Geranium pusillum, are self-fertilizing likewise, and many flowers belonging to the rose tribe, Rosaceae, such as Potentilla, fertilize themselves. It is a remarkable fact that in certain plants, for example many violets, Lamium implexicola, oxalis, etc., very small, inconspicuous, and closed flowers are produced, in addition to the ordinary conspicuous and, as we shall see, cross or insect-fertilized flowers. These closed flowers have been named cleostogamous, a term applied by Kuhn in 1867. They are self-fertilized and produce numerous seeds, and their occurrence in the same plant along with cross-fertilized blossoms may perhaps be best explained on the theory that, whilst the ordinary and less fertile flowers will afford to the plant the advantages and benefits which accrue from cross-fertilization, the cleostogamous flowers may be regarded as the normal means for the ordinary increase of the race. What the flower loses in variation by the sparing fertility of the cross-fertilized flowers, it may gain in the number of seeds which the cleostogamous flowers produce. Cleostogamous flowers likewise tend to economize pollen. Whilst 400 pollen grains may serve the purpose of close or self-fertilization in oxalis, or even 100 grains in some violets, 3.5 million grains may be produced in the insect-fertilized flowers of the peony, and many millions in the case of wind-fertilized flowers whose pollen, like that of the firs, has to be distributed over immense areas of land. End of section 38. Chapter 14, The Fertilization of Flowers, Part 1. Section 39 of Chapters on Evolution by Andrew Wilson. This LibriVox recording is in the public domain. Chapter 14, The Fertilization of Flowers, Part 2. There appears, therefore, to be a proportion of plants in which the existence of stamens and pistil in the same flower, the normal condition of matters in ordinary plants, is meant to and does secure the fertilization of the ovules by the flower's own pollen. Why, then, seeing that the presence of correlated stamens and pistils in each flower appears to be a common condition of plant life, do we assume that not self-fertilization, but the opposite process, cross-fertilization, is the rule of nature? The reply to this query involves more than one important consideration. Let us briefly endeavor to find a convenient starting point in the familiar flower which Peter Bell despised, and which to minds of utilitarian type amongst ourselves is but a primrose still, and nothing more. If we study the structure of the primroses, we may gather in a bed of these flowers it will be found that the blossoms obtained from one set of plants will vary in certain respects from the flowers of other and neighboring plants. There is no difference in appearance or in outward aspect between the primroses, because the differences referred to affect chiefly the position of the stamens and the length of the style or neck of the pistil in each variety. But we may readily discover that, selecting any one primrose plant, all the flowers of that plant will be either long-styled or short-styled, and will not exhibit a mixture of the two varieties. The two kinds of flowers, says Mr. Darwin, speaking of the long and short-styled cowslips, which form a closely allied species to the primroses, are never found on the same individual plant, and he also remarks that he has never met with any transitional states between the two forms growing in a state of nature. The cowslips and other allies of the primrose exhibit a like disposition of parts. Thus, when we slit one of the primroses longwise, we see that the stamens are placed high up on the petals or near the top of the corolla, and the style is comparatively short. In the other variety, the stamens are placed far down within the tube of the corolla, whilst the style is so long that the stigma appears to block up the entrance to that tube, and reaches to the top of the petals. Thus we speak of short-styled and long-styled flowers in primrose and in all other plants in which these conditions occur, whilst popularly the short-styled forms are called thrum-eyed and the long-styled ones pin-eyed. Such a disposition of stamens and pistil also occurs in Pulmonaria officinalis, in Linum perenni, and in other plants which are hence called dimorphic, that is, having two forms of flower. And in some plants, for example oxalis and the spiked loosestrife or Lythrum salicaria, three varieties of flowers are known, and these latter are named trimorphic in consequence. Returning to our primroses, we find that the pollen grains of the two forms of flower differ in size. Those of the long-styled primroses are smaller than those of the short-styled flowers. Mr. Darwin remarks of the pollen grains of the latter flowers that, quote, before they were soaked in water, they were decidedly broader, in proportion to their length, than those from the long-styled. After being soaked, they were relatively to those from the long-styled as 100 to 71 in diameter and more transparent, unquote. Mr. Darwin also compared these two forms of flowers in other respects. He found that the seeds of the short-styled flowers, quote, weighed exactly twice as much as those from an equal number of long-styled plants, unquote, the short-styled being the more productive of the two forms. As final facts concerning the differences between the two varieties, it may be noted that the stigma or head of the pistil in the long-styled form is more distinctly globular and roughened on its surface than that of the short-styled primroses, whilst the stigma in each form stands nearly, but not quite, on a level with the anthers of the opposite variety. What can be affirmed as a matter of observation to be the meaning and purpose of this diverse arrangement of stamens and pistils in these plants? Meaning it must have, and that one which is closely bound up with the history of the species. So indeed it was found when, through Mr. Darwin's researches, contributed to the Linnean Society's Transactions in 1862, it was clearly demonstrated that the arrangement in question had reference to the cross-fertilization of the primroses and of all other plants in which a like diversity of structure was found. Mr. Darwin then pointed out that the structure of the primrose was eminently adapted to favor the visits of insects as aids in procuring the fertilization of the long-styled flowers by the pollen of the short-styled flowers, and vice versa. Such an interchange of pollen is accomplished in a manner readily understood. Suppose that an insect, such as a humble bee, first visits a long-styled flower, drawn to the primrose in search of the nectar which this flower, the cowslip, and other members of the genus secrete in quantity. The proboscis of the bee will be thrust into the tube of the corolla, and in the act of nectar gathering it will unconsciously dust its proboscis with pollen nearer the tip of that organ than at the base. Suppose next that the bee, with its pollen-laden proboscis, flies to another primrose plant of the short-styled variety. The proboscis inserted therein as before will come into contact with the low-lying stigma, and upon this surface will be left the pollen which was gathered from the stamens of the long-styled flower. Thus, interchange the first is accomplished. But when visiting the short-styled flower, the bee's proboscis, coming in contact with the stamens placed at the top of the flower, is dusted near the base with short-styled pollen. Hence, the next visit paid to a long-styled flower results in the placing of pollen from the short-styled flower upon the stigma of the long-styled primrose. The stigma of the latter is placed, as we have seen, at the top of the flower, and is thus well calculated to meet the base of the bee's tongue, which has been dusted with short-styled pollen. Interchange the second is thus accomplished, and the cross-fertilization of the primrose race becomes a matter of well-nigh absolute certainty. As indicated in the annexed figure from Mr. Darwin, the legitimate fertilization is that which occurs when pollen from the long-styled form is placed on the short-styled pistil and vice versa. The illegitimate fertilization is self-fertilization in either case, namely, through the pollen of either flower being placed upon its own stigma. Mr. Darwin's own words, applying to his observations on the cowslip, Primula virus, may be read with interest as applying likewise to the similar arrangement in the allied primrose. After noting that humblebees and likewise moths visit these flowers, Mr. Darwin says, quote, "It follows from the position of the organs, anthers, and stigmas that if the proboscis of a dead humblebee or a thick bristle or rough needle be pushed down the corolla, first of one form and then of the other, as an insect would do in visiting the two forms growing mingled together, pollen from the long stamened form adheres round the base of the object and is left with certainty on the stigma of the long-styled form, whilst pollen from the short stamens of the long-styled form adheres a little way above the extremity of the object, and some is generally left on the stigma of the other form." Unquote. Mr. Darwin is also careful to note that self-fertilization must occasionally occur in these flowers through, quote, "an insect in withdrawing its proboscis from the corolla of the long-styled form," unquote, leaving pollen from the flower on that flower's own stigma. Such a result will occur most frequently in the case of the short-styled flowers, as may be experimentally demonstrated, and small insects such as those belonging to the genus Thrips, wandering aimlessly about within the flower, may likewise be the means of inducing self-fertilization. But, as if in anticipation of such defeat of her clear intent and purpose, we find a very significant observation brought to light in the fact that even if a flower's own pollen be placed on its pistil, cross-fertilization may yet take place, inasmuch as pollen from a different form of flower seems to be capable of obliterating the effect of the flower's own pollen. Even as Mr. Darwin, quote, "when this has been placed on the stigma a considerable time before," unquote. An experiment of very crucial nature supplies an instance of the prepotent effect of foreign pollen over a flower's own. On the stigma of a long-styled cowslip, Mr. Darwin placed plenty of pollen from the same plant. After a lapse of 24 hours, he added pollen from a short-styled dark red polyanthus, which is a variety of cowslip. Quote, "From the flowers thus treated, 30 seedlings were raised, and all these, without exception, bore reddish flowers, so that the effect of the pollen from the same form, though placed on the stigmas 24 hours previously, was quite destroyed by that of pollen from a plant belonging to the other form." Unquote. The philosophy of primrose existence can hardly be said to be in any sense comprehended through the mere knowledge of the contrivances which exist in that flower for the prevention of self-fertilization and the favoring of the opposite process. On the contrary, the philosophy which carries with it the understanding and appreciation of the system and order of nature is only discernible when firstly we step forth more fully into the light of things, and when secondly we discover, from such wider views of flower life, the advantages gained and the ends served by the processes under consideration. Hence, for the present, we may turn with profit from the polity of a primrose to discuss some analogous features in that wider realm of flowers to which the primrose and its kind may fitly introduce us. After such survey we may, with additional likelihood of arriving at just conclusions respecting the philosophy of plant life, return to the primula and its lessons once more. It has been already remarked that self-fertilization is the exception and cross-fertilization the rule of plant nature. At any rate, the cases where cross-fertilization is obviously the process which by manifold contrivances nature seeks to further and effect increase in number year by year. Although self-fertilization does occur, and is a possibility even with normally cross-fertilized plants, yet the whole drift of modern botanical teaching tends towards the recognition of the mutual interchange of pollen betwixt related flowers as the normal way of plant reproduction. Nor do the comparative results, to be hereafter detailed, of cross and self-fertilization in the least degree vitiate these conclusions. On the other hand, every fact of botany dealing with ascertained results of the one method of fertilization, as compared with those obtained by the other, testifies to the enormous gain, possible and actual, to the plant creation through the effects of cross-fertilization. The presence of so many different methods whereby this end is secured constitutes an eloquent fact in favor of the supposition that the normal way of plant life undoubtedly lies in the direction of pollen interchange, as a necessity for energetic development and for the full fruition of the races and tribes of plants that people Earth's firmament. Within the limits of the present chapter, it would be impossible to enter into the discussion of those peculiarities of insect structure which have been developed or modified in turn, like the forms of flowers, for the due performance of the work of cross-fertilization. It may suffice at present to simply point out that the conformation of the legs of certain insects, as well as the form of the mouth parts, and even the hairiness of body or the reverse conditions, all bear witness to special adaptation in different insects for the fertilization of special flowers. Certain insects are known to confine their visits to special plants, some to one species of plant only, and probably, when this department of the subject is more fully and completely studied, the number of cases in which insect visitation is of a rigid or exclusive kind will be largely increased. The two chief methods of cross-fertilization, or in other words of flower fertilization at large, are thus 1. By insects, or more rarely birds, snails, etc., 2. By the wind, whilst 3. Pollen may be floated on water from one plant to another, as in the case of Vallisneria spiralis. Botanists term plants fertilized by insects entomophilous, and those fertilized by the wind anemophilous. Some plants, for example common rhubarb, and some species of plantigo, exhibit an intermediate condition in that they may be fertilized in either way. The wind-fertilized plants, as an invariable rule, according to Darwin, possess small and inconspicuous flowers, whilst the insect-fertilized flowers, as might be expected, are conspicuous, or if not brightly colored, are strong-smelling. Moreover, there are certain conspicuous differences between the pollen and its quantity, and between the form of the stigma, etc., in wind-fertilized and insect-fertilized flowers. The pollen of the wind-fertilized plants is produced in far greater quantity than that of the insect-dependent flowers. Then also the former flowers open before the leaves are in full growth, in order that the clouds of pollen may gain easy access to the pistils, whilst their stigmas are usually branched and bending, for example, alder, wheat, etc., so as the more readily to intercept and detain the pollen in its wind flights. Allusion has already been made to the showers of pollen emitted by coniferous trees, and it may be added here that bucketfuls of pollen from conifers and grasses are occasionally swept off the decks of vessels off North American coasts, whilst North American lakes may be covered over a considerable area of their surface by the yellow pollen of the pines. Most of our cereals are presumably wind-fertilized, and the importance of light breezes in the early summer may therefore be a matter of consideration in respect of the full ears of autumn. Hudibranch and Kuhneke, in their practical suggestion, carried out in Belgium and Germany, of drawing a rope across the full-flowered ears so as to distribute pollen and cross-fertilize the plants, seem therefore to have imitated nature's method. The question of the wind fertilization of the cereals, it may be remarked, however, is at present an open one, since some botanists elect to believe that the wind-distributed pollen is simply the excess or useless pollen remaining after fertilization has been accomplished, the actual agency in scattering abroad the fertilizing dust being said to be the sudden extension and elasticity of the stalks of the stamens. That cross-fertilization is the rule of nature is a fact amply demonstrated by the well-nigh endless contrivances in flower structure, form, appearance, and function through which the interchange of pollen is brought about. Let us briefly glance at the outlines of such a study. Allusion has already been made to cases in which a separation of stamens and pistil takes place as a normal condition of many plants. Such separation may proceed to the extent of placing stamens in one set of flowers and pistils in another set on the same plant, or it may be illustrated by the more complete isolation of these organs, so that in the latter case we find all the flowers on one plant to be staminate and all the pistillate flowers to be borne on another plant. The lesser nettle, for instance, has its stamens and pistils in different flowers on the same plant, as also have the oak, melon, cucumber, maize, hop, hazel, carex, etc. The greater nettle, on the other hand, bears on one plant none but staminate flowers, and on another plant none but pistillate-bearing flowers, whilst hemp, willow, the variegated laurel, Aucuba japonica, palms, etc., also illustrate the complete separation of stamens and pistil. Other conditions more or less uniting these dispositions of the stamens and pistil may be found in flowers. In a daisy, which is a collection of flowers, we find the outer or white florets to possess pistils but no stamens, and the yellow and central florets to possess both stamens and pistil. We can readily discern that all such arrangements secure pollen of essentially foreign kind for fertilization. Self-fertilization is, in fact, impossible in such cases as those just described, and some very curious facts are found in botanical archives concerning the difficulties experienced in obtaining seeds where one of the necessary elements, usually the pollen, for fertilization was absent. The variegated laurel presents a case in point. The first specimen of this species introduced from Japan was a pistillate or female plant, and could produce ovules from its flowers, but no seeds, inasmuch as no pollen from another and staminate plant was forthcoming. The plant was largely reproduced from slips alone until within comparatively recent years, when staminate plants being imported, pollen was then forthcoming for the production of seed. The Egyptians have long been in the habit of bringing palm branches bearing stamens from the desert in order to fertilize the domesticated pistillate or fruit-bearing palms grown at home. This necessary process was frustrated in 1808 when the French occupied Egypt and when the stamen-laden branches could not, in consequence of foreign invasion, be procured. In the well-known Vallisneria spiralis, a water plant of southern Europe, which, like the willow and palm, has stamens and pistils on separate plants, the pistillate flowers are borne to the surface at the proper period by relaxing of a spirally coiled stalk on which they are supported. The stamen-bearing flowers, on the contrary, are borne on short stalks, and becoming detached therefrom, float to the surface of the water. There they scatter their pollen, which reaches the pistillate flowers, and the latter being fertilized are drawn by their stalks once more beneath the water, where the seeds mature and the fruit in due course ripens. The present is perhaps a fitting stage of our inquiries to remark that the tendency towards cross-fertilization in nature is nowhere more strongly marked than in cases where a plant is utterly infertile with its own pollen, but perfectly fertile when impregnated with pollen from another plant of the same species, or in some notable instances from an entirely different species of plant. Species of passion flowers have been found sterile with their own pollen, although slight changes in their conditions, such as being grafted on another stock, or a change of temperature, rendered them self-fertile. More extraordinary still, however, is the knowledge of the fact that the pollen of some orchids actually acts like a poison if placed in what one would have deemed the most natural position for it, namely on their own stigmas. Such facts as these entirely alter the former conception of a species as a group the members of which were fertile inter se, but infertile with members even of nearly allied species, and such knowledge supplies a wholesome corrective to the theory that species are separate, independent, and distinct entities both as to origin and after relations. If nature contrives by such means to effect cross-fertilization, there exist ample fields for the demonstration of a like result in other and very varied fashions. In a very large number of flowers, for instance, the stamens ripen and discharge their pollen before the pistil is ripe, or the ovules ready for fertilization. In other cases, but more rarely, the pistil ripens before the stamens. The former case is illustrated by most species of geraniums, pelargoniums, by harebells and other Campanillaceae, by many umbelliferous plants, by carnations, sweet william, and allied plants, and by many plants of the daisy and dandelion type, Compositae. The latter case of the earlier ripening of the pistil is illustrated by the ribgrass, Plantago, of the roadsides, by the cuckoo pint, Arum, and other plants. One or two familiar illustrations will suffice to show how clearly and effectually nature carries out her intention of securing cross-fertilization by different periods of ripening in stamens and pistils. The pink or carnation in its first condition exhibits the case of a plant possessing stamens alone. These organs ripen, discharge their pollen, which is carried by insects to flowers whose pistil may then be ripe, and then die away. After the stamens, and with them all chances of self-fertilization, have disappeared, the pistil matures, and its style and stigma develop fully. It is then fertilized by foreign pollen, that is, by pollen from a pink whose stamens are at that period in full development. So also is it with thyme, whose stamens ripen first, and with the Canterbury bells, harebells, and like flowers. In the Campanulas, anthers and pistil are closely related before the flower opens, and when the anthers discharge their pollen, it is shed upon the style or stalk of the pistil, and only after the stamens have shriveled up and their pollen has been carried away by insect agency to other bellflowers, does the pistil develop fully, and its three conspicuous stigmas open out so as to receive pollen from another and, at that period, pollen-producing flower. In cases like the preceding, therefore, it is evident nature does not intend that the flower's own pollen should fertilize its ovules. The opposite case occurs in Plantago, where the elegant little pistils ripen first, and where the stamens do not mature until fertilization of their flower has been accomplished by foreign pollen. In the cuckoo pint, Arum, there is also witnessed the ripening of the pistil before the stamens. Everyone knows this plant with its sheathing leaf and the central stalk bearing the flowers. The anthers are placed above the stigmas, hence it would seem at first sight as if nature intended that their pollen should fall downwards and fertilize the plant's own ovules. But the pistils ripen long before the stamens. When the latter are mature, the pistil has been already fertilized. Hence the pollen, it is evident, must be intended for fertilizing other pistils of the species, unless, indeed, we can maintain that nature, like Homer, sometimes nods. The pollen in this case falls to the bottom of the sheathing leaf, where it might well seem to be lost entirely to the outer world. Small insects, however, in due course arrive upon the scene. Entering the cavity of the leaf readily enough, on the principle of facilis descensus Averni, they find the reverse process, revocare grandum, to be impossible. By an arrangement of stiff hairs pointing downwards, which they readily enough brush aside on entering, they are prevented from escaping out of the flower. Hemmed in by this natural chevaux de frise, as in an eel trap, we may find inside an arum 100 or 2 small insects in durance vile. Here, however, they find nourishment in the honey secretion, and here they in due time work out nature's will, in that they become laden with the discharged pollen, so that when the opposing hairs shrivel and wither away, the insect crowd disperses itself and its units, undeterred by reminiscences of their imprisonment, entering other arums in which the stigmas have just ripened, duly cross-fertilize the latter. End of section 39. Chapter 14. The Fertilization of Flowers, Part 2.